Okay, the best tool for numerically approximating a function near a particular point x naught is the Taylor polynomial. And you developed the Taylor polynomial back in Calculus 2, where you found a polynomial that would match the function's value, the derivative at that x naught, the second derivative at that x naught, up to the nth derivative, all would match the function exactly at that x naught value. And so now the form of that Taylor polynomial was that, okay, so if we're approximating it at the point x naught, that means the terms are each going to have an x minus x naught. Well, you can assume there's an x minus x naught to the 0 for this first term. Then you have an x minus x naught to the first, an x minus x naught to the second, all the way up to the x minus x naught to the nth. So that'll give you an nth degree polynomial, and it's built to be of the form the x minus x naught, powers. So now each coefficient of those terms will be the nth derivative evaluated at the x naught over the n factorial. Okay, so the first term then, the 0th derivative is defined to be just the function's value itself at x naught. And then, of course, 0 factorial is just defined to be 1 as well. So we have that same form for this term. This term, it would be the first derivative evaluated at x naught over 1 factorial. Here's the second derivative evaluated at x naught over 2 factorial, and so on. And if you want to check here, let's check the derivatives. First off, if we just evaluated this polynomial at x naught, that's just replacing all the x's with x naught, you'll notice that every one of these terms will have 0 because of the x minus x naught expression, and so you're just going to get the f of x naught. So you'll see that this polynomial matches the function's value at x naught. Let's look at the derivative. P sub n prime of x, so I'm just going to take the first derivative of the right side here, will be f prime of x naught. Well, wait, f of x naught is just a constant, so that's just 0. Okay, the derivative of this, now you're taking the derivative with respect to x. So if I multiply this out, I have f prime of x naught times x, so that means it's going to have a derivative of just f prime of x naught. And then the f prime of x naught times x naught is just a constant, so it'd have a derivative of 0. Okay. The next term, to take the derivative of this, I'm going to take the constant, f double prime of x naught over 2 factorial, and then I'm going to multiply by the derivative of this, which is what contains the x. So using the power rule, it's 2 times x minus x naught to the first power, and then times just 1 for the derivative of the x inside. Okay. The third term, I'm going to take that constant, which is the f triple prime of x naught over 3 factorial, and then the derivative of the x minus x naught cubed is 3 x minus x naught squared times 1. Okay, and then I could keep going forever. But now if I evaluate that first derivative at x naught, so replace all the x's with x naught, I will have this first term, which is f prime of x naught. This becomes 0, and every term after that that has that same x minus x naught expression becomes 0. And you can see that the trend's going to continue. If you took the second derivative of, so take the derivative of this function again, it's going to end up that the second derivative evaluated at x naught will come out to be the f double prime at x naught. Okay, so this polynomial matches every derivative, the n derivatives at x naught. Okay, so exactly they match at x naught. It's just nearby. With all those derivatives matching, it's going to tend to have the same rates of change in every aspect, and which will cause to be a really good approximation. Okay, so let's find the first 4 Taylor polynomials for e to the x expanded around x naught equal to 0. Now, if we're using x naught equal to 0 for the place that we're expanding this makes the problem much simpler. That's called the Maclaurin series. Okay, so our Taylor polynomial then simplifies. So here's the Taylor polynomial. If the x naught is just 0, we're going to have just x to the jth power, and then we'll have the jth order derivative evaluated at 0 over j factorial. Now this is an infinite series. If you're finding the nth derivative of this, you're just going to go up to, I mean, if you just want the nth polynomial, you're just going to go up to n. So what this is saying down here is that the Taylor polynomial Pn is just the n plus first partial sum, where you're just taking those first n plus 1 terms of that Taylor series. So back to this other problem, we're trying to find an approximation for e to the x. That's our f of x. And we know by Taylor series that the nth, okay, we want the first 4 Taylor polynomials. Now the nice thing about the Taylor polynomials is they build on themselves. So if we can get the 4th degree polynomial, I have the first, second, and third degree is the first, second, and third partial sums of that as well. So let's just go ahead and get the 4th degree polynomial, and then I'll show you from there. So we want p sub n of x. And for the Taylor polynomial expanded around 0, that'll be of the form f of 0 okay, so it's f of x naught plus the f prime of 0, and then we'll have x minus 0, and that's all over 1 factorial. Then f double prime of 0, x minus 0 squared over 2 factorial, f triple prime of 0 over 3 factorial, x minus 0 to the third. Okay, so the first 4 polynomials, the first polynomial will be just this. So P1 would just be whatever f of 0 is. P2 will be the first 2 terms. P3 is add 1 more term, and P4 will be adding an additional term. Okay, so let's find these values. To do these, I need to have the function evaluated at 0, the f prime at 0, the f double prime at 0, f triple prime at 0. So I need to find those values. So I'm going to come over here to the side, and I know my function is f of x equal e to the x. So let me find up to the third derivative. F prime of x is e to the x, f double prime of x is e to the x, and f triple prime of x is e to the x. So now just evaluate all those at 0. F of 0 is e to the 0, which is 1. F prime of 0, again, will be 1. So let's get all these values, and then we'll just plug them in. So I know this is 1, this is 1, this is 1, and this is 1. That's what I just found. So this comes out to be 1 plus 1 times just x plus 1 over 2 factorial. Remember, factorials just start with that number and multiply every number below that down to 1. So 3 factorial would be 3 times 2 times 1. Okay, so this will be times x squared plus 1 over 6 x cubed. Okay, so this would be our P3. Okay, so P0 is just 1. P1 is 1 plus x. P2 is 1 plus x squared over 2. So notice each time we just get a little more accuracy by adding that additional term. So you can actually determine how many terms you need to add to get whatever accuracy you need, because you can determine errors as well. Okay, so there's our first 4 Taylor polynomials for e to the x, where we expanded it around x not equal to 0. If you look at the graph over here, the first polynomial, P0, notice is just, well, it'd actually be a constant function. P not equal to 1. This will be the function that just matches the function's value itself, but notice it doesn't match the slope, rates of change, or concavity, or anything like that. The second one, P1 here, is the line 1 plus x, which would be this one. So there's the P1. P2 will be a quadratic, right? It's just a parabola. Okay. So each of those is matching. Now, e to the x, if you look at the graph of e to the x, which is on this graph as well, This is e to the x. And so notice as you add one extra term, those polynomials, we start with the horizontal line, then the other line, and then the quadrat, those are getting closer and closer to, and then we had a cubic equation down here, which notice that. They're getting closer and closer to the function's values, the e to the x values, further away from x equals 0. They all match at x equals 0, but the further away, the higher degree polynomial will better approximate values farther away from x equals 0 and more accurately. Okay, let's look for the fourth degree polynomial. Okay, so now fourth degree polynomial, that means we need to go up to the x to the fourth term. And we want to match the function cosine of x at x not equal to 2. So we're going to have, this is a polynomial in the expression x minus 2. Okay, so let's first write out what the form is going to look like. The fourth degree polynomial, so P4, will be the function evaluated at that. Now they're not looking to plug in a specific x value, so we're just going to have, well, it's still just f of the 2, whatever the value is that you're building it around, plus f prime of 2, x minus 2 over 1 factorial, plus f double prime at 2, and then getting up to the fourth degree polynomial would be f. And now sometimes they'll, instead of, they put the Roman numerals after 3, so then we just put a little 4 with parentheses around it to indicate it's the fourth order derivative. And when they expand these around a different point, they don't multiply this out. They leave it as x minus 2 to the power. Because if you're plugging in numbers near 2, which is where the approximation is best, it's easier to evaluate if you have it left like this. Okay, so that's our fourth degree polynomial that'll match it. So now to find that actual polynomial, we just need to fill in the values for f of 2, f prime of 2, f double prime of 2. Okay, so let's find those. So over at the side, I know my function f of x is cosine of x. So that means f prime of x is negative sine of x. F double prime of x is negative cosine of x. Triple prime is sine of x. F4 is cosine of x. And notice here we're going to be repeating because these 4 values we'll just keep repeating over and over after that. Okay, so now we're evaluating them at 2. So we're going to have f of 2 is cosine of 2, f prime of 2 minus sine of 2, f double prime of 2, and f triple prime of 2. Okay, so now let's build our polynomial. We know P4 of x is f of 2, which is cosine of 2. F prime of 2 will be minus sine of 2, okay, over 1 factorial, which is 1, times x minus 2, plus we have our f triple prime, or f double prime, which is negative cosine of 2, x minus 2 squared over 2 factorial. F triple prime, there's sine of 2 over 6, which is 3 factorial. And then we're back to cosine of 2. 4 factorial will be the 4 times the 6, so it's 24. X minus 2 to the 4th. Okay. There's not a lot of simplifying you can do to that. We want to leave it as a polynomial with the expression x minus 2. If you plug in 2, you're going to see that all these, the second to the the fifth terms all go away because of the x minus 2, and you get just cosine of 2. So it will agree at that value. But this is the fourth degree Taylor polynomial that matches cosine of x at x naught equal to 2. Okay, let's find the first few Taylor polynomials that approximate the solution for this differential equation with the initial values that are given around x naught equal to 0. We'll mostly work with x naught equal to 0 just to simplify it. Everything else will be a shift if you want to do it at another value. Okay, so let's look at what the Taylor polynomials will look like. We know that p sub n will be the function y evaluated at 0 plus y prime at 0 times x to the 1. Now it's x minus 0, so we just put the x, plus y double prime at 0, x squared over 2 factorial, okay, let's just go up to the fourth or fifth. So it would go, in general, goes up to the nth order derivative, evaluated at 0, x to the nth over n factorial. Okay, so that's your nth polynomial. Let's just see what that looks like. Well, first off, notice that we're given y of 0. That's our initial condition 10. So this is 10. Y prime of 0 is 5. So if we have initial conditions, we can already start filling in and get our first and second polynomials. So now we need to find y double prime at 0 here. Now we're not given that, but we are given what y double prime is. So I'm going to go over here to the side and say, okay, since y double prime is 3y prime plus x to the 7/3 y, that means then that y double prime at 0 will be 3 times y prime at 0 plus 0 to the 7/3 times y of 0. All I'm doing is changing all the y's to be evaluated at 0 and then putting in 0 for the x. So that means y double prime of 0 will be 3 times whatever y prime of 0 was, which is 5. And then this term will make the following term 0. So it's just 15. Okay, now I need y triple prime at 0. I'm not given y triple prime, but I can easily take the derivative of this and get y triple prime. So y triple prime, notice I'm taking the derivative with respect to x, is 3 times the derivative of y prime, which is y double prime. Now here I have to use the product rule because y is a function of x and x is our independent variable. And all these derivatives are taking the derivative with respect to x. So I'm going to have 7/3 x to the 4/3 times the y plus x to the 7/3 times the derivative of y, which is y prime. So that means that y triple prime at 0 will be 3 times y double prime at 0 plus 7/3 times 0 to the 4/3. And notice all the other terms are going to have this x to the power that'll be a 0. So this comes out to be just 3 times y double prime of 0, which was 15, gives us 45. Okay, so this one is 45. Okay, let's look at y to the 4th. Take the derivative again of this. Derivative of y double prime is y triple prime. Again, I need the product rule here. So that's going to be 28/9 x to the 1/3 times y plus 7/3 x to the 4/3 times y prime. Product rule in the last one, 7/3 x to the 4/3 times y prime plus x to the 7/3 times y double prime. Okay, evaluated at 0. That'll be 3y triple prime at 0 plus 20. Now notice every other term from here on has an x in it, and so when you plug in the 0 for the x, all these other terms will be 0. So this comes out to be just 3 times y triple prime at 0 is 45. Okay. Okay, let's look at one more. Fifth derivative. Okay. I'm going to have 3 times y to the fourth derivative. Here I'd have 28 over 27 x to the negative 1/3 times y plus, and then I'd finish off that product rule and then the derivatives. I want you to notice something here. This term has an x to the minus 1/3 in it, which is equivalent to 1 over x to the positive 1/3. So now if I evaluated it at 0, that's no longer defined. So we can't evaluate y to the fifth. So these terms have to go away. The highest derivative, Taylor polynomial, would be P4. So let's write down those polynomials. We have that P0 is just 10. P1 will be 10 plus 5x. P2 is 10 plus 5x plus 15 halves x squared. P3, that's always the same first terms, with one extra term added each time. So we're going to have 45 over 6 x cubed. This would reduce, divide both by 3, it'll be 15 halves x cubed, and then we'll have plus 135 over 24 x to the fourth, and that will reduce down as well. So this is just 15 halves, and this one both divide by 3, so this one's going to be 45 eighths. Okay, so there's all of the Taylor polynomials that actually exist for that would be solutions. So they're giving us solutions, approximations to the solution of that differential equation. Okay, let's look at another example. I want the Taylor polynomial of degree 3 for the solution to the initial value problem. So again, I've got y of 0 is 0. Let's look at what our polynomial is going to look like. We want the degree 3. So that means that now we know we're evaluating this at x equals 0 because they're giving me the initial condition at 0. So we are expanding this around 0. Okay, so that's what we want to find. So we already know y of 0 is 0. We can find y prime of 0 by just evaluating this function. So y prime, so that means y prime at 0, we're putting 0 for the x, will be 1 over 0 plus y at 0 plus 1. Y of 0 was 0 as well, so that gives us just 1. Okay, now, so we have this is 1. So now let's find y double prime, and we'll get that by taking the derivative of this. Okay, so we're going to need the quotient rule to take the derivative. Okay, so we're going to start with the x plus y plus 1 times the derivative of 1 minus the 1 times the derivative of the bottom, which will be the derivative of x is 1, the derivative of y is y prime, and then the derivative of the last one is 0. So that comes out to be negative 1 minus y prime over x plus y plus 1 squared. So now let's evaluate. Y double prime at 0 will be negative 1 minus y prime at 0 over 0 is the x plus y at 0 plus 1 squared. So that's minus 1 minus y prime of 0 up here was 1. Y of 0 was 0 plus 1 squared. So that's going to give me just negative 2. Okay, and one more. I need to find the derivative of this now. So y triple prime, again using the quotient rule, whoops, to the 4th power now, times the derivative of 1 minus y prime, derivative of negative 1, 0. The derivative of y prime will be y double prime. We'll have minus times the derivative of the bottom using the power rule will be 2 times x plus y plus 1 to the 1st power times the derivative of the inside, which will be 1 plus y prime. Okay, instead of cleaning that up, I'm just going to evaluate it now. We have that y triple prime at 0 will be 0 plus y at 0, which was 0. We'll have 1, so 1 squared. We have minus y double prime at 0, which was negative 2. So we have that other negative in front of it, so it's going to be a positive 2. Okay, now we have a bunch of negatives here. I'll just keep them so it doesn't confuse anybody. Y prime at 0 was 1. And we have 0 plus y at 0 was 0. And then we have times 1 plus y prime at 0 was 1. 0 plus 0 plus 1, so we have 1 on the bottom. So we've got 2 minus negative 4. Wait, that's times 1 times 2. Okay, so that makes it 2 plus 8 is 10. Okay, so that was the y triple prime. Okay, so let's look at our polynomials then. Our first polynomial, P0, will just be 0. P1 will be the first two terms, so it'll be 0 plus 1x. P2 is 0 plus 1x minus 2 over 2 factorial times the x squared. And then P3, and then the last term we had 10 over 6. Well, the 10 over the 3 factorial, which is 6, will be 5/3. Okay. Oh, so if we just want the polynomial of degree 3, I didn't need to find the others. I just needed this one right here. So that's the solution to that differential equation, and we gave a 3rd degree polynomial approximation. Okay, so we can get Taylor polynomial approximations to these differential equation solutions but we are limited to how many times we can take the derivative, as the previous example showed, where we couldn't take a derivative anymore at that value. If you want to find the accuracy, the amount of the error of the polynomial approximation will be whatever the function's value is minus that polynomial. So that gives you the error for any x value. That error can actually be estimated by looking at the n plus first derivative at some number. This symbol here represents some number that's between the x0 and the x. So if you just found what the largest value of that function, that n plus first derivative would be for any values in that interval, then you can get an upper bound for that error. So this is what the form of the error would be. So if you wanted to make this as small of an error as possible, you could take the n to be larger because you'll have that n plus first derivative in the denominator. So the bigger the n, the larger that value will be in the denominator, which will cause the error to be smaller as long as you're able to continue taking derivatives. So the more derivatives you take, the higher order of the derivative, the polynomial that you use, the smaller the error will be. Okay. Here in the past, we found solutions to differential equations that were of the form linear combinations of polynomials, sines, cosines, exponential functions. Okay. Often you're not able to get solutions that are in that form. So when you can't, the next method that we might try is to get a power series solution. So that's going to be where we have an infinite series that approximates what the solution is of the differential equation. So a power series about a point is just an expression that's of this form, where you have a constant, the a sub n's are constants, and then you have an x minus x naught to an nth power for each term. Okay? So if you think of this as like an infinite polynomial, you have a constant term, a constant times the x minus x naught, constant times the x minus x naught squared. So you've got it as a polynomial in the term x minus x naught. Okay, what that does is it causes it to be centered at the value x naught. Okay, x here is the variable. Okay, now a power series is convergent at a specific value of x if the sequence of partial sums converges. So if we take the sum of the first n terms and then just keep adding an additional term by letting that n get larger and larger, if those values have a limit, they're approaching a specific real number, then we say that it converges. So the limit of the partial sums is defined to be the limit of the sum of the first n terms of this power series as that number of terms goes to infinity. Now, if the limit does not exist at a value, then we say that the series is divergent. Okay, now every power series has an interval of convergence. Okay, it's the set of all the points, all the numbers x for which the series converges. Now, the center will always be x naught of the series. We know the function will converge, or the series will converge at x naught. Okay, it will just be the function's value at that number. So we know it converges there. If that's the only place it converges, then we say that the interval of convergence is 0. So if the series only converges at x naught, then the interval of convergence, we're calling rho, this number rho, which is just some real number, something between 0 and infinity, is called the radius of convergence. So if the series only converges at x naught, the radius is 0. Now, inside of that interval of convergence, a power series will converge absolutely. So if we have some interval, radius of convergence, rho that's not 0, so we'll have some interval here from x naught minus rho to x naught plus rho. So inside that interval, the series converges absolutely. And what that means is that if we took the sum of the terms from 0 to infinity and took their absolute values, then that sum of all those positive values would converge as well. So converging absolutely just means if adding up all the absolute values of the terms does converge. Now, what we don't know, though, is whether it converges at those endpoints, at the x naught minus rho and the x naught plus rho. We'll have to check those numbers out independently. But if rho is the radius of convergence, then that's half of this length of the interval from here to here. And so 2 times rho would be the length of that radius of convergence. So we know the series will converge absolutely for x minus x naught. So any x in here whose difference from x naught is less than rho. Okay, so this will be our interval of convergence if that rho is a number bigger than 0 and not equal to infinity. And it will diverge then outside of that interval. So anytime the x, when you subtract it from the x naught, is larger than the rho. So that would be talking about all the values out here and out here. Okay, that's if rho is a finite number. Okay, now if the series converges for any x, then we say that the rho is equal to infinity, and that would be the entire number line. So the interval of convergence in that case would be from minus infinity to infinity. Okay, so now we want to find that interval of convergence. We want to find the x values so that this infinite series will converge and give us a value so that then we'll know where that differential equation solution will have a finite value. So the series will only be a function's value if the series converges for that given x. Okay, so now to test it, we're going to use the ratio test for power series. Now, this is a little bit different from when we did it in Calculus 2. If for large n, the coefficients, the a sub n's, are non-zero and satisfy this. So if you take the limit of the a sub n over the a sub n plus 1 term, so just 2 consecutive terms, if that limit is some real number L, well, you could actually have it be an infinity as well, but take that limit, and then that will be the radius of convergence for the power series. Okay, so just find the limit of the a sub n over a sub n plus first term, and that will be that radius of convergence. Okay, so let's look at an example. I want to find the interval and the radius of convergence of this power series. Okay, so to do that, I need to find what the radius of convergence is, and I do that by taking the limit. Now this a sub n over a sub n plus 1, we want the absolute value of that. That means if there's a negative sign, we don't have to worry about it. The negative will go away from the absolute values. So we are not worrying about this x minus x naught term, just the a sub n, which was the part in front of that. Okay, so the limit of the a sub n over the a sub n plus 1, its absolute value, okay, now a sub n is just going to be minus 2 to the n over n plus 1. So it's whatever that term is. And now over the a sub n plus 1. So just replace the n's with n plus 1. Putting the n plus 1 for the n. So I'll really have n plus 2 there on the bottom. Okay, now I'm going to invert and multiply here. This is the same thing as minus 2 to the nth. Okay, so we invert the bottom fraction. We'll have n plus 2 over the minus 2 to the n plus 1. Okay, I'm going to group the terms that are similar. Okay, and when you simplify, you have a single minus 2 on the bottom. So that's 1 over just a negative 2. And then the n plus 1 over n plus 2 over n plus 1. Okay, so that ends up being just 1/2. If I want to take the absolute value of the negative 1/2 and pull it out in front, that's the limit then of n plus 2 over n plus 1. As n goes to infinity. I don't need the absolute values anymore because the n's are something bigger than 0. And so I just needed it for that negative 1/2 that was there. Okay, so now if you recall, the limit of an expression n plus 2 over n plus 1 as n goes to infinity is simply going to be 1. So this is 1/2 times 1, which is 1/2. Okay, the way you did that back in Calculus 1, well, you did it in algebra by looking at the powers of the top and the bottom when you were looking at limits as n goes to infinity. And when they had the same power, you just took the ratio of the numbers in front, which would have been the 1 here. Or you also did it in calculus where you looked at the limit, you looked at what the biggest power of the variable was in the denominator, which was n to the first, and you divided the top and the bottom by it. So if you divide top and bottom by just an n to the first power, this becomes a limit of just 1 plus 2 over n over 1 plus 1 over n. And you can see as the n goes to infinity that these two terms will go to 0. So that does just give you a limit of 1. So what we have here is we have that the radius of convergence is 1/2. So that was the row. Okay, so now if you want to find the interval of convergence, well, the interval of convergence will just be absolute value of x minus 3. So you want all the x values within 1/2 of 3. So the absolute value of x minus 3 then would be less than 1/2 is the interval of convergence. Okay, so if you want to remove the absolute values, that's minus 1/2 less than x minus 3 less than 1/2. So that means that the x is between 5/2 and 7/2. Okay, so there's your interval of convergence. Now the only thing we aren't sure about though on that is what about the endpoints? We need to check 5/2 and 7/2 and see if they actually, the series will converge at those points. So checking endpoints. So that's just the interval where it converges absolutely, right, so far. So we're going to look at x equals 5/2, and I'm just going to plug it in to the series. We're hoping to get a series that we actually recognize from Calculus 2, and we'll know the convergence of it. So when I put 5/2 in for the x, I get 5/2 minus 3, so that's negative 1/2 to the nth power. Well, we have minus 2 to the nth, and this term this is the same thing as the minus 2 to the nth in the denominator. Or if you want to look at it as these both have the same exponent, so we can just take the minus 2 times the minus 1/2 and combine those. So either way, whichever way you feel most comfortable here. This is the same thing as minus 2 times negative 1/2 to the nth power, and then we've got that single n plus 1 in the bottom. Okay, so that ends up being just a 1 to the nth, which is just 1. So this is the sum of 1 over n plus 1. Okay, now this is very similar to the harmonic series. If you recall, the harmonic series was the sum of 1 over n. So that was n equal 1 to infinity. So if you expand this out, this was 1 plus 1 over 2 plus 1 over 3, and so on. This one just has a different value. It starts at n equals 0 and has n plus 1 on the bottom. But if you expand it, you have 1 over 1, 1 over 2, 1 over 3. It is the harmonic series. It just has different counters. The indexes are different. So this series, if you recall, the harmonic series diverges. Okay, it's that p series where the p is equal to 1. Okay, so now let's check the other endpoint, x equals 7/2. Well, the series becomes negative 2 to the nth over n plus 1. And then we have 7/2 minus 3, so we'll have a 1/2 to the nth power. Well, that's just going to be the series of minus 2 times 1/2 to the nth over n plus 1, which gives us a negative 1 to the nth over n plus 1. So what we have here is we have the alternating harmonic series. And if you recall, the alternating series test says if you ignore the minus sign and the other terms, the 1 over n plus 1, go to 0, which they do, and it's a non-increasing series, the numbers are getting smaller as they go, we're ignoring the minus sign, then it converges. And so the alternating harmonic series does converge. Okay, so our interval then of convergence will include the 7 halves but not the 5 halves. One property that we're going to be working with as we find these power series solutions is called the identity property, or the book refers to it as power series vanishing on an interval. It says that if you have a power series equal to 0 for all x in the interval, then the only way that can happen is if each of the coefficients is equal to 0. So we have a power series now that we'll say converges. So for every value that it converges for, we're going to denote that with a function. So for each x that it converges for, we're going to call that f of x. So the x will be a specific value, and it'll have a different value depending on what the x is. So this will be a function's value. Now, if you recall back in Calculus 2 and probably even college algebra, you had a geometric series, and you knew the sum of this geometric series. So it was of the form 1 plus x squared plus x cubed, and so on. This was just an infinite series where you were multiplying by that same ratio from one term to the next. So it's a geometric series. The sum of this geometric series was the first term, which in this case is 1 over 1 minus that ratio. Okay, because this series converges. Now this series converges only for the x values between -1 and 1. So on the interval from -1 to 1. So because we know it converges for those values, we call this function f of x equal either that series, the series of x to the n for n equals 0 to infinity, or f of x equal 1 over 1 minus x. So we just use the function f to refer to what that sum is, the convergent value, just on that interval. Okay, so now if we have a series that has a positive radius of convergence, so we know that there's more than just the x naught where it converges for, then that series will be, the function that it represents will be differentiable on that interval. Okay, so if the function exists, the series converges for all the points in that interval, the derivative will also exist for all the points on that interval. Now that's the points on the inside of the interval. Okay, so it's only talking about the interval. Those are the values of x between x naught minus p and x naught plus p. Now, I'm calling it p now. Rho, p, I'll interchange it. So to find that derivative, we just take the derivative of each term individually. So if you have it written in this form, remember x is your variable, the derivative of this would just be the a, that constant, times n, remember bring the exponent down in front, and then take that x minus x naught to 1 less power. Okay, so this is just the derivative of that function, even when it's represented as a power series. Okay, and that's going to be true just for the x's, again, within rho or p of that x naught. Now, also, if that power series converges for values in an interval, so we have a function that's representing what that convergent value is, then we can do integration. And the integral, the antiderivative of that function, will also exist for all the values in that interval. So we can do term by term integration. So if you have this function for f, then integration would just be taking the a sub n term, now taking the term that has the x minus x naught to 1 larger power, and then divided by the n plus 1, dividing by that new exponent. So that's just doing the integration of one term, just like you did back in Calculus 1. So now the integral, the antiderivative, will exist also for all values inside that interval if the function was convergent in that interval. So it's just saying we can form new power series from ones that we have by taking the derivative of both the power series and the function, or we can integrate the power series and the function to get new functions, new power series. So I'll show you some examples here. We're going to start with the geometric series. Okay, so this is one of the the one you pretty much start and build from. We know that if you expand it out, this is 1 plus x squared plus x cubed, and so on. Or if you write it in summation notation, it's just x to the n, letting the n go from 0 to infinity. So that's the summation form. But that converges to 1 over 1 minus x. So this is the function's value for the x's only between -1 and 1, because those are the only times it's going to converge. If you used other x's, it will just keep getting larger and larger, and it won't approach a fixed value. We want to find new power series using that one and the fact that we can compose functions with it. So we can replace the x with another polynomial, or we can take the derivative of it, or we can take the antiderivative of it. Okay, so now I'm going to compare 1 over 1 plus x squared. I'm trying to find a power series for this function. I know a power series representation for 1 over 1 minus x. So if I want to find the representation for 1 over 1 plus x squared, I can simply replace the x in this one with minus x squared. So I'm composing this function. So what I'm essentially doing is I'm finding f of minus x squared. So replace x with minus x squared in here. So I would have 1 over 1 minus negative x squared equal 1 plus negative x squared plus negative x squared squared, negative x squared cubed. And then in the summation form, I'll do the same thing. So that's minus x squared to the nth. Now, when you do compositions, it will have the same interval of convergence, just like differentiation and integration. So the interval of convergence here will be from -1 to 1. Okay, so now that means then that 1 over 1 plus x squared is equal to 1 minus x squared and plus x to the 4th minus x to the 6th, multiply exponents, plus x to the 8th. Now we can write this as -1 to the nth, if we want to break up the -1 and the x squared, and then just x to the 2n, just using some of our exponent rules. So there's a power series. We know it converges on the interval from -1 to 1. So we have a series representation now for 1 over 1 plus x squared, and it's this right here. Let's put off the equal. Okay, so now let's look at a power series representation for 1 over 1 minus x squared. Now notice we can't replace x with something in this original power series up here to get this. But notice that we have 1 minus x in the denominator of the geometric series, and here we have the 1 minus x squared. Okay, so if you think about when you took a derivative of 1 over x back in Calculus 1, the derivative of this with respect to x was minus 1 over x squared. Remember, this was x to the -1, and so you've got minus x to the -2. So maybe if we take the derivative of this power series, the geometric series, we would be able to get an expression that contained 1 over 1 minus x quantity squared. So let's do that. We're going to differentiate the geometric series. So the left side, I'm taking the derivative, so I'm going to use the quotient rule. 1 minus x squared in the denominator, 1 minus x times the derivative of the top minus the top times the derivative of the bottom, which is minus 1. So now, if you simplify that, that becomes just 1 over 1 minus x squared. So now let's see what the power series representation would be. Well, if we use the expanded form and just take the derivative term by term, we would have 0 plus 1 plus 2x plus 3x squared, and so on. Or if we work with it in the summation form and just do the term by term integration of differentiation, we would have the sum of n times x to the n minus 1. Now, hold off putting the indices here, the counter, because I need to know what will the value start with. Notice if I started with 0, I would have a 0 times x to the negative 1, which isn't going to be a part of the summation. You can see here there's not an x to the minus 1 term. So let's just start with n equal 1 then to represent this. So if you do it in the, take the derivative of the expanded form, you can see what the terms, individual terms, will be, and then that allows you to set your index to start at the right value. So now just checking to see if this is correct. If I put in n equal 1 into this form, I would have 1 x to the 0, which is this first term. And then n equal 2, I would have 2 x to the 1, which is the second term, and so on. So you can always check this summation form with the expanded form to make sure that you're actually representing the same values if you expanded it out. So our power series representation for 1 over 1 minus x quantity squared is either 1 plus 2x plus 3x squared plus so on, 4x cubed and so on, or you could write it as just n times x to the n minus 1, starting with the counter of n equal 1 to infinity. So that's a power series representation now for 1 over 1 minus x quantity squared. So we've now got 3 different functions that we have their power series representations for. Now, taking the derivative term by term only gives us valid values in the same interval of convergence. So again, this is only valid for x's between -1 and 1. So now let's look at arctangent. Arctangent, that's inverse tangent, if you recall that. Inverse tangent, the memory that I have of it from Calculus 1, the inverse tangent or you probably wrote it as inverse tangent of x. Now I remember the derivative of that was equal to 1 over 1 plus x squared. Okay, so that's probably what you remember from Cal 1. So that means that if I wanted to find an expression for the inverse tangent of x, then I could just take the integral of both sides. So I would have inverse tangent or arctangent of x equal the integral of 1 over 1 plus x squared. Well, I have an expression for 1 over 1 plus x squared. I do know what that power series representation looks like. So I'm going to integrate that to find inverse tangent. Okay, so I have inverse tangent of x will equal to the integral of 1 over 1 plus x squared, which I'm going to look at the expanded form. That helps me to check to make sure I'm doing the summation correct. I'll have 1 minus x squared plus x to the 4th minus x to the 6th. Or integrating term by term, I would have the summation of the integral of the minus 1 to the nth x to the 2n. Okay, so looking at the expanded form, I've got 1. Well, the integral of 1 we know is x. The integral of x squared is x cubed over 3, x to the 5th over 5, and so on. Okay, so that's the expanded form. So let's see what we would get if we did it just using the general expression in that summation. I'm going to have the minus 1 to the nth, x to the 1 bigger power over the new power. Okay, so now let's see what that looks like. If I plugged in n equals 0, I'm going to have an exponent of x to the 1 power, which is what I want. So let's start with n equals 0 and see if that works out correctly. N equals 0, I'll have minus 1 to the 0, which is 1, x to the 0 over, x to the 1 over 1. And that's exactly the first term that I want. N equal 1, I'll have a negative 1 to the 1 power, which is a negative, x to the 3 over 3. And so that does give me this expanded form. So inverse tangent or arctangent of x is equal to either x minus x cubed over 3 plus x to the 5th over 5, Or in the summation form, we'll start with n equals 0. We'll have minus 1 to the nth, x to the 2n plus 1 over 2n plus 1. And now integration also preserves that interval of convergence, so we know that this will converge for all x between -1 and 1. Okay, so that's how we can get new power series from previous ones that we know: integration, differentiation, and compositions. Okay, now we're going to look at working with the summations to change the way that we represent the series. Okay, so when we start working with differential equations, we're going to substitute this power series form into the equation for the variable that we're looking for, the function y that we're trying to find. And so to do that, we're going to often have to add two different summations. Now, to add two different summations and be able to do them term by term, they have to have matching indices. Their variable needs to be the same, and the indices need to start at the same place. Like if one of them's in n equals 0, the other one has to be in n equals 0. So we have to be able to adjust the indices so that we have expressions that can then be added term by term. So I want to express the series. Now this one is starting with n equal 2, and notice it has an x to the n minus 2 as the power on the series. I want to write it with just a general term, x to the k, instead of the x to the n minus 2. So I'm going to change, I don't want the exponent to be n minus 2. I want it to be just the single variable. So to do that, I'm going to look at the form that they want me to have it in. I want a k for the power. And so that means I'm just going to let the k equal to the n minus 2. Now to do that, though, that's going to adjust the indexes that, just like the limits of integration, we have to adjust the indices based on this change. And all the terms here that have the n included will have to be adjusted as well. Okay, so to do that, we know k has to be n minus 2, which means that the n will be k plus 2. And also, when the n is 2, which is that lower counter, the lower indexes value to start with, when n is 2, that means that the k will be 2 minus 2. So the k will start with 0. So we're changing the series. That is the smart board itself that flakes out. Okay, so now I'm going to replace n with k plus 2 throughout the expression. And the n equal 2 will become a k equal 0. So n is k plus 2. We'll have k plus 2 minus 1. We will have a to the k plus 2, x to the k plus 2 minus 2. Simplifying. And k goes from 0 to infinity. So we have the same exact values. If you expanded this out term by term, you will have the exact same values in that expanded form. It's just we have it now where we have the x to the k instead of the x to the k minus 2. The variable you use is totally irrelevant. We could have had the first one all k's, starting at k equal 2, k times k minus 1, a to the k, a sub k, x to the k minus 2. The variable is irrelevant, but the form of that is what we're going to be looking at, because we're going to have two different sums match when we start combining them, because adding like terms means the x squareds have to add with the x squared. So we need to make sure we have our like terms, easily recognizable. Okay, so the second one here, I want to show that this is the same thing as this. Okay, so now notice that first one is just multiplied by an x to the third. So let me take that first expression, the x cubed times this summation, and I'm going to distribute that through the sum. Remember, the summation is just an infinite number of things added together. So I'm just going to multiply each of those by the x cubed. So I'll have the sum and then I'll put the x cubed here times the x to the n that's already there. And so now just using our rules of exponents, we know that that's just equal to x to the n plus 3. Now again, just like in the last problem, what if we don't want an n plus 3 for the power? We might just want the single variable, something that agrees with whatever the variable is in the index. So I'm going to make a change. I'm going to change this to k. So I'm going to let k equal to n plus 3. We're starting here with an n equals 0. So when n equals 0, the k will be 3 then. Okay, just by plugging that in. Also, since we're going to be changing the n's to k's, it's easier if we look at this equation as n equal k minus 3. So then we'll just replace all the n's with k minus 3. So this becomes the summation. So instead of n's, we're going to have k starting at 3. The n squared will be k minus 3 squared. Then we have k minus 3 minus 2, a sub k minus 3, x to the k minus 3 plus 3. I replaced every n with k minus 3. Now notice I didn't have to worry about the infinity for the k values, because if n was infinity, k is still going to be infinity. It's just 3 more, than that, which is still infinity. So then we have k minus 5, just simplifying, a sub k minus 3, x to the k. Now again, the variable name totally doesn't matter. This is equal to, let's just change it back to n. We used k just so it wasn't confusing when we were making the substitution. But what variable you leave it in is totally up to you. Okay, and that should match this perfectly. Okay, so if you have to multiply by a power of x like this, you can do it through each term and then combine them, and then you might have to adjust counters in the variables as well, the indices again. Okay, so I want to show that this identity is 0, and that means that the A0, A1, A2 have to all be zeros, as well as the A sub n relationship with the b's in that second expression. So we're starting with two summations. We want to add a summation of n equal 1. I'm not going to put the infinity just for less clutter. And I want to add that to a summation here that starts at n equal 2. Okay, so now to combine these, if I'm going to combine them term by term, they have to have the same matching powers of x. So in the first one, if I plug in the lowest index value of 1, this becomes x to the 0. When I plug in n equal 2, this would be an x to the 3rd. So right now I can't add those, because one of them would be starting with an x to the 0 and one would be starting with an x to the 3rd. So what I'm going to do is I'm going to kind of parse out terms here until I get the summation remaining with just an x to the 3rd power. So now notice that if n equal 1, okay, for n equal 1, this will be x to the 0. So this entire term here for n equal 1 will be 1 times a to the 0, x to the 0. Just plug in n equal 1 into everything. Now, n equal 2 will be 2 a sub 1, x to the 1. N equal 3 will be 3 a sub 2, x to the 2. Okay, I pulled off the terms that have lower powers than where this one starts. So now the next value I would be plugging in would be n equal 4. So instead of actually separating it out in expanded form, I'm going to leave the summation with 4 and up. Okay, so this entire thing is equivalent to this first summation. All I did was I changed it so that the terms that didn't match the second one were separated from the summation. So now, notice when n equal 4 in this summation here, it would be 4 a to the 3 x to the third. That's the main thing, is the fact that the x would be to the third power. Okay, now the second summation, we already started with x to the third, so I'm not going to touch it. I'm going to leave that one the way it is, because now I know that these two summations, this one and this one, both start with x to the third. Okay, so I would be able to, if I combine them term by term, I will be adding like terms, same powers of x. So now to do that, though, I have to have matching indices, the matching variable, and starting at the same place. Because I matched them to make sure they had the same exponent first, I know that when I switch it to a different variable, they will both be able to start with the same value for the index. Okay, so these I'm just going to kind of let come along. They're just going to trail out here. I'm going to have a0 plus 2a1x plus 3a2x squared. And now this second summation, or this first summation here, I'm going to change the variable. I want to make it a single power for the exponent. So I'm going to change the n minus 1 to k. That means that if n was starting at 4 here, so when n equals 4, the k will be equal to 3. Also, this tells me that n is just k plus 1. Okay, so now let's switch it over. I know the index is going to start at k equal 3. The n becomes k plus 1. K plus 1 minus 1. X to the k plus 1 minus 1. Okay, so this becomes and that's where the k starts at 3 and goes up to infinity. Okay, the second summation right here. I want to do the same. I want a single power up here. I'm going to let k equal to n plus 1. Well, that means when the n is 2, the k is going to start at 3. Also, this tells me that n is just k minus 1. So now, making the substitutions, we're going to start with k equal 3. We're going to have b to the k minus 1, x to the k minus 1 plus 1. Just replacing the n's with k minus 1. And so that becomes b sub k minus 1, x to the k. Okay, now we're ready to combine our two summations. They now both start with x to the thirds. So if I want to combine them, I'm just going to be combining them term by term. So make one summation out of these. We're going to start with k equal 3 to infinity. I'm just going to say, okay, we'll have k plus 1 times a sub k plus the b sub k minus 1, and all of that times the x sub k. All I did was I combined the terms in the summation and factored out the x sub k. Okay, so we've got one summation now. Now look at this. We now have a power series on the left, okay, an infinite polynomial, and it has to equal to 0. So we're going back to that identity property I mentioned before. The only way for this entire thing to be 0 for every x is if the a0 here is 0, the 2a1 is 0. Notice I'm taking this is the constant term, the only constant term on the left side. It has to be 0 if it's going to equal to 0 on the right side. The only x term on the left is 0. Well, on the right, this is the same as 0x. 0x squared. Okay, so the 3a2 has to be 0 because it has to match the x squared coefficient on the right side. So I know that a0 is 0. I know that 2a1 is 0. I know that 3a2 2 is 0. And I know that the coefficient of each of the x's has to be 0 because all the other x's that have powers 3 or bigger have coefficients of 0 also, since the right side is just 0. So that means then that the k plus 1 times the a sub k plus the b sub k minus 1, that's the coefficient of the x to the k term, and it has to be 0 for all the k's 3 or bigger. So let's say greater than or equal, let's say k equal. Okay, so I'm going by this to know what these values are. Okay, so that means then that this expression to be equal to 0 means that the a sub k, if I take this to the other side and divide by the k plus 1, and of course down here it doesn't matter what letter you use. It doesn't matter if I'm using a sub k or a sub n. So let's just switch all the k's here to n's. So that means that a sub n is minus b to the n minus 1 over n plus 1 for n greater than or equal to 3. And over here we had that a0 was 0, a1 had to be 0, and a2 has to be 0. And that proved exactly what they were asking us to show. Okay, and a little just terminology here, and then a refresher on some of the power series representations for some of the elementary functions. A function f is analytic at x naught if there's an open interval around x naught so that the sum of the power series has a positive radius of convergence. So you want to know that there's a power series that exists for an interval around that x naught. So analytic at x naught just means that the function can be expressed as a power series in this form that has a positive radius of convergence. Now, a polynomial will be analytic at every x naught because you can write every polynomial in this form. Okay, for some x naught, you can just do a shift to get it to look that way. A rational function, p of x over q of x, where p of x and q of x are both polynomials that don't have a common factor, will be analytic at all x values except for the ones that make the denominator 0. Okay, so rational functions will be analytic everywhere the denominator is not 0. Just be sure you reduce the fraction down. Elementary functions, e to the x, sine of x, cosine of x, those are all analytical at x values. Okay, and that's true for all x values. So for all x, so their radius of convergence would be infinity. So from minus infinity to infinity. And that's true for e to the x, sine of x, and cosine of x. Okay, the log function, ln of x, though, is only analytic for x values greater than 0. Okay, so, and the x has to be less than 2 for it to converge as well. Okay, so these are the intervals of convergence for these functions. If you need to have these function representations, now this one is being expanded about 1. You can't expand it about 0. E to the x, sine of x, cosine of x are all representations expanded around 0, which means we have just x minus 0 to the nth power in their representations, versus this one is the x minus 1 to the nth, since it doesn't even exist at 0. Okay, so these are your power series representations for these basic elementary functions that you're familiar with. Okay, we're almost ready to start finding power series solutions. Let's recall that a linear differential equation of order 2 has the form a2 of x, y double prime, plus a1 of x, y prime, plus a0 of x, y equals 0 for the homogeneous case. Now, when we put that in the standard form, we have y double prime plus a1 of x over a2 of x, y prime, plus a0 of x over a2 of x, y equal to 0. Now, this is the function that we've called p of x, and this is the function that we call q of x. Okay, so now a point x naught is an ordinary point if P, which is the A1 over A2, and the Q, which is A0 over A2, are both analytic at that value. So if we want to see if a point's ordinary, we need to check that power, the function in front of the y prime and the y in that standard form to see if we could write them as power series at that x value. Now, if it's not an ordinary point, then we call it a singular point. Okay, so let's find the singular points for this equation. First step then is to find the p of x and the q of x. So y double prime plus, when we divide by x, we're going to have 1 minus x to the negative 1, which is just 1 over 1 minus x. Okay, so our p of x, which was really x over x times 1 minus x, which would reduce down to this 1 over 1 minus x, and the q of x is the sine of x over x. Okay, so now the question is, can we write these as power series? Well, we know that the p of x, which is 1 over 1 minus x, that's just the geometric series. So we know that this can be represented as a power series for any x except when x is equal to 1. Remember, being analytic just meant it had to be representable as a power series in an interval around, one that had a positive radius of convergence. So this can be represented as a power series, except when x is equal to 1. Okay, so x equal 1 then would be a singular point. The second one, the q of x, sine of x over x. We want to see if that can be represented as a power series about some x value. Well, to do that, remember that sine of x does have a power series representation. This is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. So there is a power series representation for sine of x, and if we divide that by x, we would have 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial. So there is a power series representation for the q of x as well. Okay, so in this problem then, the only singular point then would be x equal 1. Right. Okay, so all the others are ordinary points, which means there will be a power series solution for this differential equation for any x value except for 1. Okay, so let's look at how we're going to find that. Now we want to find a power series solution about x equals 0. So that means that we want it to be of the form y equal the summation of a sub n x minus 0, so just x to the nth. Okay, so we're expanding about x equals 0. So the x naught is 0. Okay, so now to find that solution, we're going to substitute into the differential equation. So that means we need to also multiply, we need to find what y prime is. Well, y prime, which is the derivative of this, will be, I'm taking the derivative term by term, it'll be n times a to the n, a sub n, x to the n minus 1. I'm just taking the derivative of x to the nth using the power rule, n times x to the n minus 1. Now, recall that when we do that, we can't start with n equals 0 anymore, or we'd have an x to the negative 1 power. So we'll start just with n equal 1. Okay, and that's all we need for this differential equation. So substituting in, y prime will become this. So we'll have the summation n a sub n x to the n minus 1 for n equal 1 to infinity, plus 2x times the y, which is the summation a sub n x to the n minus 1, or x to the n, and we want that to equal to 0. Okay, before we try to combine the summations, we need to multiply the second one here by the 2x. So I'm going to have the summation and we'll have a summation here of 2a sub n x to the n plus 1, because we have an x to the 1 times an x to the n. Notice we have different indices also. One starts with n equal 1 and one starts with n equal 0. Now, look at the two summations and check their powers of x for their first index value. So when n is equal to 1, this becomes an x to the 0. When n equals 0 here, this becomes an x to the 1. So this first summation has an extra term. It has an x to the 0, then it'll have an x to the 1. So I'm going to break off the n equal 1 term. I have to have them matching the same power of x initially when you plug in the lowest value for the index. So when n equal 1, this is going to become a 1, a sub 1, x to the 0. And then I'm leaving the rest of the value, the terms in the summation, but now since we already used n equal 1, we're starting with n equal 2. The second one's already starting at x to the 1, so I don't need to touch it. I just need them to match. So take the one that has the lowest power of x and break off as many terms as needed to get them to match with the remaining summations. Okay, so now let's double check here. When n is equal to 2, this starts at x to the 1. When n equals 0, this starts at x to the 1. So now we're ready to change our indices so that they'll match what they start with, and both terms will be just an x to the k. So I have this a1, x to the 0, which is 1. This first summation, I'm going to let the k equal to n minus 1. And that means then that the n will be k plus 1. And when n starts at 2, that means that the k is going to start at 1. So this becomes k equal 1. N is k plus 1. And then x to the, we know is to the k, because n minus 1 is k. Okay, the second one, I'm going to do something similar. Over here, though, I'm going to let the n plus 1 be my k, because I want the exponent to be k. When n is equal to 0, that means k will start at 1, and this also means that n is just the k minus 1. So this summation will be starting at k equal 1, 2a sub n, which is k minus 1, x to the kth power. And now we're ready to combine our two summations. Notice they both now start with the same k equal 1. They both have the same power on the x. So this becomes a1 plus 1 summation, and I'll have a k plus 1 times a sub k plus 1 plus 2 times a sub k minus 1 times a sub k, a to the kth power. Okay, so now, the only way the left side can be 0, we want it to be 0, is if this constant term is 0 and every coefficient for each of the x's is 0. So I can say that a1 is equal to 0, and I can say that k plus 1 times a sub k plus 1 plus 2a sub k minus 1 must be 0 for all k's from 1 on. I go by this. This is the k values that has to be 0 for. Okay, so now we know that a1 is 0. And we have that I'm going to solve this second one. This is called a recursion formula. Or recurrence formula. Okay. I'm going to solve it for the largest indices a. So a sub k plus 1, k plus 1 is bigger than k minus 1. I'm going to take the 2a sub k minus 1 to the other side and then divide by the k plus 1. Okay, so there's our recursion formula. This is going to allow us to get what the series solution will be. Now let's go back to this form up here. This tells me that y in expanded form would be a0 x to the 0 plus a1x plus a2x squared. I'm just going to look at what the expanded form would be. This is the series form that we're trying to find. To find that, all we need is the a's. So we need to know a0, a1, a2, a3, a4, and then we have the series solution. Okay, so you don't always need to write these in that summation form. Expanded form will be good. So we already know that a1 is 0. So we don't know the a sub 0 yet. Okay, so we'll find those other terms. So now this is how we're going to get them. For the different values of k, I'm going to start with k equal 1. This says that a sub 2 is equal to minus 2 times a sub 0 over 1. I'm just filling in k equal 1 everywhere. That's just negative 2 times a sub 0. When k is equal to 2, a sub 3 will be minus 2 a sub 1 over 3. Well, we know a sub 1 was 0, so this is just equal to 0. When k is equal to 3, a sub 4, I'm just plugging into this, is equal to minus 2 a sub 2 over 4. So that's minus 2 over 4. Now notice this was minus 2 over 1. So I have minus 2 over the 4 times the a sub 2, which was minus 2 over 1, a sub 0. I'll worry about simplifying in a minute. K equal 4. If you want to do a bunch of them at once also, this will be a5, this will be a6. We'll have minus 2 times a to the third then. This will be minus 2 times a to the fourth, all over 5 over 6. This one's in terms of a3, which we know a3 was 0 up here. So this one's going to be 0. This one's going to be minus 2 over 6 times the a4 that we found up here, which was minus 2 over 4 times minus 2 over 1 times a0. Now notice I'm not simplifying because I'm trying to see the pattern here. Okay? So I can see then, just going to the next term, I know that next one's going to come out to be 0 as well. And just following the same pattern that I found, the next one's going to be a minus 2 over 8 times the minus 2 over 6 times the minus 2 over 4 times the minus 2 over 1. So I can build as many of them as I need to. Okay, so now let's go back to our power series that we're trying to find. I'm just going to fill in for all these a values. I have that y is equal to a0 I never found, but I found all these other ones in either as zeros or in terms of a0. We know a1 is 0. So we'll have a2, which is negative 2 a0 times the x. So this is my a, this is a2. a3 is 0. So now we're on a4. a4 is minus 2 squared over 4. Oops, I got this one wrong up here. When k was 1, this should have been a 2 on the bottom. So I'm glad I didn't. It was messing my pattern up. Okay. Okay, so then we have minus 2 squared over 4 times 2 times the a naught. Okay, I'm getting my powers of x. Look up here a little farther. Okay. So we have a0. This one's 0. This one's 0. So the a2 x squared plus the a4 is minus 2 squared over 4 times 2, a0, times x to the fourth. The x to the fifth term will be 0. We're going to have minus 2 to the third for the next one over 6 times 4 times 2, a0, x to the sixth. And you can find as many terms as you need to. You could find a general term, but it's going to be a little harder to get a nice expression for 2 times 4 times 6. Well, that's just, if I take a 2 out, it's just going to be the 3 factorial. So I could find a term. Let's see, I have a minus 3 to the n, and then I'm going to have a 2 times the n factorial. So that'll be 3 times 2 times 1 times that 2 on the bottom, and then we're going to have an x to the 2n. I don't know where that 3 came from. That's a minus 2 here. Okay, so that would be the form of our, this is our solution. Okay, so if we wanted to write it a little bit differently, notice I can take an a0 out of everything. I'm going to have a 1 minus x squared I think I'm going to be able to tell better if I actually do simplify these over here. When I reduce this down over here, this would end up being just 1/2. This one, I have 8 on the top and cancels out to be just 1/6, negative 1/6. This one, 16 on the top, will cancel. I end up with positive 1/24. If you notice, the bottom is just the 2 factorial or 3 factorial or 4 factorial. So let's see if we can get a general term here. We have a 1/2, so plus a 1/2. I factored out the a naught, x to the 4th. So that was looking at this term. Now I need the x to the 6th term. The x to the 6th will be this minus 1/6. Then we'll have a plus 1/24, x to the 8th. So if I wanted to try to write this as a summation, it would be the summation. I've got even powers of the x. I also have alternating signs, so let's make it minus 1 to the nth, and we're going to start here with n equals 0, and let's make it x to the 2n, and that will start me with x to the 0, then x to the 1, and so on. And then each term is going to have that factorial on the bottom, so let's make it n factorial on the bottom. So it starts with 0 factorial on the bottom, which matches the first one. 1 factorial on this bottom, 2 factorial will be on the bottom of this one, and it looks like that matches our solution. Okay. This actually ends up being, if we'd solved this equation using the methods that we'd done earlier in the book in chapter 2, solving the linear first order equations, this could be solved, and it's actually an e to the minus x squared solution. You could solve it using the separability to this problem, I believe. So this is the same thing as a0, and then it's e to the minus x squared, which is what you would have gotten had you solved it, by separability. This is separable. So you don't always have to put it in the summation form, because it's not always easy to recognize the pattern or even to know whether to look for one or not. But if you just find these coefficients and then just fill them in for the a's up in the equation, you'll get a power series representation. Okay, I want to find a general solution in the form of a power series about the point x equals 0. First, let's make sure 0 is an ordinary point. If you took this differential equation and rewrote it, y double prime plus x over 2 y prime plus 1 over 2 y equals 0 in that standard form, here's our p of x and here's our q of x. Well, p of x is 1/2 x. It's a polynomial, so it can be written as a power series, and likewise the q of x. So there are no singular points here, so all points are ordinary. So we will be able to find that power series expansion. Now, this is a second order differential equation, so we need to find 2 solutions to this differential equation, and we're going to find those in the form y equal the summation of a sub n x to the n equals 0 to infinity, since we're expanding it about 0, so the x naught would be 0. Well, from that, we know then that y prime will be the summation of a sub n times n x to the n minus 1, and we'll start that summation at 1, and then y double prime would be the summation of a sub n times n minus 1 x to the n minus 2. I'm just taking the derivative of those x to powers, and this one will start with n equal 2, so that we'll start with an x to the 0 term. Okay, so now substituting the differential equation, we're going to get 2 times the summation of the a sub n's times n minus 1 x to the n minus 2 and that one starts at n equal 2 plus x times the sum for n equal 1 a sub n x to the n minus 1, that's y prime, and then plus the y, which is the sum a sub n x to the n equals 0. Okay, now check the powers of x in each summation. This one would start with x to the 0, since you're plugging in n equal 2 first. The second one here would start with x to the 0. But we can't do that yet because we have another x out here. So before we try to worry about the powers of x on the summation, we need to get everything into the summation. So we have the first one, leave it alone. The second one, I'm multiplying this x to the 1 times the x to the n minus 1. That'll make it x to the n, starting at n equal 1. Okay, now check the powers of x. We need to make sure before we combine into one summation that they're all the same power, and we have to make the indexes match. So this one, when n starts at 2, this starts at an x to the 0. When n starts at 1, this starts as an x to the 1 term, and when n 0, this starts as an x to the 0. So that means the first and last summations will have an x to the 0 term before they get to the x to the 1. So we're going to break those first terms off. I'm going to let n equal 2 in this first summation, that's the first n value, and I'm going to get 2 times a sub 2 times 3 I just changed this to a plus. I just realized that. I don't want to do that. So this is times 1. And then x to the 0. And then I'm going to put the rest of it. So that was n equal 2. And now for n equal 3, this is going to be 2 times a n minus 1, x to the n minus 2. The second sum is already starting at x to the 1, so we leave it alone. And now the next one, I have an x to the 0 term, so I'm going to break that out. N equals 0 is the first index you plug in. And so that's going to be a to the 0, x to the 0, and then I'm just putting the rest of the terms starting at n equal 1. Okay. So now I'm going to take these two terms that are the x to the 0 and pull them in front. So I have a 4a2 plus an a0 that are the x to the 0 term. And now I'm going to focus on these other summations. Now notice the summations. They should all agree with the same starting power of x. So when n is 3 here, we start with x to the 1. When n is 1 in the second one, it's x to the 1. And when n is 1 in the last one, it starts with x to the 1. So now let's make them have common variable names. I'm going to let k be the n minus 2 here. And so that means that the k value, if n starts at 3, will start at 1. And that tells me also that n is just the same thing as k plus 2. So now switching all the n's to k plus 2, the index becomes k equal 1, 2a sub k plus 2, k plus 2, k plus 1, x to the k. Second summation, I'm simply going to let k be n, so that means k will start with 1, and n will be k. So we'll have ak times k, x to the k, starting k equal 1. Same thing with the last one, just let k be n. So now we've got them all with matching k values, all start with k equal 1, and they all have x to the k. So now let's combine all those into one summation. So now these last two, when I combine them, they both have the AK. So I'm going to take the AK, it's AK times K plus AK. I'm going to take the AK out. So we'll have K plus 1 times AK, and then all of that, x to the K. And the K does start at 1 here. Okay, now, for the right side, since it has to be 0, that's 0 plus 0x plus 0x squared and so on, each term, each coefficient of the x powers has to be 0. So the constant term here, 4a2 plus a0 must be 0. That's the only constant term on the left side. Then I know that every coefficient of the x to the k, from k equal 1 on, has to also be 0. So this is going to tell me that 2a k plus 2 times k plus 2 k plus 1 plus k plus 1 times a sub k has to be 0, and that's true for k greater than or equal to 1. Just going by this index here. Okay, find the recursion formula or recurrence formula. I'm going to solve for the largest subscripted a, which is a k plus 2, and that's going to be a minus ak times the k plus 1 over 2 times the k plus 2 times the k plus 1. Now we can cancel the k plus 1s, okay, because k is going to start at 1, so that's not going to be 0. And so we have that ak plus 2 is negative ak over 2 times k plus 2. We also have that a2 would be negative 1/4 a sub 0 if we solve that equation. Okay, so this one will give me the values of the a's for k greater than or equal to 1, and I already know a0 you leave just as a0. A1 will just be a constant you leave as a0, a1. A2 we know this recursion formula will help us to find all the a3s and greater. So here's where you need to make sure you have plenty of room, because it gets really messy, messier than what we've already been doing. So I'm going to look at the k values. I'm going to look at k equal to 1, k equal to 2, k equal to 3, and we're going to go until we find a pattern. If k is equal to 1, now this is the formula I'm using. A sub k plus 2 is minus ak over 2 times k plus 2. So when k is 1, this is going to tell me a3. This will tell me a4, a5, a6. When k is 1, the right side over here becomes minus a1 over 2 times 3. A4, I'm plugging in k equal 2. This will be minus a2 over 2 times 4. K equal 3. This is minus a3 over 2 times 5. K equal 4. Minus a4 over 2 times 6. Okay. We're going to leave a1 and a0 as they are. Okay. We know that a2 is negative 1/4 a0. So I'm going to go to where I have an a2 here. This is minus 1 over 2 times 4 times the a2, which is negative 1 over 4 a0. So that's my a4 in terms of a0. Now I'm going down here, which also has an a4. That's minus 1 over 2 times 6. And then I'm going to replace the a4, which was this term. So I'm going to have minus 1 over 2 times 4 times minus 1 over 4 times a0. Now if I wanted to jump down and look at a8 and just see if I could guess the pattern, I see a negative 1 times negative 1 times negative 1 times another negative 1 will come into it. And I'm going to have 2 times 8, 2 times 6, 2 times 4, and I could write that 4 as a 2 times 2 as well. And this would be in terms of A0 also. Okay, so if I wanted to try to write this as a general term, now notice the ones that have A0 are all going to be just even subscripted. A2, A4, A6, A8. Okay, so let's look at those separately. A0 we know that A2 is negative 1 over 4 A0. We have that A4 is positive 1 over 2 times 4 times 4 A0. A6 will be negative again. We have a 2, 2, 2. We have 3 2's and then a 6, 4, 2. So 2 times 6, 2 times 4 times the 4, A0. And then our A8 will be positive over, now here I'm going to try to use this to get the pattern. I see 1, 2, 3, 4 2's. If I take a 2 out of this, this, and this, that's 8 2's. And then all I have left is a 4, a 3, a 2, and a 1. Okay, let's see if we can get that similar pattern. The A8 has 2 to the 8, so can I get 6 2's out of this? 1, 2, 3, 4, 5, 6. So this is negative 1 over 2 to the 6th, and then I would have 3 times 2 times 1. So the same pattern here. This one's now positive. I want 2 to the 4th, and then I'd have a 2, which is a 2 factorial. The A2, I would want to have 1 over 2 to the 2, and then just 1 factorial. So I see a nice pattern there. To write it, you don't have to find the patterns all the time. It really kind of gets you bogged down into it. But if you wanted to find a pattern for these, you see the pattern and you could write it as a summation. I'm going to go ahead and write it down. What they're going to do because you have this number that's always half of the previous exponent, they're going to write this as a to the 2n so that they can see that half that number, and then it's negative 1 to the nth over 2 to the 2n, and then it's n factorial. That way I can specify that factorial by having half of the number that was the subscript. Okay, so that's the form of what the even ones will look like for n greater than or equal to 1. The odd ones, let's look at those. The A3 is minus 1 over 2 times 3 times A1. We're just assume A1 is itself. This one would be minus 1 over 2 times 5, but times the A3, which would be another minus 1 over 2 times 3 with an A1. Okay, so let's see if we can predict what A7 would look like without plugging it in. You can check it by plugging it in. We're going to have this minus 1 over 2 times 5, minus 1 over 2 times 3, and then we'll have a minus 1 over 2 times 7, which would have actually come first. I was looking at the previous ones first. You get to 2 times 7 when you plug in the k equal 5, but then I'm taking the previous ones because we're substituting in the A5. Okay, so you can see the pattern here. Because these are all going to be odd subscripts, we could write it as 2n plus 1. Okay, and I see I have 1, 2, 3 2's here, and it's odd, so 1 over 2 to the 3rd, and then I have 7 times 5 times 3. This one will be a positive 1, 2 to the 2nd times 5 times 3. Okay, so you've got that similar pattern. So if I were writing a general term, then I'm going to have a minus 1 to the nth over 2 to the nth. Notice the n is always, if you take 1 away and take half, that's the number here. So 7 here, that gives you a 3, and this is very confusing, I understand. And then you're going to start with whatever this 2n plus 1 is. This number is the first one that you actually start with, and you multiply all the way down until you get to 1. Okay, so that would be the coefficient with the A1 for the odd terms for any n greater than or equal to 1. Okay, now don't worry about getting the summation forms for these because they're not going to be pretty. Go ahead and just calculate those out if they want some of the terms. So we know our solution is y equal a0 plus a1 x plus a2x squared. This is the form of the power series expanded around x equals 0, 3, x to the third. Just write out a few of them. I'm not sure how many they want. Let's see, that'll give me 3 of each of the 2 series. We leave a0 the way it is. I'm leaving a1 the way it is. a2 we got to be minus 1/4 a0. a3 was minus 1/6 a1. a4 over here, if you want to actually multiply that out, it's 1/32, whatever a0 is, x to the 4th. a5 right here will be 1/60, whatever the a1 is, times x to the 5th. So you can actually calculate those out, but notice that every other one has a0 and every other one has a1. So if you take the odd ones and take out the a0, you're going to have a 1 minus 1/4 x squared plus 1/32 times x to the 4th, and then take a1 out of the others. So you're going to have x minus 1/6 a1. I've already took the a1 out. Okay, so I'm taking this this one, a1x. Take a1 out of this, minus 1/6 x cubed. Take a1 out of this one, plus 1/60 x to the 5th. Okay, and so you've got our 2 solutions here. Here's our y1, and here's our y2, just expanded out as power series. And so any linear combination of those 2 will give you a solution to the differential equation. And so here's our constants times the first solution plus the constant times the second solution. Okay, let's look at another example of a power series expansion about x equals 0 for this differential equation. So we've got a second derivative, so we're going to need since we're expanding it about x equals 0, it'll be of the form a sub n x to the n. The derivative then will be the sum of n times a sub n x to the n minus 1, starting at 1. And then the second derivative would be the sum of n times n minus 1 a sub n x to the n minus 2, starting at n equal 2. Okay, substituting that into the differential equation, and we get 1 plus x squared times the y double prime minus y prime plus the y equal to 0. Okay, I need to distribute this through, so I'm going to do 1 times that summation. And then I'm going to do x squared times that summation. So this will make it x to the nth. Okay, so I did the x squared times this and got this over here. And then the second one again from the first line. and then the last one. Okay, I need to combine these summations. So first, though, I need to check the powers of x. In the first one, we start with an x to the 0 because we're plugging in the n equal 2 into x to the n minus 2. The second one will start with an x squared. The third one will start with x to the 0. And the fourth one will start with x to the 0. Okay, so the one that starts with the latest x to the power is x to the second, which is this one. So what I need to do then is I need to pull the x to the 0 and the x to the 1 term from the others by using the first two values of n for each summation. So when n is equal to 2 here, I'm going to have 2 times 1 a sub 2 x to the 0. Okay, so this is n equal 2. Then I'm going to have n equal 3 for this same summation. So I'll have 3 times 2 a sub 3 x to the 1. The second summation, okay, then whatever's left. So that was n equal 2, n equal 3. Now I'm going to be starting with n equal 4 and have the remaining of that summation. Okay, so this entire thing here was this. All I did was I took the first two, n equal 2, n equal 3, and then left n equal 4 the rest. Okay, the second summation is already at n equal x to the second, so I'm just going to leave it alone. It doesn't have the extra terms. Now the next summation here, I need to pull off 2 terms since that had an x to the 0 right now, so I'm letting n equal 1 first. So I'll have 1 a sub 1 x to the 0, then n equal 2. Now notice I have this minus in front, so I do need to have a minus right here. Then minus the n equal 2 will give me 2 a sub 2 x to the 1, and then minus the rest. And so this will be starting at n equal 3. Okay, the next one, again, we have 2 extra terms. So when n is equal to 0, we would have a sub 0 x to the 0. When n is 1, it'll be a1 x to the 1, and then the rest. We'll start with n equal 2. Okay, so now let me pull all the terms that have the x to the 0 out in front. So I have a 2a sub 2 here. Minus an a sub 1 plus an a sub 0. Now I'm going to look at the terms that have an x to the 1. I have a 6a sub 3 minus a 2a sub 2 and then plus an a sub 1. And now let's look at the summations. Now each of these summations should be starting at x squared now. So you'll notice that when n is equal to 4 on this one, this will be an x squared term. So I'm going to let k equal to the n minus 2, meaning that n will be k plus 2 when I make my substitution. And when n was 4, the k will be 2. So this will become a summation k equal to 2. N is k plus 2. K plus 2 minus 1 will be k plus 1. A sub n, which is a sub k plus 2. And then we'll have x to the k. Okay, this summation. We're starting at n equal 2, and we have x to the n. We're just going to let the k be the n. Just changing the variable name. Okay, the one over here. Again, if n's 3, it starts the next to the second. So we're going to let the k be n minus 1, so that the exponent here will be a k. That means that n will be just k plus 1, and when n is 3, the k will be 2. n is k plus 1. Then we have a sub k plus 1. Then we have x to the kth. Okay, and the last one over here, we already have the kth power, so we're just going to have the k equal to n. So I'm just going to rewrite it again, changing the variable to k. Okay, so now I want to make all these summations into one big summation. They all have matching indices now, same starting value and power of x. I'm not going to put this x to the 0. That's obviously just 1. So I have my constant term. Now one summation, k equal 2. Okay, so I have an ak plus 2 in the first term. I'm going to go ahead and grab the third, so I've got this one. I'm going to go ahead and grab this one next, because it has that ak plus 1. And now the last, the second one here and here both have the a sub k. So I would have this k times k minus 1 a sub k plus a 1 a sub k. So that's going to give me k squared minus k plus 1 a sub k. So all I'm doing is I'm combining those two, the second and the fourth summations, and taking out the a sub k. And then all of this to the x sub k. Okay, now we're ready to set terms equal. Using the identity property, the constant term on the left has to be the same as the constant term on the right. Then the x term on the left has to be the same as the x term on the right. And I'll just say x sub k. Okay, so I know then that 2a sub 2 minus a sub 1 plus a0 has to be 0. I know that 6a sub 3, this is the coefficient for the x term, minus 2a sub 2 plus a1 has to be 0. And I know then that this huge recursion formula, k plus 2, k plus 1, a sub k plus 2, plus k plus 1, a sub k plus 1, plus k squared minus k plus 1, a sub k, all has to be 0. So again, doing what we've done in the past, we want to solve for the largest indexed a. So that tells me that a sub k plus 2 is equal to negative k plus 1 a sub k plus 1 minus k squared minus k plus 1 a sub k, and all of that over k plus 2 times k plus 1. And I know from these first two equations, I know that a sub 2 will be 1/2 a sub 1 minus a sub 0. And I know that a sub 6, or a sub 3, looking at this one, will be equal to 1/6 2a sub 2 minus a sub 1. Now that we already know a sub 2, we have it right here, we can substitute it into this and get 1/6 twice a sub 2 will be a1 minus a0, and then minus the a1. And so that means that a3 comes out to be negative a sub 0 over 6. Okay, so now let's look at some of the values. From our summation up here, the recurrence formula starts with k equal 2. Okay, So let's plug in k equal 2, k equal 3, k equal 4, and let's see what comes up. So k equal to 2. We're going to have a sub 4, I'm just using this formula right here, equal negative, well, let me go ahead and just plug in these two, a sub 5 and a sub 6. I'm just doing them all at once. Okay, so now plugging in 2 into this next term, I'm going to have minus 3 a sub 3. So this one will be a minus 4 a sub 4. And this one will be minus 5 a sub 5. Then I'm going to have minus, okay, 2 squared. So 4 minus 2 is 2 plus 1 is 3 a sub 2. This one will become 9 minus 3, so 6 plus 1 is 7 a sub 3. And this one will become minus 16 minus 4, 12, 13 a sub 4. And then we'll have 4 times 3, 5 times 4, and 6 times 5. Okay, so we know what a sub 3 is. A sub 3 is negative a0, and a sub 2 we have over here as well. So this would end up being minus 3 times negative a0 over 6 minus 3 times 1/2 a1 minus 1/2 a0. So I've got 3/6 a0, so 1/2 a0 minus 3/2 a1 plus 3/2 a0. So that comes in all over 12. So that comes out to be 2a0. This will make it, with a common denominator, that'll make it 4 minus 4a0 minus 3a1 all over 24. Okay, I just noticed up here I missed a sign. I had a minus here, which when I changed the into k plus 1, I lost it here. So this should have been a minus sign, which would have put a minus here, which would have made this a minus, which would have made this a plus. So this should have been a plus here. So let me do that before I get too far gone. Okay. And so that's going to make all of these positive here at the front. Okay, so now back to where we were. We've got 3a sub 3, which is negative a0 over 6, minus 3a sub 2, which will be 1/2 a1 minus 1/2 a0, all that over 12. So we have minus 1/2 a0, minus 3/2 a1, and then plus 3/2 a0 over 12. So we'll have just a0, so that'll be 2a0 minus 3a1 all over 24. Okay, just following that along that same idea. This term, the a5, when we substitute in the a4 we just found in the a3, this comes out to be 3a0 minus a1 over 40. Same thing for a6. Once I plug in the values that I found above, I get 36a1 minus 17a0 over 720. Okay, so now, how are we going to get the solutions out of this? Remember, we're looking for two solutions. Now, the two solutions can come from choosing values for these a1 and a2, a0s. We have values. Okay, so now this will be the easy part. if we have the a's in terms of two different a's, we didn't have that in the previous problems. We're going to do this. We're going to split it into two cases now. We're just trying to find solutions. We know that any multiple of some of these will be solutions as well, but we're going to make it easy on ourselves by saying, okay, we have A0 and A1 that everything else is going to be in terms of. So I'm going to say, okay, case 1, I'm going to use A0 just as it is, and then I'm going to let the A1 be 0. So now I have A0, I have A1 is 0, go back to A2 up here. A2 then, if A1 is 0, is going to be just minus 1/2 A0. The A3 is right here. Letting A1 be 0 doesn't matter. It's just going to, the A3 will be minus A0 over 6. The A4, which is right here, if we let A1 be 0, we get A4 is 1/12 A0. The A5, right here, we're going to let A1 be 0. We get 3/40 A0. And the A6, if we let A1 be 0 here, we're going to have minus 17 over 720 A0. Okay, so now this has given us one of our solutions. We know that y, which is of the form A0 plus A1x plus A2x squared, and so on, will be, we keep the A1 the way it is. A1 is 0. A2 is minus 1/2 A0. A3 A4, A5, and A6. Of course, you could keep going. So then our first solution, y1, will be A0 times 1 minus 1/2 x squared minus 1/6 x cubed plus 1/12 x to the 4th plus 3/40 x to the 5th minus 17 over 7/20 x to the 6th, and so on. So actually that's a multiple of the solution. That's just a solution. So if we were listing A1 and A2, I would give this as Y1 and Y2. Here's what I would give for my Y1. And then any multiple is the A0 to give us, an infinite number of solutions. Okay, now let's go up to the other case. Our case 2 here is going to be letting the A0 be 0. And then A1 will just be whatever value it is. So we have, go back up to the A2 over here. Our A2 then, if A1 is 0, will just be 1/2 A1. Our A3 is going to be 0. Our A4 over here, let A0 be 0, will be minus 3/24, so minus 1/8 A1. Our A5, right here, let A0 be 0, and we're going to have minus A1 over 40. And here, let A0 be 0. A6 will be 36 over 720, so that's going to be 1 over 20th A1. Okay, so now let's form that solution. We know this is the form of it. And we're just listing some of the terms. We're going to have A0 is 0. The A1. A2 is now in terms of A1. A3 is 0. Yeah. A4. Here's our x to the 6th. And then you could keep going. So our solution then would be A1 times x plus 1/2 x squared minus 1/8 x to the 4th minus 1/40th x to the 5th. It's 1/20th x to the 6th, then you could go on all day. So our y2 then would be this function. Okay, so if you end up with an a sub k where when you solve for that in that recurrence relation, let one of the two a's, if you have two different ones, you know, in terms of a2 and a1, just let one of them be 0 and look at two different cases that way. And that way they'll split them up, you know, a little bit more easily. Get your two solutions. Okay, now let's look at the existence theorem for an equation of the form y double prime plus p of x y prime plus q of x y equal to 0. So it's our second order linear differential equation, and we already have it in the standard form. Okay, so we knew that there's going to be a solution as long as the p of x and the q of x are both analytic. In other words, there's power series representations. We know that we're going to be able to find a solution. So if x naught is an ordinary point for that equation, then we know that it'll have two linearly independent analytical solutions that are of this form. Okay, so that's our guaranteed, our existence theorem. Moreover, the radius of convergence of any power series solution of that form will be at least as large as the distance from x naught to the nearest singular point. And we can have singular points that are both real and complex valued. So if we want to find the radius of convergence, then we're going to find the value x naught that it's being, you know, generated by around, and then we're going to look for the singular points, and the distance to the nearest one will be the radius of convergence. Okay, so let's find the minimum value for the radius of convergence of a power series solution about x equals 0. So we're expanding about x equals 0. So we're looking at the solution of the form y equal a sub n, just x to the n. Okay, so we want to find first singular points. Well, we have y double prime plus x over 2 y prime plus 1/2 y equal to 0. Now, since the p of x and the q of x are both analytic, they're both just polynomials, then we know that there are no singular points. Okay, so the radius of convergence then is the distance to the closest singular point, but since there isn't one, that radius of convergence would just be infinity. So rho is equal to infinity for our radius of convergence. Okay, now let's look at the minimum value for the radius of convergence of a series solution about x equals 0 again. So again, of this form, x minus 0 to the nth power, to this differential equation. So let's look for singular points. If you rewrite this in standard form, we have y double prime minus 1 over 1 plus x squared y prime plus 1 over 1 plus x squared y equal to 0. Well, we've got rational functions here for the p of x and the q of x. The only singular points will be values that make the denominator 0. So 1 plus x squared will only be 0 when x is either I or negative I. X squared is negative 1, and so that means the square root of negative 1 is I, and plus or minus the square root of I. So those are our singular points. So we do have complex singular points here. Now we need to find the distance from these complex numbers to x equals 0. Now the way you calculate distances between complex numbers and real numbers is you use the plane. This is called the complex plane. And you graph the real numbers on one axis and the imaginary parts on the other axis. So a number like 0 is 0 plus 0i. So 0 is like our independent variable would be 0 over, and then 0 up or down. So here's 0 in the complex plane. So real numbers are actually on that horizontal axis. Okay, so now I is 0 plus 1i. Okay, 0 plus 1i means we'll go over 0 and then go up 1. So it'll be one value up. So this is 0 plus 1i. Now the distance between them is the same as you would find the distance between 2 points. So if you look at this as a point 0, 1, and this is the point 0, 0, The distance, using the distance formula, would be the square root of 0 minus 0 squared plus 1 minus 0 squared. Now, I know you didn't have to do that since they're both on the same vertical axis, but if one of them were out in the plane somewhere like 2, 3, you just use the distance formula between the 2 points. Okay, so the distance to I is 1, and the distance to negative I, which would be 0, negative 1, so 0 minus 1I would be plotted as the point 0 minus 1. And so the distance there is also 1. So our minimum radius value for the radius of convergence here is rho equal to 1. Okay, now we want to look at a power series expansion about another value than just x equal to 0. So what we want to do is we want to convert this equation over to an equation that would be equivalent, that would have the value that we're expanding about at 0, and then we'll just make a quick, easy substitution at the end. So it's much easier to work with, a value. So what they're asking here is to find an expansion about x equal 1. That means the expansion is going to look like this. It's going to be of the form x minus 1 to the nth power n equals 0 to infinity. Okay? Instead of working with something with that x minus 1 to the nth power, we're going to make a substitution. I'm going to let t equal to the x minus 1. So since we know x is equal to 1, that means x minus 1 is 0. So if I let t equal to x minus 1, then that would be an equivalent value is t equal to 0. So this means that when x is equal to 1, t would be equal to 0. Okay? So now, the substitution that I'm going to make is I'm going to define a new function. The new function will be a y of t, okay, which will be the same thing as our y of x, which will be the same thing as y of t plus 1, since we know that x is equal to t plus 1. Okay, so now to make this substitution, we're going to change the equation over to this new function, the y of t. So it's going to be a function of t instead of a function of x. So right now we have y prime, which is a derivative of y with respect to x, and we have y double prime, which is the second derivative of y with respect to x. So we need to convert these over to derivatives with respect to t. Okay, so using our equation here, we know y of t is equal to y of x, and we know then that the derivative of y with respect to t is going to be the derivative of little y with respect to x. Okay, the second derivative of y with respect to t then will also be just the second derivative of y with respect to x. So that's going to allow me just to change this y double prime then, which is the second derivative with respect to x, over to the second derivative with respect to t. So we're going to have the derivative of y with respect to t. So we'll have plus x, which we're converting everything to t, so x is the same thing as t plus 1. And then the derivative of y with respect to t. That's just the derivative of y with respect to x here, which is equivalent. And then plus just y itself, which little y as a function of x is just capital Y is a function of t. So we'll just use the y. Okay, now one thing I want to point out before we get too much further here is the radius of convergence. Now notice here that there are no singular points. Okay, so that means x equal 1 that we're trying to expand it around is an ordinary point. Okay, and our previous theorem said that the radius of convergence will be the distance from this ordinary point to the closest singular point. So since there are no singular points, the radius of convergence then will be infinite. So the radius would be just infinity. Okay, so the interval would be from minus infinity to infinity. Okay, so now let's go back to our solving for this power series expansion. Okay, so I want to take this equation then, and I want to find y, which will be an expansion around just t equals 0. Okay, so this will be y as a function of t. Okay, so if that's y, then we know that y prime will be equal to n times a sub n t to the n minus 1, and that'll start at n equal 1. And then our second derivative will be n equal 2 to infinity, n times n minus 1, a sub n t to the n minus 2. So now substituting those into this equation, we're going to get twice the summation n equal 2 to infinity plus t plus 1 times the first derivative, which is n a n t to the n minus 1, which is this right here, and plus our y. And that equals 0. Okay, so we need to combine these summations. So first check the powers of the t on each summation. This first one, when you start with n equal 2, in here, this is going to be a t to the 0 for the first term. This one is going to have a t. We need to expand this out. So before I can combine things, I need to distribute this through this summation. So let's do that first. So we'll have t times that summation. So that'll be t to the n. Just add 1 to the exponent. And then we'll have 1 times this whole thing. So that'll be plus n a sub n t to the n minus 1, still starting at n equal 1. And then we've got our last one here. Okay, so now we've got them as 4 separate summations. Check the powers of the t on each one. Since this one starts at n equal 2, this will be a t to the 0. This next one starts at n equal 1, so this is going to be a t to the 1. This one's n equal 1, so this will be a t to the 0. And this one will start at 0, so that'll be a t to the 0. So we have 3 of them that are t to the 0. This is a t to the 1, so that means the ones with the t to the 0 have an extra term. So I'm going to pull one term out of each of the ones that have the t to the 0. So all 3 of these, we're going to break them up, letting their first n value be that t to the 0 term, plus then leave a summation for all the rest. So this is going to be 2 times, so this is when n equal 2. We're going to get 2 times 2 times 1, a sub 2, t to the 0. And now I'm going to leave the other summation. I'm going to go ahead and pull that 2 on the inside. 2n, n minus 1, a sub n, t to the n minus 2, and now the n will start at 3. So all I did was I pulled the n equal 2 out, n equal 3 and on will be still in the summation. Okay, the next one is already a t to the 1, so I'm going to leave that one alone. The next one is a t to the 0 term, so I'm going to break off the first n term. So I'm going to have n equal 1, and then we'll have n equal 2 on for the summation that remains. So n equal 1 into this will leave us with 1, a sub 1, t to the 0, and then the summation that will be the rest of the terms will be n, a sub n, t to the n minus 1, starting at n equal 2. Same thing in the last one. I'm going to break off the n equal to 0 as a separate term. Then the rest will be n equal 1 on. So I'm just breaking this summation into 2 sums. So this will be a sub 0, t to the 0, plus the sum of a sub n, t n. And now this will start at n equal 1. Okay, so collect all my t to the 0 terms. We're going to have 4a2 plus a1 plus a0, and all that's the t to the 0 term. All the other summations now will start with a t to the 1 power. So we're going to change them now so that the indices match. So I'm going to let, in this first one, I'm going to let k equal to n minus 2. So that means the n will be k plus 2. So when we start the summation at n equal 3, that means that k is going to start at 1. And I'm going to replace all the n's now with k plus 2. And then now it's going to be t to the k power. Okay, now in the second one here, I'm going to let k equal to n. So that means if n starts at 1, k starts at 1. So we're just letting the n be the k's in all those terms. And in this next one, we're going to let k equal to n minus 1, which means n will be k plus 1. And again, since n starts at 2, k will start at 1. N will be k plus 1 everywhere. And now in the last one, I'm just going to let the k equal to n. Again, all of them will be t to the k now. And so k is n, so that means k starts at 1. We'll have a to k, t to the k equal to 0. So now all of our summations have a t to the k as the first term with a t to the 1 being that first one. So I can write that as one giant summation. So I'm going to have my 4a2 plus a1 plus a0. Now notice that's a constant. It's a t to the 0, which is a constant term. And then I have a summation. I'm just combining all these other terms. I'm going to start at k equal to 1. Okay, now I can clean that up. I've got some things there with both two of them with an AK, and then I've got an AK plus 1. So I'm going to kind of separate those out a little bit. So I've got 2, k plus 2, k plus 1. That's the AK plus 2. I've got a k plus 1. If I factor out an AK out of the first and last terms here, I've got a k plus 1 AK, and then I've got a k plus 1 AK plus 1. Notice each of those coefficients now have a k plus 1 factor, which is going to make it simplify nicely. Okay, so now, for the left side to be 0, right, we have 0 on the right side. That means each coefficient of every power of t has to be 0. So that means this first expression must be 0, and this must be 0 for every k from k equal 1 to infinity. So I'm going to set them equal to 0. So we'll have 4a2 plus a1 plus a0 equal to 0. What that means then is that a2 can be written in terms of a1 and a0. So it'll be 1/4 a1, negative 1/4 a1, minus 1/4 a0. So we're going to end up with two variables, a0 and a1, which we had a second order equation, so we're going to expect to have two separate solutions to this. So one will have everything with a0s, one will be everything with the a1s. And then the next one will be, now when you take this and set it equal to 0, I'm going to solve for the biggest indexed term. So that means ak plus 1 is going to be minus, now notice the the k plus 1s are canceled because I'm going to take this and set it to 0. Solve for ak plus 2. So that means this and this term will go to the right side, and I'm going to have minus ak plus 1, all of this over 2 times k plus 2. Because the k plus 1s will cancel for all those. Okay, so that gives me an expression then, and that's true for every k from 1 on. So let's start with various k's here. Well, this should have been ak plus 2, not k plus 1. Because we already have a 2 over here, so we shouldn't get a2 again. Well, now, when we plug in k equal to 1, we're going to have that we have a3 is equal to minus a1 minus a2 all over 2 times 3, all over 6. Okay, but we know a2 is this. Okay, so that's going to give me a minus 1 over 20, or positive 1 over 24, a0. And then I've got a minus 1/6 a1, and I've got a, so minus 1/6 plus a 1 over 24. So this is going to be minus 4 over 24 plus 1. So that's going to be minus 3 over 24, which is negative 1/8. A1. Okay, so that should be enough to get our solution here. So now we're trying to find, remember, our y of t. Let's expand it out. A0 plus A1t plus A2t squared okay, so that's the form of our y, since we're expanding around t equal to 0. And so now we know that that's going to equal to A0 is an unknown, A1, A2 we know is minus 1/4 A0 minus 1/4 A1. And over here. The A3 we got to be this. We could get more terms if we wanted to. Now I'm going to rewrite this. Y of t is going to be A0 minus, I'm looking for all the terms that have A0. So here, this, this, and then I'm going to take all the terms that have A1, okay, and now I'm just going to factor out those common terms. So this is y of t. I'm going to take A1 out. So that's given me my two solutions for a function that had y as a function of t. But now, recall that we let our t was x minus 1. Okay? So if I just replace the t with x minus 1, I get y of x minus 1, which is this little y of x. Okay, recall that we had that we said earlier that y of t was little y of t plus 1. Okay, so I'm just replacing the t with x minus 1. So that means y of x minus 1, the big Y of x minus 1 will just be the little y of x. And so all I'm doing is I'm going to replace all the t's with x minus 1. Okay, and so that's why most of these problems we don't work with the x values, expanding around x values other than 0, because it's really just a matter of doing the problem with a 0 and doing a shift afterwards. So it's just as easy to transform it over to an equation that would be centered at 0 and then shifting it back at the end. So we can always just work with the ones with the 0 with the correct shift at the end. So here's our solution for y of x to the original equation. Okay, we've already seen that if we have an ordinary point, that a differential equation will have power series solutions. What we want to look at next is, what if we have singular points? Are there any cases where singular points might lead us to a series solution? So the first thing we need to do is look at a classification of singular points. We'll have a singular point is called a regular singular point if once we have the differential equation in standard form, if x minus the x naught times the p and x minus x naught squared times the q are both analytic. In other words, can both be expressed as power series about that singular point. If that's not the case, if one of them is not analytic, then we would say that the singular point's irregular. So let's classify the singular points of this equation. First, let's find the singular points. Okay, so if we're finding the singular points here, we're first going to write it in standard form. Okay, so here's my p of x and my q of x. Okay. Singular points are going to be points where these expressions cannot be expanded into power series. And so even though we have an x plus 1 in the numerator of the y prime, we'll still have an x plus 1 factor in the denominator after we factor the denominator and reduce it. So let me write this one more time. This is y double prime plus x plus 1. Factoring the x squared minus 1 to x plus 1 x minus 1, you have okay, so we see even here when an x plus 1 cancels, you'll still have an x plus 1 factor in the denominator. So we would have singular points of x equal negative 1 and x equal positive 1. Okay, so now let's classify each one of those. To determine if x equal 1 is a regular singular point, we multiply by x minus 1. We'll look at x minus 1 p of x. And then we'll look at x minus 1 squared q of x. That's all this is saying. We're using the singular point x equal 1. Well, x minus 1 times p of x results in 1 over x plus 1 times x minus 1. X minus 1 squared q of x results in 1 over x plus 1 squared. Okay, so now this singular point, x equal 1, gives us this x minus 1 p of x. It's not analytic because it's still got the x plus 1, x minus 1. Specifically, it still has the x minus 1 factor in the denominator. Versus this one, since the x minus 1 is no longer the denominator, this would be analytic at 1. Okay, so if either of those is not analytic at x equal 1, then we call this a irregular singular point. Okay, now let's look at x equal 1. Okay, now we're going to look at the expression x plus 1 times the p of x, and then the x plus 1 squared times the q of x. X plus 1 p of x will be x plus 1 times x plus 1 over x plus 1 squared, x minus 1 squared. And we get 1 over x minus 1 squared, which is analytic at negative 1. It would not be analytic at positive 1. But we wouldn't be looking at that term if that's what's the case. This one, x plus 1 squared times the q of x, comes out to be 1 over the x minus 1 squared as well, which again is analytic at negative 1. The only place it's not analytic is at 1. So that means that x equal negative 1 would be a regular singular point. Okay, now we want to look at what's called an indicial equation. That's going to give us the values where we're going to be able to get power series, not power series, actually series solutions. Okay, so this comes from considering the Cauchy-Euler equation. Now I'm going to look at the Cauchy-Euler equation in the form of y double prime, x squared y double prime, plus x, y prime, plus y equal to 0. Oh, let's go ahead and use the p and q that they have here. Okay, now recall that a Cauchy-Euler equation had the solution of the form y equal x to the m. I'm going to use y equal x to the r. And I'm going to call these p naught and q naught here. So it's pretty much just, I just don't have a leading coefficient of the equation. I just have that x squared. Okay, so now if x to the r is a solution, then I can plug it into this differential equation and it'll satisfy it. So that means that y prime is r x to the r minus 1, y double prime r minus 1, x to the r minus 2. And now substituting these into the equation, I get x squared times r minus 1, x to the r minus 2, plus q naught times x, r x to the r minus 1, plus p naught, not q naught, plus q naught times x to the r. And just like when we dealt with Cauchy-Euler, pairing the x values up, we end up with each of these terms having an x to the r factor. So I'm just going to take the x to the r out of each one. Since we want the differential equation to equal to 0, the coefficient of every power of x must be 0. So the only way that's going to happen here is if this expression is equal to 0. This is called the indicial equation, okay, for the series written in this form. Now, we've already, I'm showing you where it doesn't have the x powers in front, but we're looking at having singular points. So if we have a singular point, we had something in front of that y double prime term that caused these, the p and q here to have singular points. So it's the same type situation, but this is the indicial equation. So now we're going to look at cases where the p naught here, we may not have just a constant term. We may have actually an expression that's analytic. So it may be that the function here, which we're going to call the x minus x naught p naught, this is analytic. And the x minus x naught squared q of x is analytic. If those are analytic, that means we had some power series expanded around x minus x naught. So we can rewrite these as power series, and we would have some q naught plus q1 times x minus x naught, and so on. Likewise, this one could be written as some p naught plus p1 times x minus x naught, and so on. So now when we look at the limit of these expressions, the x minus x naught p of x and the x minus x naught squared q of x, if x is approaching x naught, that means that all of these terms out here that have the x minus x naught expression are going to go to 0. So we're going to get simply the p naught and the q naught. And those are going to be what we're going to use to determine what the indicial roots are. We're going to need the p naught and the q naught to be able to fill into this equation. Okay, so let's look at an example here. I want to find the indicial equation and the exponents for the singular point x equal -1. So we showed that x equal 1 was an irregular singular point, x equal -1 was a regular singular point. And so those are the ones that we're going to be looking at. The regular singular points are the only ones we're going to be able to get a series solution for. So we've got to figure out what is the r value that will lead us to that series solution, that has the x to the r term in it. Okay, so for x equal -1, I'm going to consider, okay, first I need to get it in this form. I'm going to go ahead and break this down. Okay, so here's my p of x. And here's my q of x. Okay, now form the x minus x naught p of x and the x minus x naught squared q of x. Okay, which if this is a regular singular point, those will be analytic. And we'll have x plus 1 because x naught is -1. So we're looking at x plus 1 times the p of x, which when I multiply x plus 1 times the p of x here, I end up with 1 over x minus 1 squared. X plus 1 squared q of x comes out to be -1 over x minus 1 squared, okay, which are both the same expression. Okay, and then once I get the x naught, my x minus x naught p of x and the x minus x naught squared q of x, I just want to find their limits. So I want to find the limit of the x plus 1 p of x, which as x approaches the x naught, as x approaches -1, which is the limit of 1 over x minus 1 squared as x approaches -1, and that comes out to be 1/4. Just evaluate it. Likewise, the limit down here, the x plus 1 squared q of x, comes out to be a negative 1/4. Okay, so now we've got the P naught and the Q naught for this expression. Now notice if this had been a power series, we could have also just plugged in the -1 and gotten the leading coefficient as well. Okay, so using the 1/4 and the -1/4, our indicial equation then becomes r times r minus 1 times the P naught times r plus the Q naught equal to 0. So we're going to have, let's see, this is my P naught. Whoops. P naught is this. Q naught is this. So the P naught okay, so I filled in 1/4 and -1/4 here for the P naught and the Q naught. And now just simplifying, so I've got r squared minus 3/4 r minus 1/4. If you multiply through by 4, just to make it simpler to factor, okay, so we end up that r is negative 1/4 and r equal to 1. So those are our indicial roots. And this was our indicial equation. Any of these forms here, it doesn't really matter which of these you use. Okay, so that's what's going to tell us how to find the root. X to the 1 and x to the -1/4 will be what we use to try to find our series solutions. Okay, so now we want to find a series expansion about the regular singular point x equals 0. We see in this differential equation that x equals 0 and x equals -2 are both singular points. X equals 0 will be a regular singular point. So we want to find a series expansion about that. So to do that, let's first find our indicial roots. Okay, when you have a regular singular point, the solution that can be found, it'll be a series expansion, not a power series. Power series are where the exponents are all positive integers from x to the 0, x to the 1, and so on. Series expansion, we're looking for something of the form y equal the summation of the a sub n's x to the n plus r. Okay, so that's the solution form that we're going to have when we have regular singular points for the differential equation. So now let's find those indicial roots, the r's that will make that true. Okay, to find that, we know that P0 will be the limit. Since x equals 0 is the singular point, we're going to look at x minus 0, which is x, times the P of x. As x approaches the singular point, which is 0 in this case. Now, our P of x will be what you get when you divide this term by the one in front of the y double prime. So we're going to have a minus x over x plus 2 times x squared, which comes out to be the limit of minus 1 over x plus 2 as x approaches 0, which is -1/2. Our q naught will be the limit of x squared times the q of x, and we get our q of x by taking the expression in front of the y divided by what's in front of the y double prime. So we would have x plus 1 over x plus 2. The limit as x approaches 0 will be positive 1/2. Okay, so now let's find our indicial equation. Which we know is r times r minus 1 plus the p naught times r plus the q naught equal to 0. So we'll have r minus 1 plus negative 1/2 r plus 1/2 equal to 0. So we have two roots, r equal to 1/2 and r equal to 1. Okay, now we're going to go through the same process that we did before, finding the power series solutions. We're going to look at, I'm going to pick one of these r's. So I'm going to use the largest one to start with. So for r equal to 1, the series solution that I'm going to be looking at then would be the summation of the a sub n's x to the n plus 1. And I'm going to use that and plug into the differential equation. So we're going to have the second derivative of the y here. So if y is a sub n x to the n plus 1, that means that y prime will be a sub n n plus 1 x to the nth, and y double prime would be a sub n n plus 1 n x to the n minus 1. So the y double prime Now I'm going to expand. I've got x's here in front, so I need to distribute that through that summation. So I'm going to rewrite this as x cubed plus 2x squared. Well, let me do it this way. I'll have an x cubed times this whole summation, and then I'll have a 2x squared times the whole summation. Now go ahead and distribute this x through. And now here I'm going to need to do the 1 times the summation and then x times it. Now the different thing about these types of solutions, I haven't noted here, but we're starting here with n equals 0. When you take the derivative, because we allow to have exponents that are not positive integers, we continue with n equals 0 for these summations. So you don't have to get rid of them like we had to adjust them before with positive integers, because otherwise we would have had an x to the minus 1 power. Here, that's allowed. just because of the nature of the singular roots. Okay, so now distributing through the summation. This gives me x to the n plus 2. Okay, and all these are n equals 0. Okay, so I have some of them that have an n plus 2, so I'll have an x to the second, and some of them will just have an x to the first power. So let's pull out the ones that have the x to the first power. So that'll be the smaller power of x. I'll group those, and then I'll leave the summations all starting at x to the second power. So I'll have an extra term here that has an x to the 1 here and here. The other two will start with x to the second. So plugging in n equals 0 into that second summation, I'm going to get 2a to the 0 times 1 times 0, so that's just going to be 0 here because of the n here. And then this one, when I plug in the n equals 0, I'm going to have a minus a sub 0 times 1, x to the 1. And then the third one here, I'm going to have a plus a to the 0, x to the 1. Well, that just gives me 0, so I can pretty much just eliminate that first term. So this just becomes the summation of n equals 0, a sub n, n plus 1 times n, x to the n plus 2, plus the summation of n equal 1 now, because that first term was 0, same thing with this one. This is really starting at 1. Likewise, this one. Oh, those two terms canceled out, so that's why I'm... You know, actually, those two summations, if I combine them right now, they already have matching indices, and they both have that a sub n. One of them has an a sub n times n, the other one has an a sub n. So those two actually will combine. If I combine these two right now, I'll have an a sub n times n here, and then I'll have a plus a sub n, but because that minus out in front, it's going to cancel with that one. So these two summations just combine to be a sub n times n, x to the n plus 1. Okay, so now, whoops, but that count starts with an n equal 1. The first term was 0. Okay, so now let's match. We now have them all starting at x to the second, but our indices don't match. So let's change them all to k's. I'm going to let k equal to I'm going to change these to, let's see. Okay, so I'm going to start with letting k equal to n plus 2 here. And then I'll use k equal n plus 1 over here. Okay, so if k is n plus 2, that means our k is going to start at 2, since n's starting at 0 here. n will be k minus 2. So this is a sub k minus 2. K minus 2 plus 1 is k minus 1. K minus 2. This one, if k is n plus 1 and n starts with 1, k starts at 2. So we'll have 2. Now we're putting in k minus 1 for the n. Same thing here, k is 2. We're letting k be n plus 1, so n is k minus 1. And the last one, we're letting the k be n plus 2. So k will start at 2. N is k minus 2. Okay, so now we should have them all matching. So let's combine them into one summation. And again, for this differential equation to be 0, the coefficient of the x to k has to be 0. So we have the recurrence relation of a sub k minus 2 Okay. Solve for the largest a sub k. Notice I have a bunch of a sub k's. Let me group the a sub k minus 1s and the a sub k minus 2s together. So I have a sub k minus 2s, and I'm going to distribute this. So that's k squared minus 3k plus 2. And I have another plus 1 over here. And then my ak minus 1s will be 2k times k minus 2. So I'm distributing this. So that's going to actually be 2k squared minus 2k. And then minus, this minus distributed here, will be minus a k plus a 1. Okay, so now this all applied for k equal to 2 and greater. Okay, so if I want to find what the largest a is going to be, it's going to be this one. So let's solve for that. Our recurrence relation then is a sub k minus 1. And I'm just going to combine these at the same time. 2k squared minus 3k plus 1. Oops. I'm solving for a sub k minus 1. I've got them backwards here. Okay, so I'd need to take this to the other side. Whoops, and I just erased it. Okay, so let's take this term to the other side. So we're going to have minus k squared minus 3k plus 3 times the a sub k minus 2 all over. And now this is 2k squared minus 3k plus 1, which this will factor to be 2k minus 1, k minus 1. Okay, so this is for k greater than or equal to 2, and that's going to allow us to find those coefficients, the a sub k's. Okay, so just like we did before, we need to make a table where we're going to plug in all the different k values starting at k equal to 2. Okay, so when k is equal to 2, a sub k minus 1 on the left, that will become an a sub 1. So this will be a sub 2, a sub 3, and a sub 4. Okay, when k is equal to 2, I'm going to have minus k squared 4 minus 6, so that's negative 2 plus 3 is 1, so negative 1 over 3 times 1, and then a sub 0. K equal 3, I'm going to have 9 minus 9 plus 3, so minus 3 on top, over 5 times 2. And that'll be a sub 1. Okay. A sub 3 will be minus 16 minus 12, so 4 plus 3 is negative 7, over 7 times 3 is 21, a sub 2. And then we're going to have 5, so 25 minus 15 is 10, 13, negative 13 over 9 times 4. Okay, and if I didn't multiply these all out, I could probably see the pattern. I'm not going to worry about that. So this is negative 3/10 times the a sub 1, which is the minus 1/3 a sub 0. So that's going to give me a 1/10 a sub 0. This is negative 7 over 21 times the previous term. Actually, the minus 7 over 21 is 1/3. So I have minus 1 over 30th a sub 0. Okay, and let's look at what our form of the solution is here. We know our solutions of the form y equal to the sum of the a sub n's x to the n plus r, and we were using r equal to 1. Okay, this expands out. Now, notice I've got that x to the 1 with every term. I can rewrite that as x to the 1 times the summation of the a sub n's x to the n, and then it looks similar to what we had before. So we're going to have x times a0 x to the 0, so just the a0 term, plus a1 x plus a2 x squared. So if we pull that x to the n, x to the r out right here, then the rest looks like what we've had in the past. So we start with a0. Our a1 is minus 1/3 a0. Then we have plus 1/10 a0 x squared minus 1/30 a0 x cubed. And just pull out the a0. Okay, if we want to choose the a0 to be just 1, we would have our solution to be just x minus 1/3 x squared plus 1/10 x cubed minus 1 over 30 x to the 4th plus dot dot dot. Okay, so we have one solution then that corresponded to the indicial root r equal to 1. In this case, if we go back and repeat the process, so go all the way back up to here, where we actually chose the r equal 1, if we go back to there and now choose the r equal to 1/2, the second indicial root, we will get a second solution. But that it doesn't always happen. Sometimes, depending on the nature of the two roots, sometimes you won't get but the one solution. So I'm not going to go through all that work, but it'll be the same thing with the r equal 1/2. You're going to have the x to the 1/2, or n plus a 1/2 power on some of these terms. You'll want to pull out the x to the 1/2 and so that you can then work with the integers for the exponents for that. But in this case, when we're dealing with regular singular points, we're not guaranteed two separate solutions. We only will know that we for sure have one solution, a series solution, not a power series solution. This particular one was a power series. Okay, so now if x naught is a regular singular point, then we're guaranteed that there exists at least one series solution of the form y equal the summation of a sub n x minus x naught to the n plus r, where r is the larger root of that associated indicial equation. Okay, now the confidence interval, we know that the interval r, the radius of convergence, will be the distance from the x naught to the nearest singular point. Okay, so let's find a series solution about the regular singular point x equals 0. We know we're guaranteed 1 as long as the x is a regular singular point. And if we check the p of x here, we have x over x naught. So if you divide through by the x squared, you're going to have y double prime minus 1 over x y prime plus 1 minus x over x squared y equal to 0. So remember, it's a regular singular point if x times the p of x and x squared times the q of x are analytic at that point. So we're looking at x equals 0, and so these are analytic at x equals 0, which means x equals 0 is a regular singular point. Okay, so let's find the indicial roots. Okay, so to find the indicial roots, we need to find the p naught, which is the limit of the x times the p as x approaches 0. Okay, and our p of x, well, we just found these. Here's our x times the p of x, so that comes out to be just -1. Okay, the p2, okay, which is just this expression, whoops, x squared. Not sure why I'm calling these p0, but this should be the q0. Okay, and that comes out to be 1. So our indicial equation so this is r squared minus 2r plus 1, which comes out to be just r minus 1 squared. So our only indicial root is r equal to 1. Okay, so that's only going to be able to lead us to the one series solution. We'll see, we're not going to this right now, but we will see that there are ways to get a second solution once you have one, but that'll be another process. Okay, so we know that our solution here will have the form y equal the summation of a sub n x minus x naught, which is 0 in this case. We're using x equals 0, x to the n plus 1. Okay, and we're just going to plug that into the equation. We know that we have x squared y double prime. Y prime is a sub n, the sum of a sub n n plus 1 x to the nth, and y double prime will be the sum of a sub n plus 1 times n x to the n minus 1. So x squared times the summation minus x times the y prime times the y is equal to 0. So distributing through the x's, we're going to have the summation x to the 1, n plus 1, minus n plus 1, and now all these start at n equals 0. Since we are possibly going to have negative, it's not a power series, it could have negative exponents and fractional exponents. So we're going to have 1 times the summation, and then minus x times the summation, and so I'll just take that x inside. Okay, so now we have an x to the first, an x to the first here, an x to the first, and an x to the second here. Okay, so the first three will start with an x to the 1 power, and the last one starts with an x to the 2 power. So I'm going to pull a term out of each of the first three. So when I let n equal 0 on the first summation, I have a sub 0, n plus 1 times 0, so that one's not going to give me an extra term. So I can just change this to starting at summation of n equal 1. Then I'm going to have a minus a sub 0 times 1 times an x to the first, and then a minus summation of n equal 1 and larger. And this one will start with a minus a sub 0 and then an x to the 1, and then plus a summation of a sub n x to the n plus 1 starting at n equal 1. Okay, and you'll see, let's see, this is actually a plus here. So again, these two terms cancel, so we just had to adjust those summations. Okay, so now, to make all the indices match, I'm going to let k be the n plus 1 or k equal n plus 2 everywhere. Because we know they all should start with an x to the second power now. So if this one starts at k equal to n plus 1, the k value then is going to start with 2, and that means the n is k minus 1. So this summation becomes the summation of k equal to a sub k minus 1, k minus 1 plus 1, so just k, times k minus 1, x to the k. Same thing for this one. We're going to let k equal n plus 1. So a sub k minus 1, k minus 1 plus 1, so that would be k, x to the k. Same thing here. And then the last one, we will let k be n plus 2. So k is going to start at 2, and n will be k minus 2. Okay, making it all one large summation now. Notice these first three all have an a sub k minus 1. So I'm going to go ahead and group those, and of course all of them have an x to the k. So I'm going to take an a to the k minus 1 out of the first three summations, and I'm going to end up with a k times k minus 1, a minus k, and then a plus a sub plus 1. And then the last summation will leave me with the minus a sub k minus 2, and all of this is times the a sub k, x to the k. Okay, so now each coefficient of the x has to be 0, so this has to be 0 for each k from 2 on. So our recurrence formula will be a sub k minus 1. We'll distribute this out. That's k squared minus 2k plus 1 minus a sub k minus 2, and that's equal to 0. Okay, the biggest a sub k subscript will come from this one. So we have that a sub k minus 1 will be equal to a sub k minus 2 over, and this is just k minus 1 squared. And that's for k greater than or equal to 2. Okay, so we're going to look at k equal 1, or k equal 2, k equal 3, k equal 4. So we're going to have a sub 1, a sub 2, a sub 3, a sub 4. So it's going to be a sub 0 over 1 squared. A sub 2, so this will be a sub 3, a sub 4, over 2 squared, 3 squared, 4 squared. Okay, so we have 1/4, oops, this should be a sub 1, of a0. This will be 1/9 times 1/4 a sub 0. This will be 1/16 times 1 over 36 a sub 0. Okay, so our solution then, we know is of the form, the summation of the a sub n's, x to the n plus 1, since our r was equal to 1. Okay, so that's going to be that'll be a sub 0 x plus a sub 1 x squared, a2 x cubed, so we keep a0 the way it is. Our a1 is a0. Our a2 is 1/4 a0. Okay, if you want to let a0 equal to 1, you have a solution y equal x plus x squared plus 1/4 x cubed plus 1 over 36 x to the 4th, and so on. Now, since 0 was the only singular point to the equation up here, okay, so x equals 0 is the only singular point, then there's not another singular point, so that means that the radius of convergence would be infinite. So it'll converge for all x greater than 0. Okay, and so we need another process to be able to find that second linearly independent solution, but we're not going to work with that in this section. Now we're going to look at using matrix methods to solve differential systems. Okay, the product of a matrix and a column vector is defined to be the collection of all the dot products of the rows of the matrix with the vector. So I'm writing the vector v here as a column vector. So the entries will be vertical, one entry per row in a vertical fashion. The matrix A here, I'm representing each row instead of by individual entries. I'm representing it just as row 1, row 2. So if we take this first row and the dot product of this vector, so we'll denote that as row 1 dot with the vector v. Now remember how that's defined. If this is our row 1 and this is the vector v written as a row vector, then a dot product is just multiplying the first entries together plus the product of the second entries plus, and you have to have the same number of entries in each vector to find the dot product. And so a sub n times x sub n will be the last entry that you're summing. So the dot product is just taking the sum of the products of corresponding entries, first entries, second entries, and so on. Okay, so now I want to express this system of differential equations as a matrix equation. So the way I'm going to do that is to use a matrix to represent all these derivatives on the left side. So I'm going to write this as a matrix or a vector, a column vector, x1 prime, x2 prime, x3 prime, and x4 prime. Okay, now because of the way multiplication is defined, I'm going to note that each one of these equations has the variable, the x1, x2, x3, x4. That's the dependent variable that we're trying to solve for in this system of differential equations. So I've got my x1, x2, and x4 here, and x2 and x3, 1, 2, 3, 4, and then there's none of them in the last equation. But I can view this as a matrix product. So what I'm going to do is I'm going to take, for each equation, I'm going to take the coefficient of the x term. So I'm going to let x1 represent the coefficient, or column 1 will be the coefficient of the x1 term. Column 2 will be the coefficients of the x2 term, x3, and x4. So look for the coefficients of those terms in each equation. So each row will represent one equation. So I'm going to have 2t squared, and then there's no x3, so I'll put 0, and then I'll have 4t plus e to the t for my last entry in row 1. In row 2, I look at the second equation. There's no x1, so I'll have 0. I have sine of t. There's x3 has coefficient cosine of t, and there's no x4, so coefficient would be 0. In x3 prime, the third equation, I have 1 x1, 1 x2, 1 x3, and 1 x4. And the last one, there's 0, so that means 0 of each of those variables, x1, x2, x3, and x4. So now, pulling those coefficients off, and now creating the matrix x1, x2, x3, x4, which we call matrix X, we'll just use a capital X to represent this matrix that has the entries x1, x2, x3, x4. Okay, so we usually use a capital A to represent this coefficient matrix, and then the matrix over here on the left side is just the x that we have over here, except it's the derivative of each. So we'll call that x prime, represent the derivative of each of the entries in x. So this is our matrix equation. X prime is equal to A times x, where this is my x prime matrix, or column vector. This is my matrix A, and then this is the vector x. So it's just a matrix with one column. Okay, so that's expressing that system of equations as a matrix equation. Okay, so now in general, if you have a system of differential equations in this form, we're going to use x to represent the vector containing those dependent variables that we're trying to solve for, x1 to xn. So this is our solution vector. It has an entry for each of the solutions that we need, the x1 to xn. Now, so if this is x prime then is going to be the vector that's defined to be just the entries that are the derivatives of each of those. Okay, so this left side of this differential equation is the x prime vector. The a is the coefficient vector, so we're just taking the coefficients of each of the x's and making each equation a separate row. So we'll have a11, a12 up to a1n, and likewise for row 2, a21, a22, and a2n, all the way down to the last row. Now, that's our matrix A here. And now times the vector x, which again is this vector. So if I took this A times the vector x, notice the definition here, put times x on each of these. The definition is to take the dot product of row 1 with the column vector. They have to have the same number of entries to be able to find that dot product or to be able to do this multiplication. So this product comes out to be the first entry here times the x1, so a11 x1, plus the second entry times the second one, a12 times x2, plus, and keep going until you get to the last entry, which is a1n times x sub n. Now I left off the of t's. These are assumed to be functions of t. Okay, so that's the first row, and you can see that that is what you get right here, which if you then take this matrix, which has those entries in it, x1 prime, x2 prime, these two matrices will only be equal if their corresponding entries are the same. So here's the whole first row is just a single number since it's a sum of products, and that will give us this x1 prime. So x1 prime equal to this, which is just exactly what that system is saying. So we can take a system of equations with the x1 to xn, or the dependent variables. They're differential equations, so we have the x1, x2 primes on the left side. This is in that normal form. Remember, normal form is where you have the derivative solved for in each equation. And this is considered a homogeneous system because you just have x prime equal to a times x. Now, had we had some extra functions out here, meaning you had extra terms that didn't have the x's in each one of these equations. Notice every term here has an x to the n, you know, with the term. So had there been a plus t squared, then we would have had another vector over here that we would needed to add to it. So let's say we had a t squared here and a plus 3 here and a plus 2t here, or 2t sine t. Then this extra vector that we would have would be t squared, 3, and down to 2 plus sine t. So you would have an extra vector here. So when you don't have that, if this vector is all zeros, then it's a non-homogeneous system. It's homogeneous if all the terms in the equation on the right side have the x sub n. Okay, in the last section we took a system of first order equations in normal form, and we could express that in matrix notation. What we want to look at now is taking a higher order differential equation and writing it first as a system of first order equations in normal form, and then we'll be able to express it as a matrix equation as well. So I've got an equation, a differential equation for the undamped, unforced mass spring oscillator system that we were working with previously. I'm going to use y, which is that's our position function, so that's one of the unknowns, and I want to use the fact that if y is a position function, then the velocity is just the derivative of y. So I'm going to use that for my second variable in my system. So I'll use y and v as my two variables. So the vector of unknowns then will be y and v. Okay, so to get a system of first order equations in normal form, then I need two equations, one for y prime and one for v prime. Okay, and those will both be, I'll have y prime as a function of v and y, because it needs to be a first order equation, so it won't have any other derivatives. So it'll be some function of y and v, and then I'll have v prime will be some function of y and v. So that's my goal, is to get two equations, one for y prime and one for v prime. Okay, so if v is y prime, we know that acceleration is v prime, which is just y double prime. So I'm going to use that to turn this second order into a first order derivative. So my two equations I'm looking for are y prime and v prime. I know y prime is just v, just based on the substitution that I'm going to use and based on the relationship between the position and the velocity function. I need an expression now for v prime. Okay? Now I'm going to get that because this equation, if I substitute v prime for y double prime, this equation becomes m times v prime plus ky equal to 0. So my expression then for v prime will be minus k over m times y. So now I've written y prime and v prime as just functions of y and v. Okay, so now let's write that as, I'm going to write it as a system with y and v just being a little more explicitly stated here. So y prime then will be 0y plus 1v, and v prime will be minus k over my plus 0v. So now I'm going to take this system of first order equations in normal form and write it as a vector, as a matrix equation in matrix notation. So this will be yv prime equal the matrix 0, 1, negative k over m, 0, times the vector yv. So now I have matrix notation for a system, of a system that is equivalent to that second order differential equation. Okay, so now let's look at what would we do if we had an nth order differential equation. So let's say that we had an equation. We'll have a sub n nth order derivative plus a sub n minus 1, and these could be functions of a t or so. Y n minus 1, that's an n minus 1 derivative. So this is an nth order linear differential equation. So I want to be able to write that as a system. It's going to be a system of first order equations in normal form, and then we'll be able to express that single differential equation then in matrix notation. So what I'm going to do is I'm going to take all the variables here. Now I have y and all of its derivatives. So y prime, that's the nth order derivative of y. I'm going to let those be my unknowns. So I'm going to say that x1 will be y, x2 will be y prime, okay. So the first derivative is x2, so that means the nth derivative, or the n minus 1 derivative, or the n minus 1 term, will be the n minus 2 derivative, and that means the nth term, x sub n, then will be one less derivative, so the n minus first derivative of y. Okay, so I'm using these to be my unknowns. So this equation then would come out to be a sub n, and the nth derivative would be n x sub n prime. Now this n minus first derivative is just x sub n. And then I would go on down, and I've got a sub 1 times y prime, which is x2, and then plus a sub 0 times y, which is x1. Okay, so this equation, all I'm doing is I'm substituting these values. The y becomes x1, the y prime becomes x2, and I'm doing that for each one of these. So then this would be the x sub n, and so this one would be x sub n prime. Okay, so what I've got now is I've turned that into a single first order equation where I can easily put that in normal form. So that means x sub n prime will be minus so if I wanted to put these in the opposite order, I'd have minus a sub 0 over a sub n, x1, minus a1, x2, over an. And this would be x sub n. Okay, so I've got one equation here, one normal form for x sub n. So what I need now is I need to find x1 prime, x2 prime, x3 prime, all the way up to x sub n minus 1 prime. So if I want to have a system of first order equations in normal form, I need the primes for each one of these variables that I'm going to use. Okay, so we started with x1, x2, and defined our variables over here, x1 to xn. Now we want an expression for x1 prime, x2 prime, all the way down to xn prime. So now, what would x1 prime look like? And notice I need all of those in terms of just those variables as well. They need to be functions of the x1, the x2, down to the xn. So x1 prime will be y prime. But notice y prime is just x2. So there's my normal equation for x1 prime. What about x2 prime? Okay. I know from here that x2 prime would be y double prime. But y double prime is going to be x3, right? If I had written another term down here, x3 would be y double prime. Okay, so continuing with that, if I go down to x sub n minus 1, I want an expression for x sub n minus 1 prime. Well, if I take the derivative of x sub n minus 1, I've got x sub n minus 1 prime is going to be the derivative of the n minus second order derivative of y, which will be the n minus first order derivative of y. So all I'm doing is I'm taking the derivative of both sides here. So x sub n minus 1 then will be equal to the n minus first order derivative of y, but that is x sub n. Okay, there's my system of normal equations. I have x1 prime, x2 prime, and I'm just going to repeat xn prime down here. Remember, I found it up here to be okay. So there's your system of first order equations in normal form. So if you want to write that then as a matrix equation, we're going to have x1, x2, down to xn prime. I'm not going to be able to, since it's not a set size. x1 prime is x2, so that's going to be 0 x1s plus 1 x2 plus 0 x3s, and there'll be all zeros across till the nth position. x2 prime, we know has 0 x1s, 0 x2s, 1 x3, and then 0 for all the others. And then you would just continue. The n minus first would be zeros across the board until you got to the last position. And then x sub n prime, we would have minus a sub 0 over a sub n, minus a sub 1 over a sub n, down to minus a sub n minus 1 over a sub n. And this will be multiplied by x1, x2, down to xn. Okay, so if you did the multiplication, you see that you do come up with the same system. So that's how we'll take a single nth order equation like this and write it as a system of first order equations in normal form, and from there it's just easy to go straight to the matrix. Okay, so now let's say we had a system that had two variables and they were both higher order. So what we're going to do is the same thing. We're going to assign new variables. We're going to say we've got x, we've got y, we've got derivatives of x and y, and we're going to need to have up to the second order derivative. So what I'm going to do is I'm going to assign four variables, x1, x2, x3, x4. I'm going to say x1 is going to be x, x2 is going to be x prime. I'm going to let x3 be y and x4 be y prime. Okay. So now that's going to allow me to take these two equations and rewrite them, because I need to have equations now for x1 prime, x2 prime, x3 prime, and x4 prime. That's going to be my system in normal form for these four variables. Okay? So to do that, x1 prime will just end up being x prime. Okay? But I need these to be in terms of, all these need to be functions of the four variables, x1, x2, x3, and x4. So I can't leave it as x prime. I need to look at what was x prime in terms of those variables, those new defined variables. X prime is x2. x2 prime. Well, we know x2 prime is x double prime. Okay, so what I'm going to do then is, this is x2 prime. So I'm going to use that to rewrite that first equation using my new variables. I'm going to have twice x2 prime, which is x double prime, plus 6 times x, 6 times x1, minus 2 times y, which is 2 times x3, equal to 0. That gives me a normal equation for x2 prime. So I'm just going to move these terms to the other side and divide by 2. Okay? Now x3, I need to have x3 in terms of x3 prime, in terms of x1, x2, x3, and x4. And I've got here that x3 is y, and so that means x3 prime is y prime. But I know y prime is equal to x4. So that's how I'm getting x3 prime in terms of these variables, these unknowns. So x3 prime is x4. Okay? So now x4 prime. We know x4 prime from this equation is y double prime. But we're going to get that up here. We're going to use this relationship to find what y double prime is. Y double prime is x4 prime. So this will be x4 prime plus 2 times the y, which is x3, minus 2 times the x, which is x1. Again, I'm trying to get them in terms of the newly defined variables. Okay? And from that, then, I can solve for x4 prime and just by taking these to the other side. So x4 prime will be x1 minus 2x3. Okay? So now I have a system here in normal form. x1 prime is x2. x2 prime is minus 3x1 plus x3. x3 prime is x4. And x4 prime is x1 minus 2x3. Now, easily from there we can write it as a matrix equation. So now if you solve this, you're going to get all four of these variables, but you may not need them all. You may just need, the x and the y, which you'll have them. So this will be, the unknown is x1, x2, x3, x4. And so our coefficients will be 0, 1, 0, 0, negative 0, negative 3, 0, 1, 0, 0, 0, 0, 1, and 1, 0, negative 2, 0. Just realized I dropped my 2 up here. It should have been 2 when I took it to the other side. The y was x3, or the x1 was the x. So I missed that 2, so this would have been 2 down here. Okay, so easy. Just look at the variables you have, the x and the y, and we'll need a y prime, and then we'll get the expression for that y prime, the derivative of the last one, using these two equations up here. So start with this and get an expression for the derivatives of each one of those. So notice we only went up to the first order derivative when we assigned those new variables. Now we want to look at solving a system of equations using matrices. So you maybe did this back in an algebra class, and if not, this will be a chance for you to understand the method. We have a system of equations that are of this form. Okay, our unknowns are the x's, the x1, x2, up to xn. So just like you were solving a system back in an algebra class. Unknowns Okay, so the first thing we're going to do is we're going to write this as a matrix equation by taking the coefficients of the x's and forming a matrix A containing those. So it's going to be A11, A12, all the way over to A1n, and then A21, A22 to A2n, and then we'll skip down, and then we'll come down to AN1, AN2 to ANN. So that's our coefficient matrix. We'll call it A. Now, the matrix containing the solutions, x1, x2, will be called X. And then what we want to get for each equation will be the B. So we're going to have B1, B2 in a column vector on the right side. So our equation is A times X equal to B. And that's what we want to solve. Okay, so this is a linear system of n algebraic equation with n unknowns, x1 to xn. Okay, so now we're going to use an elimination method. That's what you did back in the college algebra class, where you eliminated the x terms or eliminated the y terms. But we're going to do it on a bigger scale here. And the method that we're going to be using is going to be called the Gauss-Jordan method. I'm going to do it first with keeping the equations so that you can do what see what we're doing, and then we'll eventually go to where we only work with the coefficient matrix so that we don't have to carry all those x's, since we know each column would relate to a specific x. So the Gauss-Jordan elimination algorithm, it allows us to uncouple the system, and that means to make separate equations for each of the variables. Instead of having each equation having the x1, x2, x3, if we can get it down to having one equation where all it has is one of the variables, 5x1 equal to 10, then we have the solution for x1. So uncoupling just means that we rewrite it as a system of equations where each equation has a unique variable, one of the variables remaining. Okay, so the way we're going to do that is we're going to start with an equation, and we're going to use the first x1 term to eliminate the x1 from all of the others. Okay, so if we were trying to eliminate x1 back in college algebra, you'd multiply the first equation times -2 and add it to the second one. That would eliminate the x1 from equation 2. So I'm leaving equation 1 alone, and I'm going to eliminate the x1 from it using equation 1. So I'm going to write down equation 1. And now I'm going to eliminate x1 from equation 2 by multiplying the first equation times -2, since that's what would give me the -4 that would eliminate the 4 here. And then I'm going to add it to the second equation. So I've got -2 times 2x1 plus 4x1 is 0x1. -2 times 6x2, and then add that to 15x2 would be plus 3x2. -2 times the 8x3, and then added to the 19x3 is going to give me a 3x3. And then the -2 times the 16 is 32, plus the 38 is going to give me 6. So we just eliminated the x1 from equation 2 by adding a multiple -2 times the first equation. So sometimes we'll denote that as -2 times row 1 added to row 2. And that's what we got our new row 2 here. Actually, let me go ahead and If I'm just working with the numbers, I'll tend to write this. So that's my new row 2. Okay, likewise, I have a 2x1 in the third equation. I want to eliminate the x1 term from the third equation, and I can do it by multiplying the first equation through by a -1. Because that's going to give me the -2 for the x1 that will eliminate the x1 from this one. So now I'm going to have -1 times row 1, and I'm adding it to row 3, and that's giving me my new row 3. So -2x1 plus 2x1 is 0x1. -1 times the 6x2 plus, there's no x2's here, so it'll be a -6x2. -1 times the 8x3 and added to the 3x3 will be a -5x3. And then the -1 times 16 is -16 plus the 6 is -10. So we've just now reduced our system to where only one of them has an x1 term. Okay, so that's our new system that we're going to be working with. All we've done is add multiples of a row to another row, and so the solution to this system will be the same as the solution to the previous system. Okay, now let's look at x2. I'm going to use the second equation's x2 here to eliminate the x2 from the other equations. Now to do that, I'd need to multiply that one Okay, so we now have a 3x2 here. To eliminate the x2 from equation 1, I'll need to multiply equation 2 by -2 and then add it to equation 1. So I'm doing -2 times row 2 and adding it to row 1. And I'm going to get my new row 1. So I'm going to have, notice -2 times the 0 is going to be 0x1s added to the first 2x1, keeps the 2x1 there. It's not going to ever change that first term because there's only 0 in that first entry, the x1s. Now the -2 times this term added to this term is going to give me 0x2s. -2 times 3x3 is -6x3 added to the 8x3 is plus 2x3. -2 times 6 is -12 plus the 16 is 4. So we've just rewritten equation 1 by adding the multiple of row 2, -2 times row 2, to the first equation. And we've eliminated the x2 from that equation. Okay, now we're going to just keep x2, the equation 2, the way it is. We're not going to do anything to it. So that one's still going to be the 0x1, the 3x2, plus 3x3 equal to 6. Okay, now equation 3. I want to eliminate the x2 from it, and I'm going to use equation 2 here to do that. So what multiple of this x2 would I need to add to this? I'd need to add 2 times it. So take 2 times row 2. I'm changing row 3 now. So I'm going to have 2 times row 2, and I'm adding that to the current row 3 over here. So twice this, and this added to this equation. So twice, well, I have 0x1s, and added to the 0x1s, it's going to still be 0x1s. Twice 3x2 will be 6x2 plus the -6x2, which better be 0x2 because that's how we chose the 2. 2 times the 3x3 will be 6x3 added to the -5x3, so it's plus a 1x3. And then 2 times the 6 is 12, added to the -10 is 2. So now here's our new equation. Notice we now only have one equation with an x2. So the next thing to do is going to be to eliminate the x3. Now notice the last equation now is totally uncoupled. I only have the x3 in that third equation. So I'm going to write down just x3 equal to 2. If we know what x3 is. Now I'm going to use that equation to eliminate the x3 from the second equation. To do that, I'd need to take -3 times this equation. So negative 3 times equation 3, which I'll say row 3, added to the row 2. So negative 3 times this one added to this one. So it's not going to change the x2s any, because negative 3 times 0 is still 0 x2s plus the 3x2. Negative 3 times this added to this will be 0 x3s. Negative 3 times the 2 here added to the 6 up here is 0. We've now decoupled or uncoupled equation 2. All it has is an x2 in it. So now the last thing to do is to change equation 1 by removing the x3 term from it. And that'll decouple it as well and only have an x1 remaining. So to do that again, we're going to use the equation where the x3 appeared decoupled. So we're going to use equation 3 and add a multiple of it to equation 1 to remove the x3 from it. So the multiple I need to use would be negative 2. So I'm going to now take negative 2 times row 3, which is this equation, and I'm adding it to the row 1. Since there are no x1s or x2s in equation 3, it's not going to change this at all. It's going to still be 2x1 plus 0x2, and now I'm adding negative 2 times this to this, which will be 0x3s, and now negative 2 times this, which will be negative 4, added to this will be 0. Okay, now each equation in our system has been uncoupled now. The first equation just says that 2x1 is 0, which tells us then that x1 has to be 0. The second one tells us that 3x2 is 0, which tells me that x2 must be 0. And the third one just says that x3 is 2. So our solution to this system would be, if you want to look at it as a point, 0, 0, 2. Let's see, 0, 0, 2. Let's see, just verify that this really would be a solution. So 0 plus 0 plus 16 is 16. 0 plus 0 plus 38. 0 plus 6 is 6. So that is a solution to that system. Okay, so the idea here is we're going to remove a variable from each equation. The first equation will retain its x1. Then use that to eliminate x1 from the other two. Then take the next equation. Here, it doesn't have an x1. You're going to use that equation to eliminate the x2 from all of the others. So you're keeping the x2 in that equation. Then take multiples of it and add it to the first and second and third equations to remove that x2. Then repeat, getting down to the third equation that will now have only an x3 because you've already eliminated the x1 and x2 from it. You're going to use that equation to eliminate the x3 from the first two equations. That decouples all three of them, and you're able to simply solve a system. Now, carrying the x's makes it a little more tedious, so I'm going to do the next one by eliminating the x's and just retaining the numbers, the coefficients of those values. Okay, so much bigger system here. I have 4 equations with 4 unknowns. I'm going to have one equation, one row in a matrix for each equation. So I'm going to retain 1, 2, 4, and 1. Those are the coefficients of the x1, x2, x3, x4 in the first equation. And I'm just going to put a separate column for the 0, which will be the numbers on the other side. Row 2, negative 1, negative 2, negative 2, 0, with a 1 on the right side. Okay, so now I'm going to use the matrix, but keep in mind each row is a separate equation. So my first goal is to keep x1 in only one equation. Row 1 will be the only one that contains the x1. I need to eliminate the x1 out of the others by adding multiples of row 1 to the other equations to eliminate the first entries, the first coefficients, which are the x1 coefficients. So I'm going to first just write down row 1 because I'm not changing it. Now, to eliminate the first term here, I need to add a multiple of this one of 1. So I'm going to take row 1 times 1 plus row 2. That's going to be my new row 2. So 1 times this entry is 1 added to this one. 1 times this one is 2 added to this one. 1 times this one is 4 added to this one. 1 times this one is 1 added to this one. 1 times this entry is 0 added to this entry. Okay, so now we've eliminated x1 from equation 1, from equation 2. Same thing on the third equation. We want to eliminate this negative 2. And we're going to do that by adding the multiple of row 1, which would need to be 2 times row 1 added to the row 3. That will eliminate the x1 coefficient from row 3. So 2 times this entry is 2, added to this is 0. 2 times this one is 4, added to this one is 0. 2 times this one is 8, added to this one will be 0. 2 times this one is 2, added to this one will be 0. And 2 times this one is 0, added to this one will be 4. Okay, before I get into any trouble here, I'm going to notice that when I did twice this one, added to this one, I should have gotten 4. Okay, now the same thing with the last row. I want to add a multiple of row 1, which has the x1 in it, to row 4. And so to eliminate that, I'd need to multiply row 1 by negative 1 and add it to row 4. And that's going to give me my new row 4. So negative 1 times this entry will be negative 1 added to this one is 0. Negative 1 times this entry is negative 2 added to this will be 2. Negative 1 times this one added to this one will be negative 2. Negative 1 here added to this one will be negative 1. And negative 1 times this added to this one will be negative 3. Okay, so now we have one equation that has an x1 in it. So now the next step would be to have one equation with the x2. But notice equation 2 and 3 don't have any x2's in them. So what we want to do is let's just rearrange the first and the fourth, or the second and the fourth rows, so that we can get something that has a x2 in that second row. So all I'm doing is essentially rearranging the equations. And we can just shove the other 2 down. Or you can just rearrange them. So we really rearranged. We put 4 in the 2 spot, and then we put the 2 into the 3 and the 3 into the 4. It's all just rearranging equations. Okay, so now I'm going to use equation 2 to eliminate every x2 out of the equation except for that one equation. So that's decoupling or uncoupling the x2. So take multiples of equation 2 here and eliminate the x2 from the other equations, which is just this one entry. So let's take negative 1 times row 2 and add it to row 1. So we're going to keep the other equations the way they are. Nothing's changing except row 1. Okay, so now I'm taking negative 1 times row 2 and adding it to row 1, and that becomes my new row 1. Whoops, my new row 1 up here. So negative 1 times this added to 1 is still 1. Negative 1 times this added to this is 0. Negative 1 times this added to this will be 6. Negative 1 times this added to this will be 2. Negative 1 times this added to this will be 3. Okay, so now we have one equation now that has the x2 in it. We have one equation with the x1. Now we want to do the same for x3. So we're going to use this equation. It needs to be one that already has the other variables eliminated and that has an entry, a non-zero coefficient for that variable. So we're going to use that equation and use it to eliminate the x3 coefficients from the other three equations. Notice the last one already has it eliminated, so I'm just going to write it down. And I'm going to write this one down. Okay, so now I need a new equation 2, and I want to eliminate the x3. And I do that by using row 3, equation 3, and a multiple of it added to that one. So I would have, since this is a 2 and that's a negative 2, I just need to take 1 times row 3 added to row 2, and that will give me my new row 2. So we're just doing row 3 plus row 2, and that's becoming the new row 2, which will be, notice negative 1 times this and this are still going to be 0 added to what was already up here. So this will be a 0 and a 2. Negative, or just this one added to this one will be a 0. This one added to this one. All we're doing is adding rows 2 and 3. And then this one added to this one will be a negative 2. Same thing with row 1. I want to eliminate the x3 coefficient. And I do it by using the row that we're decoupling the x3 with. That's going to be the only one that has an x3 in it. So take a multiple of that. So negative 3 times row 3 added to the row 1. And that's giving me my new row 1. So again, these are zeros, so they're not going to affect what the other row 1 already had. Negative 3 times this one added to this one will be 0. Negative 3 times this added to this will be a negative 1. Negative 3 here times 1 will be a negative 3. Added to the 3 that's here will be a 0. Okay, so now we have one equation with x1, one equation with x2, one equation with x3. Now we want to do the same with x4. So this will be the only equation with an x4, and we're going to add multiples of it to the other rows. Now notice here, if I wrote this back as a system of equations, this just says that 4 times x4 is equal to 4. Right? The third equation here just says 2 times x3 plus x4 is equal to 1, because this would be 0x1s, 0x2s. The second equation just says that 0x1s plus 2x2s equal to negative 2. And the first equation just has that x1 minus x4 is equal to 0. So I've got a simpler equation. The reason I point this out is that this one, instead of working with those 4s to eliminate the 1s in the other equation, I could just take this equation and divide both sides by 4. That's going to make it x4 equal to 1. So if I want to take an equation and divide everything on both sides by that number, it'll simplify the process a little bit when you start getting into bigger numbers here. So that's the first thing I'm going to do. Before I use row 4 to eliminate the x4 from the others, I'm going to divide that equation through by positive 4. So I'm going to have 0, 0, 0, 1, 1. And that's just going to be easier to work with multiples of to eliminate the other. Okay, so now row 2, you'll notice, already has a 0 in that entry, so I'm just going to write that down. And I need to eliminate the x4 from this row, and I'm going to do it by taking a multiple, negative 1 times row 4, added to the row 3. And that's going to give me my new row 3. So again, 0, 0, 0. Negative 1 times those is not going to affect what was already in these positions. So that becomes 0, 0, 2. Negative 1 times this is negative 1. Added to this one will be 0. Negative 1 times this is negative 1. Added to this one will be 0. Now let's go up to row 1 and eliminate the x4 coefficient. So we're going to, again, use row 4, which is the only one that's going to be allowed to have the x4 in it at the end. And we're going to take a multiple of that, which will be just 1 to eliminate that. So we're just taking row 4 added to row 1, and that's going to be my new row 1. Notice these first entries, 1 times those is still 0, so it's not going to affect what was already in those first 3 entries. Now, 1 times 1 is added to negative 1 is 0. 1 times the 1 here is 1, added to 0 is 1. Okay, we now have it decoupled. Let's rewrite it. Remember, the first column are coefficients of x1. The second were the coefficients of x2, x3, x4. We're just rewriting it as a system. We're going to have this row 1 here just says that x1 plus 0x2 plus 0x3 plus 0x4 has to be 1. Row 2, 0x1s, 2x2s plus 0x3 plus 0x4 is negative 2. Row 3, 0x1, 0x2s, 2x3s plus 0x4s is 0. And then finally, x4 is equal to 1. So the only ones we still need to do any work on is we see x2 is negative 1, x3 is 0, and the other two we already have. So our solution then would be the point 1, negative 1, 0, 1 for those 4 variables. If we want to double check ourselves up here, let's just pick one of them and verify. If I put a 1 for this, a negative 1 for this, a 0 here, and a 1 here, I'm going to have 1 minus 2 plus 0 plus 1, and it does equal to 0. So you can go back and verify all 4 equations, and this is the solution to that system of equations. Okay, so this is called the Gauss-Jordan elimination. You try to get one equation with each variable. So you're decoupling it so that all the others don't have that variable involved. Now let's look at another example that might have some complications that I want you to be able to handle. Okay, same idea. We're going to set up a matrix. We're just working with the coefficients and then the values on the right side of the equation. And we're just doing elimination on the equation so that equation 1 will just have x1. If possible, equation 2 will just have x2, and then equation 3 will just have it. We want to decouple the variables x1, x2, x3 among the equations. Okay, so writing our coefficient matrix, it's actually called an augmented matrix because we're going to have the coefficient matrix with that last column of entries, adjacent to it. So we'll have 2, 4, 1, 8, 2, 4, 0, 6, negative 4, negative 8, 1, negative 10. So the left of the bar is the coefficient matrix, and the right side is the values on the other side of the equation. Okay, so now I'm going to leave equation 1 the way it is. It's going to be the only one that's going to contain the x1 coefficient, and we're finished. Now equation 2 and 3, we want to eliminate the x1 coefficients. And we'll do that by using row 1, the one that's designated to have only the x1. So we're going to take negative 1 times row 1 and add to row 2 to be able to eliminate this 2 here. Okay, so we're going to have negative 1 times row 1 added to row 2 will be 0 here. Negative 1 times this added to this will be 0. Negative 1 times this added to this will be negative 1. Negative 1 times this added to this will be negative 2. Now, I want to eliminate the x1 coefficient from row 3. And we're going to use row 1 again. I'm going to take 2 times row 1 and add to row 3. And that will eliminate the x1 coefficient. So twice 2 added to negative 4 is 0. Twice this, 8, added to this is 0. Twice this added to this will be 3. And twice this added to this will be 6. Okay, so the next step was to get equation 2 to have x2 and be the only one with x2. The problem is it doesn't have an x2, and neither does the third one. So we're not going to be able to get an equation with only an x2 in it. So we'll just go to the x3. So I can use equation 2 for the x3 and then eliminate the x3 from the others. So let's just write. I'm going to write equation 2 down. And then let's eliminate x3 from both the first and the third equation. Now to do that, if I want to eliminate x3 from this one, I'll just need to add 1 times the row 2. So row 2 times 1 added to row 1 gives me the new row 1, which will be, row 2. We're just adding row 2 to row 1. So it's going to be 2, 4, 0, and 6. Now, to eliminate x3 from row 3, I'll need to multiply row 2 times 3. So 3 times row 2 added to row 3 will give me my new x3. So 3 times this and this are 0, so we're just going to still have the zeros here. 3 times this is negative 3, added to this is 0. 3 times this is negative 6, added to this is 0. Okay, so now, we've now decoupled. We've gotten rid of, the only equation with an x1 is equation 1. We weren't able to get rid of x2 and everything, but only one of them, x1, had the, row 1 already had the x2. Row x3 is only in one of them. So now let's rewrite this as a system of equations. Just remember, this is our x1 coefficients, our x2, our x3 coefficients, and these are the other side of the equation. So I've got twice x1 plus 4x2 equal to 6. I've got x3 times negative 1 equal to negative 2. And then the last equation would just be 0 equal to 0, which is fine. That's a true statement. If that had been a false statement, that would mean there would be no solution to this system. But we're okay. So this tells me that x3 has to be positive 2. The first one, the problem is we can't get an individual value for the x2, but the first equation I can reduce by 2, divide by 2. I'll have x1 plus 2x2 equal to 3. Now, it's the only equation with the x2 or the x1. Since there's nothing specifically telling me what x2 has to be, I'm going to use equation 1 to say that x1 will be 3 minus the 2x2. So negative 2x2 plus 3. So as long as I pick something for x2 and x1 satisfies that equation, we're okay. And we know that x3 has to be 2. So we're not going to be able to get a unique solution here. We actually have an infinite number of solutions. I'm going to use x2 to be what we call a free variable. It can be whatever it wants to be. So just pick a value for x2. 0, 1, if x2 is 0, then one solution will be x1 equal 3, x2 equals 0, and x3 equal to 2. So a free variable just means it can have any value, and the others will have to, satisfy the conditions. So we have x1 is this, x2 can be anything, x3 is 2. So sometimes we'll use parameters. So let x2 be a parameter. We'll call it s. Sometimes they use t. Sometimes they leave it as x2. I really prefer t because s looks like a 5. So I'm going to use t even though the book probably uses s. Okay, I'm going to let x2 be 2. That means then that x1 will be minus 2t plus 3. x2 will be t, and x3 will be 2. So that's our system, and that's letting t be any value from negative infinity to infinity. So that's one way to give our solution. That's when you have an infinite number of solutions. If you wanted to just pick a few, just pick different values for the t. If you want to write it in another way, sometimes we'll write it in matrix form. So if I write the solution, I know the solution is the vector x1, x2, x3. And I know that x1 is negative 2t plus 3. x2 is t, and x3 is 2. That's one way to write it, is a matrix in that form. Or another way would be to split the t's in the constant values, and you could write it this way, as the sum of two matrices. So we have minus 2t and t, and there's no t's in the last one. And then the last one, the things without the t are 3, 0, and 2. And then they could further rewrite that as negative 2, 1, 0 times t if we wanted to factor out a t, and then plus 3, 0, 2. So that's another way. That's in matrix form. But for now, this is what we'll go with. Okay, so an infinite number of solutions. And now let's look at this equation. We've got 4 equations, 4 unknowns. I'm going to first write it as a matrix, just carrying the coefficient matrix with the constant values. So the augmented form will be this. Okay, I'm going to leave equation 1 alone. It will be the only one with an x1 remaining. I'm going to eliminate the x1s out of the others, so I'm going to take negative 2 times row 1 and add it to row 2, and that's going to eliminate this entry here. So negative 2 times this, added to this will be 0. Negative 2 times the second entry, added to this will be 0. Negative 2 times this will be negative 4, added to this one will be 0. Negative 2 times this is negative 4 plus the 3 is negative 1. And then negative 2 times this added to this is 1. I want to eliminate this entry. And I'll do it by multiplying row 1 by negative 3 and adding to row 3. So negative 3 times this added to the 3 is 0. Negative 3 times this added to this is 0. Negative 3 times this added to this will be 0. Negative 3 times this is negative 6. Added to this will be 3. And we still have the negative 3 because we'll have 0 added to the negative 3. And now I want to eliminate the 4. So we're going to take negative 4 times row 1 and add it to the row 4 to eliminate the x1 coefficient. So negative 4 here added to this will be 0. Negative 4 times this is 4, added to the negative 4 is 0. Negative 4 times this, added to the 8 is 0. Negative 4 times this, added to the 8 is 0. And negative 4 times this, added to the 0 is 0. Okay, so we've got one equation now with x1. None of them have x2. None of the others have x3. So it needs to be a different one than already has the x1. So now we just go to the x4, and we're going to use this equation to be the one that's going to have the x4 remaining. And I want to eliminate the x4 from here and here. So the last equation's already fixed. And the second equation, I'm not going to do anything with it. That will be the one I have my x4 term remaining. Okay, so now multiply row 2 by 2 and add it to row 1 if I'm trying to eliminate this. So negative, just 2 times row 2 added to row 1. So 2 times this, this, and this are all 0, so we'll just retain these values. 2 times this is negative 2, added to this will be 0. 2 times this is 2, added to 0 is 2. And now I want to eliminate the 3 down here, and I'll add a multiple of 3 times row 2 added to row 3. So 3 times each of these is 0, so we'll contain zeros here. 3 times this one's negative 3 added to that is 0. 3 times this is 3 added to that will be 0. Okay, so now, if you rewrote this as a system of equations now, keeping in mind this is x1, x2, x3, and x4 coefficients, we're going to get x1 minus x2 plus 2x3 equal to 2. Then we have minus x4 equal to 1, and then just 0 equal to 0. for the last two, which don't tell us anything, but they're true statements, so we will have solutions here. So we have an infinite number of solutions again. We know then that x4 is -1. And the first one just gives us restrictions. x2 and x3 will be our free variables. We can choose any values for those. x1, though, will have to then be x2 minus 2x3 plus 2. Okay, so now if we want to, we have two free variables here, so I'm going to assign those values of s and t. They can both be different values. So I'm going to say, okay, let's let x2 be s, and we're going to let x3 be t. We know x4 has to be -1, and we know that x1 will have to be x2, which is s, minus 2 times the x3, which is minus 2t, and then plus 2. Okay, and that's where s and t can be any values between infinity and -infinity. So if you wanted to let them both be 0, that means x1 would be 2, x2 would be 0, x3 would be 0, and x4 would be -1. That's one solution. You could pick x2 to be 1 and let x3 be 0, and you're going to get another solution. So every different value you pick for x2 and x3 gives you a new solution. So you have an infinite number of solutions, again, to this system of equations, and they have to match this form. This is the way you'd give it the solutions parametrically. Okay, a matrix is a rectangular array of numbers that's arranged in rows and columns. So an m by n matrix just means that we have m rows and n columns. Okay, so to denote a matrix, we can either write it out showing the individual entries this way, or we also use the notation A of ij inside brackets, and I then goes from 1 to n and j goes from 1 to n. So that's just a shortened way to designate the matrix A. A square matrix is one that has the same number of rows as columns. Okay, so in the examples below, this is a 3 by 3. This is a square matrix. B is a square matrix. Okay, so both of these are 3 by 3. There's 3 rows and 3 columns. Okay, X here, when it's usually just 1 row or 1 column, we call it a vector. It's a 3 by 1 matrix, or a vector with 3 entries. Okay, so a column matrix we call a vector. So it's just an n by 1 matrix. A diagonal matrix is a matrix that has only non-zero, the only non-zero entries are on the main diagonal. They could all be 0, but everything off the main diagonal is 0. So in matrix B here, this is called a diagonal matrix. This is the main diagonal. That's A11, A22, and A33 entries. So diagonal matrix, the only non-zero entries are on the main diagonal. Okay, so if you have a matrix that's all zeros, it's called the zero matrix. Okay. Usually when we refer to matrices, we usually use boldface capital letters for the matrix and lowercase letters for vectors. So matrices are the capital letters and the vectors are the little letters. I'll use boldface when I can, but it's going in and changing a lot of things to bold, so I know I'm not consistent with it. Okay, so now to sum two matrices together. First off, to sum them, they have to be the same size. So the sum of two m by n matrices will be an m by n matrix, and you add them by adding them each component. So the first row, first column entry is added to first row, first column entry of the second one. So the way you define it is A plus B is, this is just a general notation for the matrices A and B, and you just take each entry, A11 added to B11, A12 added to B12, and so on. To multiply a matrix by a scalar, so a single number, so like 3 times the matrix A, just means that you take each entry times that constant value. Okay, so take every number in that matrix by that same constant. The notation negative A, that just means -1 times the matrix A. So just take every entry in A and multiply it by -1. Okay, now properties of the matrix addition and scalar multiplication. This first property just tells us that there's a grouping property, grouping of addition. So associative property of addition just says if you want to add two of the matrices together, if you want to add all three, you can add two of them together first and then add the third one. Or you could have regrouped and added the first two and add the third one. So it's just telling you different ways you can still get the same result. Either adding, you need to add two of them first to be able to add the third one if you're trying to get the sum of all three. This also tells me that if I add two matrices together, A plus B, it's the same thing as if I'd had B first and then added A to it. A plus the zero matrix, which we denote by just a boldface 0, is going to give us just the A matrix because we're adding 0 to all the entries of A. A plus the minus A, this is that, it's called the additive inverse. So it's just a negative of all the entries of A. If you add those two matrices together, you'll get the 0 matrix. This says that if you take a constant times the sum of two matrices, if you first add the two matrices and then times the constant, you'll get the same thing as if you took the constant times A plus the constant times B and then add those together. This one says if you have a constant times a matrix, that's the same thing as if you took the product of the constants times the matrix A, or you could have taken the constant R times A and then times the S. So the order you do the scalar multiplication doesn't matter. And this just says if you have two scalars that are added together and then times A, that's the same thing as if you took each scalar individually times A and then add those together. So those are just properties dealing with the addition and scalar multiplication. Okay, so let's look at how we would do a sum. This is a 2 by 3 matrix. This is a 2 by 3, 2 rows, 3 columns. So I can add them. You have to have the same size to be able to add them. You will get a 2 by 3 when you add them. And I'll go ahead and show you the steps. I'll take row 1, column 1 entries added together. Row 2, column 2, or row 1, column 2 on each matrix added together. Row 1, column 3 added together. So that's giving me the row 1, column 3 entry. Then 4 plus 1, the 5 plus 1, and the 6 plus 1. So that gives me 2, 4, 4, 5, 6, 7. Okay, second one. This is a scalar multiplication. I want 3 times each entry. And it won't affect the size of the matrix. So I have 3 times 1, 3 times 2, 3 times 3, 3 times 4, 3 times 5, and 3 times 6. So we have 3, 6, 9, 12, 15, and 18. Okay, so that's scalar multiplication. A product of a matrix and a column vector, we've already talked about, is the column vector. It's going to give you a column vector that just has dot products of rows of A with X. Okay, so now the product is only going to be defined for two matrices if the number of columns of A matches the number of rows of B. Okay, so you're doing rows of the first matrix, dot product with the column of the columns of the second matrix. So now, in example A here, I've got a 2 by 3 matrix and I'm multiplying it by a 3 row by 1 column. The number of columns here must match the number of rows of the second one, and they do. So the middle numbers have to match to be able to multiply. The result that we get will be a matrix that's a 2 by 1. So I'm going to go ahead and draw myself a 2. It's going to have 2 rows and 1 column. Now to get that, row 1 will be row 1 from this matrix dot product with column 1. So that's going to be 1 times 1 plus 2 times 0 plus 3 times 2. Dot product, remember, is just the first entry is multiplied plus the second entry product plus the third entry product. Okay, and when I get that sum, that will be the entry in row 1, column 1, because we know we only have one column in this matrix. Okay, row 2 now. I'm going to take row 2 dot product with this column. So that's 4 times 1 plus 5 times 0 plus 6 times 2. So now the resulting product will be 1 plus 0 plus 6, so 7. 4 plus 0 plus 12 is 16. So that would be the product of those two matrices. And notice it is a 2 by 1. Okay, the next one here, I'm putting some variables in, so just make sure we understand how to do this. Check the size first. I have a 2 by 3 multiplied by a 3 by 3. So they do agree, the number of columns of the first one times the number of rows, number of columns times the number of rows matches. So we will end up with a 2 by 3 for the product. So I'm going to go ahead and 2 rows and 3 columns. So just to make sure I see exactly what size I'm going to get. So now, take row 1 and column 1. That will give you this first entry, row 1, column 1. Take its dot product. So 1 times 1 plus 0 times -1 plus 1 times 4. Now take row 1 dotted with column 2, and that's going to give me this entry, row 1, column 2. So I'm going to have 1 times 2 plus 0 times -1 plus 1 times 1. And now row 1 again times column 3. So the dot product row 1 with column 3 will give me this entry, 1 times x plus 0 times y plus 1 times z. That's row 1. So that's the row 1 result in the product. Now let's go back and look at row 2 dotted with each of the columns. Okay, so that dotted with column 1 will give me this entry. So 3 times 1 plus -1 times -1 plus 2 times 4. Now column 2 with row 2. So 3 times 2 plus -1 times -1 plus 2 times 1. And finally, row 2 with column 3. 3 times x minus 1 times y plus 2 times z. Okay, so just simplifying this, we've got 1 plus 4 is 5. We've got 3 plus 1 is 4 plus 8 is 12. 2 plus 1 is 3. -6 plus 1, so that's -5 plus 2 more is -3. And then we have x plus z and 3x minus y plus 2z. And so that would be the product of those two matrices. Okay, and before I get emails about this, let's get this corrected. I do have an error here. I just added these wrong. Whoa, I didn't mean to erase it, but now that I have. Okay, that's row 2, column 2. So that's this. Get all this cleaned up here. I have row 2, column 2, dot product. So 3 times 2 plus -1 times -1 plus 2 times 1. So that's 6 plus 1, 7 plus 2 more is 9. Okay. Okay, now here's some properties and just different ways or different things that matrices can represent. Properties of matrix multiplication is if you have 3 matrices you're trying to get the product of, you can multiply the first 2 together first, then take the product, times the C, or you can do the second 2 and then times A. The main thing is multiplying matrices is not commutative. That means you cannot turn them around. You can AB is not B times A. Okay, so you've got to keep the order that they're in the same. A sum of 2 matrices times another matrix is equivalent to each of the matrices, A times C and B times C, separate, added together. Be sure you keep them in the same order. C has to be last in both of those. In this product, this is a distributive property where the matrix A is on the left side now. A times B plus A times C. Notice the A is always first if it's over on the left side. When it was on the right, it was always the last. Now here's a product with a scalar. So if you have a scalar times A times another matrix B, that's the same thing as just taking the scalar out totally, multiplying A and B first, or taking the scalar times B and then times A. So those are just properties of matrix multiplication. Now this is giving you ways that, or things that matrices are representing. Matrices are linear operators. You'll look at this more in linear algebra class, or even a Cal 3 class essentially is doing the same thing. If A is a matrix, okay, and X and Y are just n by 1 vectors, then you can look at the product A times X as you're taking a vector. So A was m by n. You were multiplying by an m by 1 vector, which was the X. When you multiply those together, you're going to get a vector that's an m by 1 vector. Okay? When you look at it this way, this A is a transformation. It's an operator that's taking a vector X to another vector. And you can look at these as being in different spaces. You can say that this is in a vector that's in Rn, and this is a vector that's in Rm, just meaning that it has m components or n components in it. So that's looking at it as an operator. Some of the things that operators, well, one property that linear operators have is that you can add the two vectors first and then multiply by the matrix, or you can multiply each of them individually by the matrix and then add them together. So this is called a linear property. Or taking A times a scalar times X is the same thing as the scalar times the transformation of the vector X by A. So these two properties together make it linear. These are linearity properties, which you'll study more in other classes. Operators. These transformations, this matrix A, could cause a vector to be stretched or contracted. So maybe you had a vector that had length 2, and that when you multiplied it, it was going to end up with a vector that had length 1. So the matrix, the operator, the matrix looking at it as a linear operator, can stretch or contract components of a matrix. It can rotate a vector. So let's say we had a vector that was here. You can get a matrix A that when you multiply it, it rotates it around a certain angle to another vector. Okay? So you can actually get a matrix that will perform a rotation of every vector that it's multiplied by. So it'll take care of actually rotating a coordinate system like that. You can also reflect a vector through a plane. So if I wanted to reflect a vector through this line, I'm not going to draw a plane, I could take this vector and it would reflect it through here and give another vector. So reflections can be done by a matrix multiplication. So just different things that matrix multiplication can accomplish. So that's used a lot when you're dealing with computer graphics. Okay, so now another thing I want to look at is how do we look at a matrix with our linear system, which is what we're going to be doing. We're going to start with our linear system. Okay, so we've already talked about taking a linear system like this and writing in matrix notation where AX is equal to B. So B is just the vector that's made up of the values over on this side here. X is the vector of unknowns. So that'll be our solution to this system. And then A is just that constant coefficient matrix. So it's just taking all the coefficients of each of the variables X on that side. If the B's over here on the right side were all zeros, so if every one of these was 0, then we call that a homogeneous system. So if B is equal to 0, the system's homogeneous. If B's not all zeros, then it's a non-homogeneous system. Okay, now just some other terminology here. A matrix transpose is just going to be the matrix you get by interchanging the rows and columns. So that's called the transpose of A, and we denote it with a capital T raised. So if I want to find the transpose of A for this matrix, this is a 2 by 3. The transpose changes the rows to columns. So the A transpose then is going to look like it's going to be a 3 by 2. And we just make row 1 becomes column 1. and row 2 becomes column 2. Okay, so that's the transpose. Matrix identity. There is a multiplicative identity in matrix algebra. That means there's a matrix that if you multiply by it, you will always get the matrix you started with. Just like in real numbers, there's an identity called a multiplicative identity, which is the number 1. Anything times the 1 will give you the number you started with. Okay, so matrices have that same property, that there is a multiplicative identity. The identity will be the square diagonal matrix that has 1s down the main diagonal and 0s everywhere else. Now, to multiply by a matrix, though, it has to be the right size. So if I want to demonstrate the identity property for A here, where A is a 2 by 3, if I'm going to multiply A times I, I'm going to have to multiply I is going to have to be a 3 by 3 matrix. I must be a square matrix. Okay? So if it's on the right, it has to be size 3 by 3. So I'm going to show you here. 1, 2, 6, negative 1, 2, negative 1. Multiplying by the identity matrix, that means 1's down the main diagonal, 0's everywhere else. Notice I'm multiplying a 2 by 3 by a 3 by 3. I will get a 2 by 3. So we're going to take row 1 with column 1. You have 1 times 1 plus 2 times 0 plus 6 times 0. You're doing the dot product, so it's just 1. Row 1 times column 2 gives me just 2. Row 1 times column 3 gives me just 6. Row 2 times column 1 is negative 1. Times column 2 will be the 2. Times the column 3, I'm doing dot products, is negative 1. Notice we got the matrix we started with. Now what if we, though, multiplied the I on the left side of A? Well, now, because A is a 2 by 3, it can only be multiplied by a 2 by 2 square matrix. The middle numbers have to match. So this will give us a 2 by 3 again, but now we've got a 2 by 2 identity if we're going to be able to multiply it on the left side. Again, we get a 2 by 3. We'll have row 1 times column 1. So that'll be 1 times 1 plus 0 times negative 1, dot products. Row 1 times column 2. So that will be a 2. Row 1 times column 3 will be 6. Now row 2 times column 1 will be negative 1. Row 2 times column 2 will be the 2. Row 2 times column 3 will be negative 1. And notice we get A again. So that's the identity matrix. Just make sure it's the size that you need. In this case, it was a 2 by 2. Up here, it was a 3 by 3 because we needed that size to multiply on the left or the right. Okay, now matrix inverses. I think I'll make this a separate, it's a little bit longer. Okay, so we're going through properties that matrices have that are similar to the properties that the real numbers had. So if you remember real numbers, they had an additive identity. So that meant if you took any real number and added 0 to it, you always got the number you started with. This was called the additive identity. And matrices have 0, which is it. The 0 matrix is the additive identity. They also had inverses, additive inverses. So any number had a negative, which was called the additive inverse, that would give you the 0, the additive identity. Well, you also had multiplicative identities. So with real numbers, take any number times the number 1, and that gives you the number you started with. So it's the number you'd multiply by that would always give you what you started with. So this is called the multiplicative identity. And so we have that in matrices as well. That's just the identity matrix that has 1 down the diagonals and a 0 everywhere else. And then the last one is the inverse. A multiplicative inverse is what would you multiply by to give you the 1, the additive identity. the multiplicative identity. And so with real numbers, that we called that the reciprocal. So this was the multiplicative inverse. So it's using multiplication to come up with the identity. So now in matrices, we have those same ideas, except not all matrices will have multiplicative inverses. So a matrix, some square matrices can be paired up with other square matrices to have the property B times A is the identity. Now this identity is the matrix that has ones down the main diagonal and zeros everywhere else. So to have an inverse, the multiplicative inverse, we have to be working with a square matrix, and the inverse then will be a square matrix as well if it exists. So if B times A is the identity, it's going to happen that A times B is also going to be the identity. So we will have that commutative property of multiplication if there's an inverse that satisfies that first matrix. Plus, if there's a B so that B times A is I, then it will be a unique matrix that has that property. So that B will be the only matrix that times A would give us that identity matrix. Okay, so when that happens, then we say that B is the inverse of A. So when a matrix does not have an inverse, we call it a singular matrix. And you'll see that on your calculators sometimes when you're dealing with matrices. It'll say singular, meaning it doesn't have an inverse. Okay, so when there is an inverse, and we're trying to solve a system of the form AX equal to B, so when the inverse exists, what we're going to do is we're going to multiply both sides of that equation by the inverse on the same side. So A inverse times AX, so I'm doing A inverse on the left of both sides, will be A inverse times B. You have to be very careful about where you place it because the multiplication's not commutative. You can't just switch the order in multiplication. So when you have A inverse times the AX equal to A inverse times the B, so this is only when the inverse exists, then we can regroup using one of our properties of multiplication and do A inverse times A first times the X. And remember, A inverse times A is just the identity. So that means that the vector X is just going to be A inverse times the B. So if A has an inverse, X will have a unique value, and we can compute it by just taking the inverse of A times the vector B. So that in that case, we will have a unique solution to the system. Okay, so now, multiplicative inverses when you have a 2 by 2 matrix. You learned this probably back in college algebra, and I just want to remind you of this. If this is your matrix A, you can get the inverse by rearranging and swapping out the signs. So if A is the entry here, and then A, B, C, D, you're going to put A down in this corner, D here, so you're swapping the entries down the main diagonal, and then you keep the ones down this off diagonal, but make them opposite signs. Okay? And then you have to take that matrix that you just formed and divide by AD minus BC, and we'll get to that in a minute. This is called the determinant of the matrix, AD minus BC. It's this product minus this product. Okay, so that's how you find the inverse. 1 over the determinant, AD minus BC, and then times the new matrix you formed by swapping the A and the D, changing the signs of the B and the C. Okay, so A will be invertible only if this AD minus BC is not 0. If it is 0, then you do not have the multiplicative inverse for A. Okay, so let's find the inverse of this 2 by 2. So we've got a 2 by 2 here. The first thing I'm going to do is I'm going to compute AD minus BC, which is this product minus this product. So 2 times 1 minus 1 times 4. So the inverse, or the determinant, is -2. Okay, so now the inverse, we know the inverse exists since the determinant is not 0. So A inverse then will be 1 over -2 times, swap the A and the D, so I'm going to put 1 here and 2 here, change the signs of the other two numbers, the B and the C values, and now I can take this scalar multiplied through by the matrix. So we're going to have -1/2. I'm just taking -1/2 times each entry. -1/2 times -4 is 2. -1/2 times -1 is +1/2. And -1/2 times 2 is -1. Okay, so there's your inverse of the matrix A. Okay, so now, if I want to solve AX equal to B, I know, since the inverse exists, I know that X is just going to be A inverse times B. And then B is the vector 1, 2. So now just taking row 1 times column 1, it's negative 1/2 times 1 plus 2 times 2. And then 1/2 times 1 plus negative 1 times 2. So that's going to give me 7/2 and negative 3/2. And so that would be the solution to the system AX equal to B. So if you want to see what that system looked like, it's 2, 4, 1, 1 times x, x1, x2, or xy equal to the vector 1, 2. So multiplying out the left side, we would have 2x plus 4y equal to 1, x plus y equal to 2. And what we just found is that 7/2 negative 3/2 is the solution. So if I put 7/2 here for the x minus 3/2 for the y, I do get the 2 here. So just verify it in the second equation and it does work. Okay, so now let's look at a larger matrix. Finding the inverse of something larger than a 2 by 2 requires some row operations. Now the row operations are exactly what we used when we were doing the Gauss-Jordan elimination earlier. We could interchange two rows. You know, that's just essentially changing the order of two equations in a system. We could multiply a row of a matrix by a scalar. That's like dividing an equation both sides by a number. Or we could add a scalar multiple of one row to the other. You know, we took like 2 times row 2 added to row 1. We were doing those operations, that elimination, to get rid of some of the variables. So these are what are called row operations. If we perform those operations on a matrix, we're going to be able to find its inverse. So what we do is we're going to start with an n by n matrix A. We can find A inverse, if it exists, by doing row operations on the n by 2n matrix that you form by taking A and the identity side by side. Okay? So when you do that and do row operations so that we transform this to the identity, you're going to now have a matrix of this form where the identity is the first 3 rows and 3 columns, and then you'll have another matrix after that. This matrix B will be the inverse of A. Okay, so let's demonstrate that. I'm going to set up A. And then the identity following. So it's got to be the same size as A is. Now do the row operations, and we say these are row equivalent matrices. If you want to put a bar down the middle, you can make it look like an augmented matrix. I'm going to transform the first 3 rows and columns to the identity. It's the same thing as the Gauss elimination. We want to make this the only entry with a number in it. So I'm going to keep that row the way it is. And then I'm going to use that row to eliminate the first entries, you know, the x1 coefficients in the other 2 rows. So I'm going to do -1. This new second row will be -1 times row 1 added to row 2. So -1 times row 1 added to row 2 will be 0. -1 times row 1 added to row 2 will be 1. -1 times this one added to 2 will be 1. -1 times this one added to 0 is -1. -1 times this added to that. -1 times that added to the row 2. Now I want to eliminate this. So I'll do -1 times row 1 added to row 3. So again, -1 times everything up here, or on the second matrix, added to row 3. So -1 times this one added to this will be 0. -1 times this one added to this one will be -2. -1 times this one added to this one. -1 times this one added to this one. -1 times this one added to 0. -1 times this one added to this one. Okay, so we've got our first column that is the identity. So now let's do the second column. We want a 1 here. Now if we can't get it in this form, that means there's no inverse. So if you end up where one of them, the second or third rows don't have that second value, you're not going to be able to make it look like the identity. So that would mean that you don't have an inverse for that matrix. Okay, so now I'm going to leave row 2 alone, and I'm going to eliminate the entry from column 2 from the other two. So let's eliminate this 2, and we'll do that by multiplying row 2 by 2 and adding to row 3. So 2 times row 2 plus row 3. Okay, so 2 times 0 added to the 0, 2 times the 1 added to the negative 2, 2 times the 1 is 2 added to the 0, 2 times the negative 1, negative 2 plus negative 1, 2 times the 1 add to the 0, 2 times 0 add to the 1. Okay, now I want to eliminate this 2 up here. So I'll do negative 2 times row 2 added to row 1. So negative 2 times 0 added to that is 1. Negative 2 times 1 added to the 2 will be 0. Negative 2 times the 1, negative 2, added to the 1 is negative 1. Negative 2 times this will be 2 added to the 1 is 3. Negative 2 and 0. Okay, so now we've got 2 columns right. So now we want to come to the third column, and we need a 1 here. We've got to get the identity. So that means a 1 has to go there, and so we'll get that by dividing the whole third row by 2. So now we're just using property B up here. So I'm just writing the third row down, dividing everything through by 2. And now I need to eliminate the other entries here and here. Okay, so I want to eliminate the 1 here, and I can do that by multiplying this row by negative 1. So negative 1 times this new row 3 added to the old row 2. Well, that's going to be this one. That's giving me the new row 2. Whatever I'm adding it to is where I replace it. Okay, so negative 1 times row 3. So these two are 0, so they're not going to affect the first 2 entries. Negative 1 times the 1 added to this will make that one 0. Negative 1 times this one will be 3/2 added to the negative 1 will be positive 1/2. Negative 1 times this is negative 1 added to the 1 is 0. And negative 1/2 added to the 0 is negative 1/2. Okay, the last thing now is to eliminate the negative 1 here. And I do that by just adding the row 3. So I'm going to have 1 times row 3 added to row 1 to get the new. So take this row 3 and the old row 1 and replace the new row 1. So adding them, I'll get 1, 0, 0. And then negative 3/2 plus 3, so that's going to be a 3/2. 1 and negative 2 is negative 1, and then 1/2 and 0. And so now once we get it in this form, this is the inverse. So A inverse for this matrix A is 3/2, negative 1, 1/2, 1/2, 0, negative 1/2, minus 3/2, 1, 1/2. And if you want to verify it, just take A inverse times the matrix A that you started with, and you better come up with the identity matrix. Or A times A inverse will also be the identity matrix. Okay, now let's look at a determinant of a 2 by 2 matrix. We're going to use this to determine whether or not a matrix is invertible or not, or has an inverse. Okay, so if you have a 2 by 2 matrix A, the determinant, we'll use the notation either DET of A, or you put vertical bars around the matrix A that represents that you want the determinant of the matrix. It's defined to be the product of the main diagonals minus the product of the off diagonals. So A11 times A22 minus A12 times A21. Now that's just for a 2 by 2 matrix. Now, if you have larger than that, then the determinant then is done by doing a cofactor expansion on a row or a column. So now, if we expanded on the first row, that means we're taking these entries, A11, A12, A13, and we're going to multiply those by the cofactor of those entries. So A11, you mark out the row and column containing A11, and that gives you the 2 by 2 whose determinant would be multiplied by A11. Then when you get to A12, you're going to take that entry, mark out its row and column, and take the 4 numbers remaining, and that's where you get this matrix, A21, A23, A31, A33. And then similarly, you do look at the A13 entry, which is this one, mark its row and column out, and take the 2 by 2 that results from that. Now, those are the cofactors for those entries, but you also have to consider a negative sign with each entry. The negative applies to the sum of the positions. So for this first term, we're going to have a -1 times 1 plus 1, because this was entry row 1, column 1. This A12 will have a -1 times to the 1 plus 2 power. So that's why it ends up with a negative in front. The A13 would be multiplied -1 to the 1 plus 3. So that's part of that cofactor expansion. So you'll take the entries in the row, multiply by the proper sign depending on the position of that entry, and then get the matrix that results by marking out the row and the column. So that's the determinant of a 3 by 3, and if you had a larger matrix, you would just end up with 3 by 3s for each of these when you actually marked out rows and columns, and you'd have to break those down even further, so it'd be kind of tedious. So let's find the determinants here. I've got a 2 by 2, so it's just the product of the main diagonals, 2 times 1 minus the 1 times the 4. So we've done this before. It comes out to be a -2. That means that the inverse of that matrix does exist. The next one, let's expand on the first row. That means I'm taking 1 times the determinant, 2 times the determinant, and then 1 times the determinant. So I'm taking the 3 entries on that first row. Then I need to affix the sign. Since this is row 1, column 1, this is going to be -1 to the 1 plus 1, so positive. Row 1, column 2, -1 to the 1 plus 2, so this is going to be negative. And then this one's row 1, column 3, so this one's going to be positive, since it's -1 to the 4th power. So the signs will always be alternating when you expand on a row or column. Just make sure you start with the right sign. Like if we were using row 2, we would have 0, 3, and 5 for the numbers, but this is row 2, column 1, so that would start negative and then positive, negative. Okay, so now when I mark out, I'm looking at the entries on the first row. I mark out the row and the column, so I'm going to have a 3, 5, 1, -1. The 2, I'm going to have a 0, 5, 2, -1. And then the 1 here, mark out its row and column, and I end up with a 0, 3, 2, 1 remaining. And now we just have to evaluate those 2 by 2s to get the determinant. So I've got 1 times -3 minus 5, minus 2 times 0 minus 10, and then plus 1 times 0 minus 6. So I've got 1 times -8, minus 2 times -10, so plus 20, and then I've got minus 6. So -14 plus 20 would be 6. So because that's not 0, this is the determinant of the matrix A in part B. Because it's not 0, we know that that matrix does have an inverse. Okay, so now some relationships to a system of equations, a linear system we've been talking about off and on. If A is an n by n matrix, then these statements are all equivalent. A will be singular, meaning it does not have an inverse. That's equivalent to the determinant being 0, which we've already discussed that. A matrix won't have an inverse if the determinant is 0. But that's also equivalent to the matrix equation AX equal to 0, that homogeneous equation where the right side's always zeros, that will have a non-trivial solution. That means you won't have the only solution being all zeros for the x, because we know that's always a solution. If you put 0 for the x, a times 0 will always be 0. But if it's a singular matrix, meaning the determinant was 0, there will be a non-zero vector solution to this system of equations. The columns of A also form a linearly dependent set. So what does linearly dependent mean? Well, the columns of a matrix are linearly dependent if they're scalars, just constant values, not all zeros, so that if you take a constant times each column, you can come up with 0 by combining those. Now, we know that if C1, C2, up to Cn are all 0, that will be true. But there has to be a solution where they're not all 0 that make that true. Okay? What that's essentially saying is that one of the columns can be written as a combination, as a sum or product or sum or difference of other columns or multiples of other columns. So it's kind of a redundant. It's not expanding the set of vectors, in other words. So, okay. So that's what we mean by linearly dependent. And I'll look at an example of that in a minute. If A is singular, meaning the determinant 0, then we know that A times X has an infinite number of solutions. Okay? So not only it doesn't have a trivial solution, but it'll have an infinite number of solutions. If A is singular, then this equation, AX equal B, also either has no solutions to it, the system will have no solutions, or it's going to have an infinite number of solutions. Okay, that's only if the A is singular, if it has no inverse. Okay, now the solutions will be of the form, when we do have a solution to this matrix A, the matrix equation AX equal B, the solutions will be of the form X equal a particular solution, X sub P, that's a particular solution that makes AX equal B true, and then plus X sub H, where X sub H is the infinite number of solutions to AX equal to 0, that homogeneous solution system. Okay, so that's very similar to when we were solving equations previously using the method of undetermined coefficients. Okay, so now we saw previously when you had this matrix A times X equal to 8, 6, minus 10, we saw that the solution came out to be x1 equal to 3 minus 2, I used t, 3 minus 2t, x2 was t, and x3 was 2. That was the solution that we got back in the previous section. I want to write that solution in matrix notation. The matrix notation is looking at the vector x1, x2, x3. x1 we know is negative 2s minus plus 3. I'm just rearranging the order. x2 was s, and s3 was 2. I did this previously, but I'm splitting it up so that all the things with s are in one vector, and the constants without the s are in the other. So if there isn't a term like that, I put 0 in its place. So this is minus 2 s0, or 1, 0, times the vector s plus 3, 0, 2. Okay, this is our particular solution. This is our solution to the homogeneous system that's an infinite number of solutions. Okay, verify the determinant is 0. Well, let's find the determinant of that matrix A. Remember, if you have an infinite number of solutions, then that meant that the matrix was singular or had the determinant of 0. So let's look at the determinant of this matrix. The determinant of A, I'm going to expand on row 1. So it's going to be 2 times the determinant minus 4 times another determinant plus 1 times the determinant. So let's fill those in. If I mark out the 2's row in column, I get 4, 0, negative 8, 1. If I multiply eliminate the row and column containing the 4, I get 2, 0, negative 4, 1. And if I mark out the row and column containing the 1 in that first row, I get 2, 4, negative 4, negative 8. So this gives me 2 times 4 minus 4 times 2, that's the determinant, plus 1 times negative 16 plus 16. So that'll be 8 minus 8 is equal to 0. So the determinant is 0, which is why we end up with this infinite number of solutions here for the homogeneous equation. I want to give an identity that shows the linear dependence of the columns. Okay, so what we meant by the dependence is that there was numbers times each of the vectors. Now I'm looking at each of the vectors in the columns. Okay, C1 plus C2 times the second column plus C3 times the third column. If that's 0, if the columns are linearly dependent, that means that there's a C1, C2, and C3 that are not all 0, making that true. Because we know if they were all 0, we would make that have a true statement there. So we need to find the solutions to that. Now we could do this the long way, which would be looking at this as a system of equations. If you rewrote this as, if you multiply through by C1, C2, and C3, and then combine the matrices, the 3 vectors on the left side, this is equivalent to 2C1 plus 4C2 plus C3 equal to 0, 2C1 plus 4C2 plus 0C3 equal to 0, and minus 4C1 minus 8C2 plus C3 equal to 0. I could solve that system using methods that we've done, the Gauss-Jordan elimination or just elimination. Okay, but this one's a pretty simple one, and if I notice that this column is just half of this column, that means that if I chose this constant to be negative 2 and this constant to be 1, those two added together will be 0, so then I can just choose C3 to be 0. So use these values for the constants. Negative 2 times column 1 plus 1 times column 2 plus 0 times column 3. You will get all 0, and these were not all 0 constants. So that means that the columns are linearly independent. Linearly dependent, which is equivalent to saying that the determinant is 0 and saying that the matrix is singular. Okay, so now, if A is a non-singular square matrix, that means that the determinant's not 0, then AX equals 0 has X equals 0 as its only solution. And that means then that there will also be a unique solution to this equation, because you just multiply both sides by A inverse, and this will be the unique solution. So that's if A is a non-singular square matrix. If A is singular, we don't have that unique solution. We either have no solutions or we have an infinite number of solutions. Now let's look at calculus involving matrices. If we let the entries in a matrix A be functions of the variable t, then we're going to denote it as A of t, and we call it a matrix function of t. Likewise, we could have a vector with entries that were functions of t, and we would call that x of t, and that would be called a vector function of t. Now, a matrix is said to be continuous if each of the entries is continuous at a certain value. A will be differentiable at a certain value if each entry has a derivative at that value. Okay, so if we want to find the derivative of a matrix at a certain value, first find the derivative of the matrix. So the derivative of A of t, which is just taking the derivative of each of the entries individually. And so you could write that as A of ij of t prime, and then evaluate it each at t naught. So the derivative of A at t naught would be the derivative. So you're just evaluating each of the entries at t naught. Okay, likewise, An integral, finding the antiderivative, would just be finding the antiderivative of each entry separately. So that's what we mean by finding the antiderivative or integral of a matrix. Just do each entry separately, and you'll get then a matrix of the same size with, just antiderivatives in each entry. So if a of t is given by this function, a prime of t then is just finding the derivative of each entry. So first entry here has a derivative of 2t. The second entry is negative sine of t. The third entry here is just e to the t. And the fourth entry has a derivative of 0. So that would be the matrix A prime of t. And if you wanted to evaluate it for a certain value of t, you just plug in that value. So let's say A prime of 0 then would be 2 times 0 minus sine of 0, so that'll be 0, e to the 0, which is 1, and then just 0. So that's just evaluating and letting t equal to 0 in each entry. Okay, the integral of a of t, we're integrating, and then we're going to evaluate from 0 to 1, of t squared plus 1, cosine of t, e to the t, and 1. Okay, so let's first integrate each term. So this will be t cubed over 3 plus t, sine of t, that's the antiderivative of cosine t, e to the t, and then t. Now we don't need to put constants because we're going to evaluate this. This is a matrix, and we're going to evaluate that then from 0 to 1. So do that for each entry. So plug 1 into the first entry. So we'll have 1/3 plus 1 minus what we get by plugging 0 in. And then we'll have sine of 1 minus sine of 0. Then we'll have e to the 1 minus e to the 0. And then we'll have 1 minus 0. So I'm just evaluating at each limit and subtracting. Okay, so we have 4/3. E to the 1 is just e, and then e to the 0 is 1. Sine of 1, we'll just leave it as sine of 1. It's some decimal value. That's 1 radian. Sine of 0 is 0, so this part is 0. And then 1. Okay? So that would be the integral of that function, of that matrix. Okay, so now just some of the rules for differentiation for matrix equations. If you want the derivative of a product, it's just, now C is a constant matrix. It's something we're going to be working with later. So if you have a constant matrix times A, which might have functions of t, you would just take that constant matrix times the derivative of that matrix A. If you have the derivative of two matrices added together, just take the derivative of each separately and add it. If you have the derivative of a product, there's a product rule. It's the first matrix times the derivative of the second plus the derivative of the first times the second. So that would be the different differentiation rules when you're dealing with matrices. Okay, now just working with a differential equation again, we want to show that this is a solution to this matrix differential equation. Now, x here, there's an x1 and x2, so you see there's two entries in this vector x. So we have x1 is cosine of wt, and x2 is the sine of wt, or it's actually omega. But this would be two equations of the form x1 prime equal to a, well, I'd need to multiply those out. I'll show you the matrix, the system of equations. So x1, x1 prime, x2 prime. That's what x prime means. The matrix A, 0 minus omega, omega, and 0. And then times x. X is the matrix of unknowns, x1 and x2. So this is equivalent to seeing the system. Now if I do the matrix multiplication, first row times the first column, so do the dot products, this is going to be minus omega x2, and then x2 prime will be omega times x1. Okay, so that's the system of differential equations that we're working with here. So now I want to show that that really is a solution. So x prime would be the matrix containing the derivative of cosine of omega t will be omega times negative sine of omega t. So minus omega. You're on my keyboard. Sorry, my cat walked across the keyboard and put some stray letters here. Okay, x prime will be minus omega sine of omega t. And then the derivative of sine of omega t would be omega times cosine of omega t. So that's x prime. We want to show that x prime is a times x. So we're going to show that this x will be cosine of omega t, sine of omega t. So all I did was I filled in, this is the x that I was given here. This is the x prime, and here's the matrix A. Okay, so multiplying the right side out, we've got two matrices. First row times the first column, that's minus omega sine omega t. Second row, and then the column would be omega cosine of omega t. And you see that that is equal to this. So that is a solution to that system of equations given by this form. A system of n linear differential equations is said to be normal form if it can be expressed in this way. And you have the x prime solved for in each equation for each of the dependent variables. Now in this case, the x is your vector of solutions. The f, well, this should be x of n. The f is the numbers or anything that doesn't have the variables x1 to xn with them. And the a sub t are the coefficients of the x values, the x1 to xn. Okay, so the system's said to be homogeneous if the f's here are all 0, otherwise it's non-homogeneous. When the elements of A are all constants, the system's said to have constant coefficients. Okay, so now an initial value problem is just going to be a system where we're looking for that vector solution, the x, that satisfies that differential equation. Okay, and we want it not only to satisfy the differential equation, but we also want it to satisfy an initial condition so that x at some specific value for x, at x of t naught, is some initial value, where t is just something that's in that interval I, and x naught's that value of that vector at that value. Okay, so now let's suppose that A and F are continuous, and there's some t naught. Then for any choice of the initial vector x naught, there will be a unique solution to the initial value problem here. So this is just telling us when there is a solution and that it will be unique. Okay. Linear dependence again of these vector, we're looking at vector solutions now. These vector functions that are the solutions to these differential equations. The m vector functions, x1 to xm, is said to be linearly dependent if there exist constants, not all zeros, so that this is true. Okay, so this is just the same thing as when we were looking at the linear dependence of the column vectors of a matrix before. If the vectors are not linearly dependent, then we say that they're linearly independent. And that means that the only way that you can get this linear combination to be 0 is if all the c's are 0. So that means that the solutions would be linearly independent. So our goal here is to find linearly independent solutions. When we were solving second order differential equations earlier, we knew we needed to have two solutions to that to get all the possible solutions. So that's the idea here, is figuring out how many independent solutions do we need to know that we have all of them, so that we'll know that we have a complete general solution. So I want to show that these vector functions are linearly dependent. Okay, so if they're linearly dependent, that means that there has to be constants where all of them aren't 0 that make that true. So if we take some multiple of x1 plus some multiple of x2 plus some multiple of x3, we should get 0 if they're dependent. Well, we can see that x1 and x2 are just multiples of each other. So if I take -3 times the x1 plus just 1 times the x2 plus 0 times the x3, I will just get the 0 vector. Okay, so that shows that they are linearly dependent because these are constants, C1, C2, and C3 that aren't all 0 that make that true. Now I want to show that these vector functions are linearly independent. Okay, so that means if I take some C1 times the first vector plus C2 times the second vector plus C3 times the third vector the only way I can get that to be all zeros is if the C's are 0. So let's find that out. Okay, so we're trying to show that C1, C2, and C3 have to be 0 for this to be true. So let's rewrite it as a system of equations. I'm multiplying the first vector by C1. So I'm going to have C1 e to the 2t plus C2 e to the 2t. I'm just multiplying each vector by the constant in front and then adding the 3 vectors together. And that has to be equal to 0. The second one will be 0 plus C2 e to the 2t plus 2 C3 e to the t has to be 0. And then we have C1 e to the 2t plus C2 minus C2 e to the 2t. Okay, so we're looking for solutions to this. Now to be able to work with this, I need to have something that doesn't have all these functions of e, exponential functions in it. So what I'm going to do is I'm going to choose a specific t value. So let's just let t equal to 0 and look at it in that one place. So when t is equal to 0, this becomes all the e to the 0 powers are 1. So this becomes C1 plus C2 plus C3 equal to 0. C2 plus 2C3 equal to 0. And C1 minus C2 plus C3 equal to 0. So now we need to solve that system and see if there are a set of values for C. They would all have to be 0 for these to be linearly independent. Now we have a couple choices. We can either look at the matrix, we can solve the system. We can do it like we did with the Gauss-Jordan elimination before, or we can actually look at the determinant, because if these are linearly independent, that would mean that the determinant has to be non-zero. So let's just find the determinant of that matrix. Okay, so the matrix would be 1, 1, 1, 0, 1, 2, 1, negative 1, 1. Because we're trying to solve for C1, C2, and C3. So we can rewrite it like this. Okay, so the determinant of this matrix I'm going to expand on row 1, 1 times the matrix I get by marking out the row and column containing that first one, so it would be 1, 2, negative 1, 1, minus the 1 that's in row 1, column 2, and the matrix that I get by marking its row and column out are these, and then plus 1 times, and now 0, 1, 1, negative 1. Okay, so now we have 1 times 1 minus negative 2, minus 1 times negative 2, plus 1 times negative 1. So that'd be 3 plus 2 minus 1 is 4. So it's not 0. Determinant not being 0 means that A has an inverse. And if you look back in the last section, one of the equivalences to A having an inverse, meaning it's non-singular, was that the columns were, if it was singular, that meant that the columns were dependent. So if the columns are not independent, that means that it's not singular, so it has an inverse. So that means that the columns of this matrix are linearly independent. So the only values for C then here, well, the values for C are going to have to all be zeros. If If this is invertible, remember to solve for the C's, we just take the A inverse times the vector on the other side. So the vector C1, C2, C3, if this is invertible, there will be a unique solution. You just multiply both sides by the inverse of it, and this product will have to be all zeros. Okay. Okay, so now what we're trying to get to again is to find out if we have all the solutions to these differential equations. A set of vectors, each having n components, is linearly independent on an interval if we can find one point where the determinant is not zero. This determinant we call the Wronskian. We've dealt with this before. So all we're doing is we're putting the vectors that are our solutions. Now they use this to mean it's a column vector with these entries. So we just put these entries in column 1, these entries in column 2, and so on. This is called the Wronskian. If the determinant is not zero for some value, then we would say that they were linearly independent. Okay, so now we have x1 to xn or n linearly independent solutions to the homogeneous equation. Okay, then that means every solution can be written in this form, a linear combination of those linearly independent solutions. Okay, if you have a set of solutions that are linearly independent, we call it a fundamental solution set. Now that's if you have n solutions to when you have the n different equations. So it's a fundamental solution set if it has the right number of functions in the set and they're all linearly independent. Okay, so now the linear combination here would be that general solution. So now if we formed a matrix, we're going to call this matrix the fundamental matrix for the system. We're going to take the solutions. So take the solution x1 here and put the entries in column 1. Take this vector solution, put the entries in column 2. This is just forming the same matrix that we used in the Wronskian. So we know that the columns will be linearly independent. So this is called the fundamental matrix for the differential equation up here. I want to verify that this is a fundamental solution set for this system. Okay, so to do that, I first need to show that they are solutions. So here's the differential equation. Let's check each one of these. X prime for this variable would be 2e to the 2t, 2e to the 2t, 2e to the 2t, taking the derivative of each entry separately. And then we've got the matrix. And then we're multiplying by the x that we started with. Now, if you multiply these out, you're going to get first row times the column will be e to the 2t, e to the 2t. So that's 2e to the 2t. Row 2 by that matrix vector would be e to the 2t plus an e to the 2t. So 2e to the 2t. And likewise the third one. So we do see that you get that is a solution, and we can verify the others as well. So let's see, the derivative would be positive e to the minus t, 0 minus e to the minus t, and that's supposed to equal to this times the original vector. Okay, multiplying the right side out, we're going to get 0 minus or plus e to the minus t. Then we have minus e to the minus t plus e to the minus t. And then we have minus e to the minus t plus 0, so minus e to the minus t. So that one also checks. And then the third one, the derivative will be 0 minus e to the minus t, e to the minus t. Showing all of them make it true. Okay, so the right side multiplying out will be e to the minus t minus e to the minus t, then 0 minus e to the minus t, and then 0 plus e to the minus t. And that does equal to that. So all three of them are solutions. So now that we just need to know that they're linearly independent, which I believe this is what we already showed previously. Okay, no, we didn't. That was different. Those are different values. So to show they're linearly independent, we need to find the Wronskian. So the Wronskian will end up being, I just put the entries in each column. Okay, so it's the determinant of this matrix, which I'm going to expand on row 1. So that's going to be e to the 2t times the determinant and then minus a negative e to the minus t Okay, so that comes out to be e to the 2t times negative e to the minus 2t, then plus e to the minus t, minus e to the t. E to the 2t times e to the minus t is e to the t, and then minus e to the t. So we've got minus e to the 0, multiplying these two together. This is just minus 2e to the t. So we multiply that together, we're going to get minus 2e to the 0 again, which comes out to be a negative 3. Okay, so that's definitely not 0. So the Wronskian's not 0 means that the columns are linearly independent. So if those are linearly independent vectors and we have n of them, they do form a fundamental set of solutions. So now the fundamental matrix for the system. Well, this is the fundamental matrix for the system. It is just the value, the matrix inside that Wronskian. So we would call it x of t equal Okay, so there's your fundamental matrix. And now if you want the general solution, well, we found 3 linearly independent solutions, and we know we have 3 equations, so we have all of our solutions. So our general solution will be x equal C1 times column 1 plus C2 times column 2 plus C3 times column 3. Okay, so that's our general set of solutions. So any solution can be written in this form. Okay, so now the steps for how are you going to find these solutions. If x sub p is a particular solution to this system, okay, then we know that and we know that these x's are the fundamental solution set on, for the homogeneous solution. Then we know that this is what the general solution is going to look like. Take the linear combination of the fundamental set plus the particular solution here, and that gives you that general solution. Every solution can be written in that form when it's a non-homogeneous system. Okay, so the approach for solving these normal equations will be, first, find the general solution. We're trying to find the general solution to this differential equation. Find the fundamental solution set for the homogeneous system. So you're looking for n linearly independent solutions to the homogeneous system. Once you get that, take the linear combination. That's the general solution. That's your x sub h. Okay, that's your solution, general solution to the homogeneous system. Then you're going to find you're trying to find the solution to this, which is the non-homogeneous system. You're going to find a particular solution to the non-homogeneous system, and then you're going to add that particular solution to the solution to the non-homogeneous system. So whatever you found up there. Okay, so that's going to be the procedure that we're going to be using to solve these homogeneous and non-homogeneous differential equations systems. Okay, now we're going to look at a linear system that's homogeneous and of the form x prime equal to a times x. Recall our x is just a vector that has all the dependent variables that we're trying to solve for. Okay, so now when we solved this type of equation previously, we knew that the form of the solution was x equal to some constant times e to the RT. And so to represent a constant then, so some C1, to represent the whole vector of solutions, we're going to have the solutions of the form some constant vector times that e to the RT. Okay, so now if this is a solution to this equation, that means if we plug in that solution into the equation, we'll get a true statement. So now if x is equal to some constant vector u times e to the RT, x prime then would be that constant vector times r e to the RT. We're taking the derivative with respect to t. So now substituting into the left side, we have u times r e to the RT equal to a, which is just the matrix, and then x, which is u e to the RT. Now that's equivalent to this, which is equivalent, let's see, if I take out the e to the RT, I have au minus ur equal to 0. Well, the r, let's see, take that out as well. We've got e to the RT times a minus r. Now, a is an n by n matrix. R is just a constant value. So I'm going to rewrite the r as r times I so that we have compatible matrices. Both of them would be the n by n. And so r times I will be the identity matrix, but with r's down the main diagonal instead of just ones. Okay, so now for this equation to be equal to 0, for the equation to be true, I know that e to the RT cannot be 0. It's never 0. So that means that a minus Ri times u would have to be 0. Okay, so now I'm going to look at two cases here. If a minus Ri is invertible, has an inverse, then we could multiply both sides of the equation by the inverse of that matrix, and that'll leave us with u having to be 0. Well, obviously, the variable x up here is always a solution. We really don't want to consider that solution. So if u were the 0 vector, then x would be equal to 0. So we're going to assume that the u is not equal to 0. So that would mean the only way that could happen is if a minus Ri has no inverse. Okay, so now when does a matrix not have an inverse? That's when the determinant of the matrix is equal to 0. Okay, so it's equivalent then to say that the solution is of the form x equal to a constant vector times e to the RT, and the determinant of a minus Ri being 0. So those are equivalent statements. So if we're trying to find the r values that make this a true statement, we'll need the r values and the u's that are solutions, make that a solution, then it's going to be the same as trying to find the r's that make this determinant equal to 0. Okay, so now let's define some terms here. A is a matrix that's an n by n constant matrix, which is our A in this problem. The eigenvalues of A are those real or complex numbers R, so that A minus Ri times u is equal to 0. So those are eigenvalues. It'll be whatever the values of R come out to be. Now, we're assuming that you have at least one non-trivial solution. Otherwise, it wouldn't be, we just have an invertible matrix. So the values for u then that correspond to the r's that we found are called eigenvectors. Okay, so we're trying to find the solutions to this equation. We know they're of this form, x equal to u e to the rt. The values r are our eigenvalues, and then once we get an eigenvalue, we have to find the u, the eigenvector that goes with it, that makes that a solution. Okay, and so those are going to be the things that make this, if you go back and look at this again, this is equivalent to a times u equal to r times u. So we're looking for the eigenvalues, r, so that the matrix A times a u is equal to just some constant times the u. So this is our eigenvalue. And then the vectors that make this statement true will be eigenvectors. Okay, so that's how we're going to get our solutions. Find the eigenvalues, find the eigenvector for each eigenvalue, and then we'll have a solution to the equation. Then we just need to make sure we get all the possible solutions so that we can combine those to get our general solution. Okay, so finding eigenvalues of a matrix A is equivalent to finding the zeros of the polynomial determinant of A minus Ri. Okay, this polynomial, this will end up being a polynomial in R. R will be the independent variable. That's called the characteristic polynomial. Okay, so this will be the characteristic polynomial. The equation here, setting the determinant equal to 0, is called the characteristic equation. Okay, so let's do an example. I want to find the eigenvalues and eigenvectors for this matrix. Okay, eigenvalues are the r's that make the determinant of A minus Ri equal to 0. Okay, so now we have A, so I'm going to form the matrix A minus R times I. Well, that's just going to be the A. R times I will be the identity matrix times R, so it's just going to be R down the main diagonal and zeros everywhere else. So that'll be 2 minus R, minus 3 minus 0, 1 minus 0, and then minus 2 minus R. Okay, so the determinant of A minus Ri is just going to be the determinant of 2 minus R, minus 3, 1, minus 2 minus R. And I want that to be equal to 0. So this will be our characteristic equation. Okay, so let's find the determinant. So 2 by 2, so we just do the AD minus BC. So that's 2 minus R times minus 2 minus R minus 1 times negative 3. So we have 0 equal negative 4, just FOILing it out, minus 2R plus 2R plus R squared plus 3. So that comes out to be R squared minus 1. So that means R plus 1, R minus 1 are factors. Okay, this is our characteristic equation. Our characteristic polynomial is the R squared minus 1. And that's the characteristic equation. Okay, so we found our eigenvalues now. Our eigenvalues are R equal 1 and R equal negative 1. Okay, so now let's find the eigenvectors. Okay, the eigenvectors depend on the eigenvalue. So we're going to take R equal to negative 1, and then we're going to take R equal to 1 separately. So when R is equal to 1, we're going to go back and look at, we want to find the U values so that A minus Ri times U equal to 0. Okay, so let's look at the A minus Ri. This is just this matrix, but with -1 now filled in for the R value. So this is going to be 2 minus -1, -3, 1, and -2 minus a -1. So that times U. So that's going to be 3, -3, 1, -1. And we want to find those values for U that make that equal to 0. This is how we find our eigenvectors. Okay, so now to solve this. This is just a system. If you want to write U as U1 and U2, all you're trying to do is solve a system. If you want to use the Gauss-Jordan elimination to do this, it comes out pretty simply. Or you can use a calculator, and I'll show you how to do that when we get to a larger one. Okay, so for right now, I'm going to go ahead and take that first, I'm going to build my augmented matrix. That's 3, -3, and I'm putting that extra column of zeros for the numbers on this side. And then I've got 1, -1 with 0 over on that side. This is the 0 vector over here. Okay, so we've got a 2 by 2 matrix here. U is an eigenvalue. It's going to have the dimensions of n by 1, so it's a 2 by 1. And so the 0 over here is actually a 2 by 1 matrix. Okay, so now, again, going through the row operations that we've done before, I'm going to divide the first row through by 3, and I get 1, -1, 0. The second one, okay, I'm going to take a multiple of row 1 and add it to the second row. So -1 times row 1 added to row 2 will make this 0, 0, 0. Or if you just want to think of just adding those two rows together. Okay, so our values, we're solving a system here, and the system 1, -1, 0, 0 times U, and I'm going to go ahead and rewrite this as U1, U2. Okay, we're trying to find U1 and U2. Well, that's equivalent, if you expand it out, multiply it out, that's equivalent to U1 minus U2 equal to 0. And the second equation just gives you U1 minus, or 0 equal to 0. So that tells me then that U1 is just U2. Okay, and remember, if you didn't have an entry in the second column for U2, that meant that U2 was a free variable. So let's let U2 equal to some value t. And that means that U1 has to be just the t as well. So our vector, eigenvector, is the U1, U2, which we said U1 was t and U2 was t. And so you could rewrite that as just t times 1, 1. Now you can pick any value for t that you'd like. Normally we just pick 1 or -1 to get rid of negatives if we want to. So an eigenvector that we can use is any multiple of the vector 1, 1, and I'm just going to choose the vector 1, 1. So I'm going to say that U is equal to 1, 1 for the eigenvalue of -1. So keep this one in mind. That's one of our pairs. Okay, so now we need to find the eigenvector that goes with r equal to 1. Okay, so now this is eigenvector. I'm again trying to solve for a minus ri times u equal to 0. We're looking for the u values. Fill in the specific r. That means put 1 into this matrix for a minus ri, and you end up with that'll be 1, -3, 1, -3. Remember, 0 is just 0, 0. Okay, so if you want to multiply it out, whatever you want to do here to solve for U1, U2, you can write it as a system and solve it with elimination, or you can use Gauss-Jordan on it. Because the rows are the same, this matrix is equivalent to 1, -3, 0, 0. So sometimes they'll just work with the matrix and not even put the zeros, because having the zeros on the other side really don't, they're not affected when you're going through the row operations. Okay, and I got the first matrix here by taking the augmented matrix, which was A with the column of zeros, and then subtracting, multiplying row 1 by -1 and adding row 2. Okay, so now this is equivalent to U1 minus 3U2 equal to 0. That means U1 is 3 times whatever U2 is. So we're going to let, in the vector U1, U2, I'm going to let U2 be 1, or T. Okay, so if U2 is equal to T, that means U1 is equal to 3T. So that means any multiple of the vector 3, 1 would be an eigenvector for r equal 1. So U is equal to 3, 1 for r equal to 1. Okay, so we found 2 eigenvalues and the corresponding eigenvector. Now, when you take the set of all vectors, we're looking for this first one. This is all multiples of 1, 1. Okay, so that's a set of vectors that when you add it to the 0 vector, it's called a subspace. Okay, so if you take linear algebra, you'll learn more about subspaces. Okay, likewise, any multiple of 3, 1 combined with 0, all those multiples with the 0 vector make a subspace. All the subspaces together is called an eigenspace. So these are eigenspaces for each of the eigenvalues. Okay, now let's find eigenvalues and eigenvectors for a matrix A, a 3 by 3 matrix. Okay, so again, we want to find R so that A minus Ri times U is equal to 0, which means that the determinant, for there to be non-zero U's, that means the determinant of A minus Ri has to be 0. Okay, so the determinant, first let's find A minus Ri. Just subtract R in the main diagonal. So it's 1 minus R, and 5 minus R, and then everything else stays the same. Okay. So we want the determinant of that matrix. We want that to be equal to 0. That will be our characteristic equation. Okay, so now to find the determinant of a 3 by 3, remember we're going to need to expand on a row or a column. So this becomes I'm going to expand on row 1. It's 1 minus R times the determinant of minus R, 1, minus 4, and 5 minus R. And then minus 2 times the determinant of 1, 1, 4, 5 minus R. And then minus 1 times the determinant 1 minus R, 4, negative 4. Okay, so that's 1 minus R. Okay, we'll expand everything out. Multiply inside the brackets first. So this is going to be R squared minus 5R plus 4. Now I'm going to notice here, just to help me simplify this, I'm going to notice that there's going to be an R minus 1 factor in each of the terms that I have here. If I take a minus 1 out of that, it'll be minus 1 times R minus 1. And over here, if I take a minus 4, I'll take a 4 out of the parentheses there. I'm going to have the minus 1 plus r there as well. So I've got the r minus 1. So here I'd have to take out the minus 1 first. So let me go ahead, and then this I'd need to factor. So let me go ahead and do that. I can multiply it all out, but then I have to refactor. So if I can find a common factor before I get to that point, it's better. So here I've got r minus 4, r minus 1. And here I'm going to take out a minus 1, so that's going to make my plus 2 times r minus 1. And then I'm going to have minus 4 times r minus 1. Okay, now we see the r minus 1 factor. Take it out of everything. So we're going to have these two multiplied together. So that's going to be minus r squared minus 4 plus r plus 4r. And then plus a 2, and then minus a 4. So we've got minus r squared plus 5r minus 6. Okay, let's take a negative 1 out to make it easier to factor. I have a negative 1 times r minus 1. This becomes r squared minus 5r plus 6. So we've got minus 1, which we could divide both sides by minus 1, r minus 1, r minus 2 times r minus 3. Okay, so this is our characteristic equation. Okay, and the characteristic polynomial would just be the left side of that. Okay, so now we've got 3 eigenvalues. We've got r equal 1, r equal 2, and r equal 3. Okay, so I need to look at this equation for each one of those. So I'm going to put in r equal 1 into this matrix, and I end up with 0, 2, negative 1, 1, negative 1, 1, 4, negative 4, 4. We want that matrix times u equal to 0. And 0 will be a 3 by 3. Okay, so now the way you can solve this, you can just row reduce this matrix, okay, because the last column will never change from all being zeros. So a lot of times they'll just take that 3 by 3 and put it in their calculator or do the row operations. We would need to change the order of the rows since there's no number in the first column on that first one. So let me show you how to do this with a calculator. We're essentially just solving for the, we're solving this system to find u. Okay, so I've got my calculator up. I have a matrix button, which is underneath the x inverse button. So I'm going to second matrix. I want to edit. I need to enter this matrix that I have. You can either enter a 3 by 4 or 3 by 3, whichever one you want to work with. So I'm going to just choose matrix A. I'm going to set it to be a 3 by 4. So we have 0, 2, negative 1, 1, negative 1, 1, and then negative 4. Oh, I didn't get that last column. Okay, 0, 2, negative 1. Yeah, I got them off. Let me go back and fix that. Okay, so when I go into the matrix again, I'm editing. I'm going to go ahead and make it a 3 by 3. The last column's always zeros, so they don't tend to, it's always going to stay zeros. So I've got the numbers listed: 0, 2, negative 1, 1, negative 1, 1, 4, negative 4, 4. So I've got those entered in the 3 by 3 matrix. Now, you go back to the matrix command again, and you're going to go to math, and then if you scroll down, you get to a command called RREF, which is reduced row echelon form, which is just doing the Gauss-Jordan elimination on the matrix. Okay, so I want to choose that, and then I need to specify the matrix. So I'm going to go back to matrix. Oops, I didn't see that command there correctly. I'm going to go back to matrix, math. Choose B. Okay, now I pick the matrix that I want to do it on, and I have it highlighted, matrix A, so I just choose that. And so that's RREF of A, and then hit enter. And so all that does is it does the row operations, and it reduces this matrix down. This is a row equivalent matrix, so they use that little symbol, little squiggle, to say it's equivalent to 1, 0, 1/2. Now if you wanted to see it in fractions, just do the math button. So I've got to go back and get my mouse on here. Do the math and switch it to fractions. Okay, so 1, 0, 1/2, 0, 0, 1, negative 1/2, and you should have rows of zeros, 1 or 2. Okay, so this is just solving the equation, the system. If I can get rid of this. This matrix times u equal to 0, 0, 0. So now rewriting it in terms of equations, remember the first column is the u1 coefficients, the second was the u2, and the third one's u3. So we have that u1 plus 1/2 u3 would be equal to 0, and we have u2 minus 1/2 u3 is equal to 0, and then the third equation doesn't give us anything. So that means u3 is our free variable. It can be anything. So I'm going to let u3 be equal to t. And so that means then that u1 will be minus 1/2 t, and u2 is 1/2 t. So writing our eigenvector, u1, u2, u3, it'll be negative 1/2 t, 1/2 t, and then t. And then just take the t out. That's t times any multiple of negative 1/2, 1/2, 1. Which, just to simplify things, let's choose t equal to 2. 2 or negative 2. That gives us then, we're going to use the u of negative 1, 1, 2. And that's the eigenvector for r equal to 1. Okay, and then you just repeat the process for each of the other eigenvalues. Okay, so r equal 2, I'm going to speed this up a little bit. R equal 2, we're going to go back to this matrix, and we're going to have 1 minus 2, so negative 1, 2, negative 1, 1 minus r, and what was that? 1, and then 4, negative 4, and then 5 minus r, so 3. So we're trying to solve this equal to 0. Let's take this matrix. Whoops, that middle one should have been minus 2. I didn't change that r out. Okay, so now let's row reduce this matrix. Okay, so I'm going to go to matrix, edit. I'm going to go ahead and use the 3 by 3 that I already did. I already got the size in there, so negative 1, 2, negative 1, 1, negative 2, 1, oops, 4, negative 4, 3. Okay, I want to do RREF. I didn't get out of that, quit out of that command. Okay. Okay. RREF, the math. Pick the matrix. Okay. So this matrix is row equivalent to 1, 0, 1/2, 0, 1, negative 1/4, and then 0, 0, 0. Okay, so that's equivalent to U1 plus 1/2 U3 equal to 0, and U2 minus 1/4 U3 equal to 0. So U3 is free. I'm going to let U3 be equal to t. So that means that my vector U1, U2, U3 will be negative 1/2 t, 1/4 t, and just t. So that's t times negative 1/2, 1/4, and 1. So I'd probably choose t equal 4. And so my eigenvector would be negative 2, 1, 4 for r equal to 2. Okay, so now we have one more. So we have r equal 3. Okay, so r equal 3. Fill in 3 into the matrix. We're going to have 1 minus the r, so negative 2, 2, negative 1, 1, negative 3, 1, 4, negative 4, 2. Okay, row reduce this matrix. Just going to move this over out of the way so we can see the... Okay. Edit. Got my size in, so 3 by 3. Negative 2, 2, negative 1, 1, negative 3, 1, 4, negative 4, 2. Okay, verifying. It looks all good, so let me quit out of that so I don't change that last entry again. Now I'm going to go back to the RREF command. So under math, choose matrix A. Okay, and so this matrix is row equivalent to, whoops, change the whole. One, 0, 1/4, 0, 1, negative 1/4, and 0, 0, 0. So it's U1, U2, U3. Okay, so now rewriting this as a system of equations, I have U1 plus 1/4 U3 equal to 0. I have U2 minus 1/4 U3 equal to 0. And U3 again is free. So U3 will be t. U2 then will be 1/4 t. And U1 will be negative 1/4 t. So our vector will be, I'm going to go ahead and take the t out. T times minus 1/4, t times 1/4, and t times 1. And so this is my u, choosing t equal 4. Then we're going to have our u will be equal to negative 1, 1, 4. And that goes with r equal 3. Okay, so we found the eigenvectors and eigenvalues for each one. Okay, so now we know that if we have an equation in the form a x prime equal to a times x, that a solution is going to be of the form x equal to u e to the rt, where r is an eigenvalue and u is the corresponding eigenvector. Okay, now suppose that A is an n by n constant matrix that has n linearly independent eigenvectors. Okay, and we're going to let r sub I be the eigenvalue corresponding to each eigenvector u sub I. Okay, so that means that these solutions, the u's times the e to the rt's for each one of those eigenvalues and eigenvectors, form a fundamental solution set for that system of equations here. Okay, so the general solution then for the system of equations that we have here looks like this. All we're doing is we're taking linear combinations, constants times each of those solutions in that fundamental solution set. C1 e to the r1t u1 plus C2 e to the r2t u2 all the way out to Cn e to the rn t times un, that vector. Okay, so let's show what that looks like with some specific cases. We saw that for the system x prime equal to ax, where a was equal to 2, -3, 1, -2, we saw that we had two eigenvalues, r equal 1, that had the eigenvector 3, 1. That was a eigenvector. Any multiple of that would work as well. And r equal to -1 had the eigenvector 1, 1. Okay, so solutions then. The fundamental solution set would look like e to the 1t times the vector 3, 1. What I'm doing is the r times the e to the rt, comma, and then we'll have 1, 1 e to the -1t. So that's our fundamental set of solutions. Okay. Our general solution then is going to be multiples of those. So x of t will be C1 times 3, 1 e to the t plus C2 times 1, 1 e to the minus t. Now the order these are in doesn't make any difference. Now if you want to see what this looks like compared to what type of solutions we got previously when we had this type of system, I'm going to go ahead and just multiply the matrices by e to the t or e to the minus t in C1 and C2. So this is the same thing as x of t equal to 3c1 e to the t, c1 e to the t, plus c2 e to the minus t, c2 e to the minus t. So our two solutions, remember this x is just x1 and x2. Our solutions would be 3c1 e to the t plus c2 e to the minus t. That would be our x1. And our x2 would be c1 e to the t plus c2 e to the minus t. So in matrix form, you could leave it this way, or you could write it also as x1 equal the first entry, which is how we looked at it in previous chapters. And so there would be our two solutions. Now let's just go back and remind you what this looks like. This is x prime equal to a times the x. And our x prime is x1 prime and x2 prime. It's that vector. So this is the equivalent system is x1 prime equal to 2x1 minus 3x2 and x2 prime equal to 1x1 minus 2x2. So this is the system that we were solving. We just wrote it in matrix form by pulling out the A, the coefficient matrix, and this is we just solved it using vectors and matrices and got the same exact solution we would have had we solved it with methods in the previous chapters. Okay, so now we know if we have n eigenvalues and eigenvectors for a matrix that's n by n that will have the fundamental set of solutions. We have all the possible solutions there. If you have r distinct eigenvalues for a matrix, and u sub I is the eigenvalue associated with it, then those eigenvectors will be linearly independent. So to get that fundamental set of solutions, we have to know that we have n vectors that are all linearly independent. So then another result is that if the n by n constant matrix A has n distinct eigenvalues, and then the eigenvectors associated with it, or the r sub I, the u sub i's, then this is a fundamental solution set for the matrix. So that tells me we do have all the possible solutions. There's n of them when you have an n by n matrix A, which meant you had n equations with n unknowns. Okay? Okay, so now let's look at this equation of this system. I want to solve this initial value problem. The first thing I would do is notice I've got this equation, x prime equal to a times x. Okay, so it's that homogeneous equation that we've been solving. So we can solve this by finding the eigenvalues and the eigenvectors. Now this is the same problem that the same A that we used previously. So we've already found that we had three eigenvalues, r equal 1, r equal 2, and r equal 3. And the eigenvalues that are associated with each one of those, so we can call this r1 and u1, r2, r3. So the corresponding eigenvectors were negative 1, 1, 2, negative 2, 1, 4, and negative 1, 1, 4. Okay, so that's three distinct eigenvalues and eigenvectors for a 3 by 3 matrix. So I know that the fundamental set of solutions will be the u1 times e to the 1t, and then the u2 e to the 2t, and then the last eigenvector e to the 3t. That's our fundamental set of solutions. So our general solution then will be x of t equal to c1 times negative 1, 1, 2 e to the t plus c2, just taking the linear combination of the three fundamental solutions, or all the solutions in the fundamental solution set. Okay, so now I just want to show you another way to look at this. That is the general solution. So I can use that to plug in my z0 for the t value here and solve it. Let me show you another way to write this, though. I can rewrite this as I'm multiplying the eigenvector and eigenvalues, and I'm going to have a minus e to the t, 2e to the t in the first column, minus 2e to the 2t, e to the 2t, 4e to the 2t, and then minus e to the 3t, e to the t, 3t, and then 4e to the 3t. Okay? The x of t can be thought of as a product. Okay? So now if you just multiplied out the three vectors that I had on the right side and then rewrote them as a product of a matrix with a vector, you'll see that these two things are equivalent. And notice this was that fundamental matrix that has all of our solutions in the columns. So the solution here was actually minus e to the t, 2e to the t in those entries. Okay, so now I'm just doing this to make it a little easier to get our solution set. Now let t equal to 0. So that means that x of 0, I'm plugging in 0 for t everywhere. So this is going to be negative 1, 1, 2. Remember, e to the 0 is 1. Negative 2, 1, 4. Negative 1, 1, 4. Okay, but we're told that x to the 0 is equal to negative 1, 0, 0. So now we're just solving a system of equations again. If you want to distribute it out and write it as a system, you can. Let me just put the constant terms over here. Okay, so you can write that out and solve it using elimination if you want to, or let's just use our augmented matrix and do it with the calculator. I'm going to set the matrix up. I'll just do it over here. Negative 1, negative 2, negative 1. I'm going to add an extra column, negative 1, 0, 0. I'm looking for C1, C2, C3 that make all these true. Okay, so I just set the A matrix up here, and then this is the B. So this is like AX equal to B when you're solving a, so here's the B, and we're just trying to find the value. So now, using my calculator, okay, I'm going to edit. I need to enter the matrix. This time I am going to make it a 3 by 4 since I don't have all 0 entries. So I want to edit this matrix and make it a 3 by 4. Okay, negative 1, negative 2, negative 1, negative 1. 1, 1, 1, 0, 2, 4, 4, 0. Okay, and if I just want to be sure I got everything entered right, I can just come down here and, whoops, I changed that last entry. Be sure I quit out of that edit mode or I'll mess it up. Okay, let's just go check that last entry. Be sure I have it right. Okay, that looks like it's all correct. Okay, so quit out. Okay, so now just to confirm that the matrix is what I think it is, I'm just going to print it out. There's negative 1. Okay, so now let's do RREF on matrix A. So go to matrix, math. I chose the wrong command. I didn't. Okay. I didn't go down enough. RREF, matrix A. Okay, so this is row equivalent to the matrix 1, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, negative 1. So now if you go back to your system, so if you come back, this system is equivalent to the system that we have here. 1, 0, 0, 0, 1, 0, 0, 0, 1. We were looking for C1, C2, C3. And now our new constants are 0, 1, negative 1. This is our last constants, and this is the coefficients for A. So now that tells me that C1 has to be 0, C2 has to be 1, and C3 has to be negative 1. So those are the constant values that will make x of 0 equal to negative 1. So we have 0, 1, negative 1. So 0, 1, negative 1. Okay, and that should come out to be this when you plug in 0 for the t. Okay, so we've found our solution then is this, x of t. So if we put 0 in here, 1 in here, we're going to have negative 2, 1, 4 e to the 2t minus 1 times minus 1, 1, 4 e to the 3t. And you can multiply that out if you want to. You can write them as separate equations for x1, x2, x3 if you'd like to. Remember, x is just the 3 values. So this would be minus 2 e to the 2t plus 1 e to the 3t. E to the 2t minus e to the 3t. 4 e to the 2t minus 4 e to the 3t. So then we've got each equation. X1 is this, X2 is this, and X3 is this. Okay, so if we have a matrix that's an n by n matrix, and it has n distinct eigenvalues and corresponding eigenvectors, then we have the fundamental set of solutions. So when can we count on that? Well, there's one specific case where we'll be able to know that we're going to get n distinct eigenvectors and eigenvalues for a matrix. And that's when you have a symmetric matrix that has real values. So a real symmetric matrix is a matrix that has real entries, and the transpose of the matrix is the matrix itself. And that's the definition of a symmetric matrix, is one whose transpose is the same as itself. So if A is an n by n real symmetric matrix, there will always exist n linearly independent eigenvectors. Okay, so I want to find the general solution of this equation, x prime equal to ax, where this is the matrix A. Now notice A is symmetric. The row 1 is the same as column 1. Row 2 is column 2, and row 3 is column 3. So this is a symmetric matrix. So by this result that I just quoted, we know we'll find n linearly independent eigenvectors. Okay, so let's find the eigenvalues and the eigenvectors for this matrix. Okay, so to find the eigenvalues first, we're going to solve for the determinant of A minus Ri to be 0. Okay, and ultimately we're looking for the eigenvectors then that will have A minus Ri times U that equal to 0. Okay, so if this is A minus Ri is just subtracting R from each diagonal entry. And all the other values will be the same. Okay, we want this determinant to be 0. So now let's expand on the first row. Minus the negative 2. And then plus 2. Okay, I'm squaring out 1 minus R. I'll have a plus 1, and then that minus 4 will make it minus 3. This is going to give me a 2R minus 2 minus 4, so minus 6. Okay, so this is going to be, I'm combining this stuff, I'm going to have a 2R minus 6. Okay, I notice here that I actually have an R minus 3 and an R plus 1. And I see that I have an R minus 3 in the other two terms. So let's go ahead and take a 2 out of here, and that's going to be 4 times R minus 3. Same thing here, that'll be 4 times R minus 3. So now I can take out an R minus 3 out of each of the terms. And again, this is my characteristic equation. So R minus 3, and now I have 1 minus R times R plus 1, which will be R plus 1 minus R squared minus R. And then take r minus 3 out here. I have a plus 4, and same thing on the last one. So I'm going to go ahead and take a minus 1 out. So I'll be able to factor it more easily. So that'll give me the positive r squared. The r's cancel. I have a plus 9, so I'm taking the minus 1, so that's r squared minus 9. Okay, so that's r minus 3 times r plus 3 times r minus 3. You can leave the minus 1 or divide both sides by it either way. Okay, so here I have an eigenvector, or an eigenvalue that repeats itself. I see that r equal 3 is an eigenvalue with multiplicity 2. But because this is a symmetric matrix, I know I'm going to end up with n linearly independent eigenvectors. So my two eigenvalues are r equal 3 and r equal negative 3. So now let's find the eigenvectors that correspond to each. I've still got to get 3 eigenvectors to get 3 separate solutions, though. So r equal 3. Okay, go back and we're going to look at a minus ri times u equal to 0. We're trying to find the u that makes this true. So the a minus ri will be, okay, I just want to take this matrix that I'm working with up here and subtract and replace the r with 3. So I'll have negative 2, negative 2, 2, negative 2, negative 2, 2, 2, 2, negative 2. Remember the 0 just as the 0 vector. Okay, so again, I'm just going to take this matrix and row reduce it and find an equivalent system. And then I'm going to repeat the same thing with r equal to negative 3. I'm going to go ahead and set this up so I'll be able to use the calculator at once. Okay, so putting in negative 3 for the r's up here, I'm going to have 4, negative 2, 2, negative 2, 4, 2, and 2, 2, 4. Okay, so clear this out. I'm just going to use a 3 by 3. So I'll choose this matrix, but make it a 3 by 3. Okay, negative 2, negative 2, 2, negative 2, negative 2, 2, 2, 2, negative 2. And double checking, that looks good. I'm going to quit out of this and then go back in and let's do the RREF. So I need to go to math. Of matrix A. Okay. So I lost it. Okay, so this matrix is equivalent to 1, 1, negative 1 with all zeros in the last 2 rows. Okay, the next one. Okay, edit. Okay, 3 by 3. And now I have 4, negative 2, 2, negative 2, 4, 2, 2, 2, 4. Quit to get out of that mode. Okay, now go back down to RREF, so math. Okay, and that is rho equivalent to 1, 0, 1, 0, 1, 1, 0, 0, 0. Okay, so now let's find our solutions. Okay, now rewriting these as a system, back in the equation form. Multiply row 1 by the column, and I get u1 plus u2 minus u3 has to be 0. And then I get 0 equals 0 for the last two. That tells me u2 and u3 are free variables. There's not columns that have the 1, on other rows for those. So u2 can be anything. I'm going to let it be s, and u3 I'm going to let be t. And that means that u1 then is going to be minus u2 plus u3. So u1 will be s minus s plus t. So if I want to write the eigenvector, u1, u2, u3, u1 is minus s plus t, u2 is just s, and u3 is just t. I'm going to split this into two separate vectors, a sum of vectors that have the s parts. If there's no s, I'm going to assume it's 0 s's, and the t parts, t0, t. Okay. Now, by doing that, I can break this into s times negative 1, 1, 0 plus t times 1, 0, 1. Okay, what that's saying is that the eigenvectors associated with r equal 3 or any linear combination, any multiple of negative 1, 1, 0 and 1, 0, 1. This is a two-dimensional eigenspace. Okay, so it's like a whole plane in 3 space. So I have two separate vectors. So what that means is that I have two vectors in the fundamental set of solutions. One would be minus 1, 1, 0 e to the 3t, and the other one would be 1, 0, 1 e to the 3t. So that gives me two of my 3 vectors, which is nice because remember r equal 3 is the one that had a multiplicity of 2. So this one had multiplicity 2, and so what we're hoping is that it has 2 eigenvalues, eigenvectors associated with that eigenvalue. That way we'll still end up with our 3 distinct linearly independent solutions. This next one, I have u1 plus u3 equal to 0 and u2 plus u3 equal to 0. That tells me that u3 is a free variable, so I'm going to let u3 be equal to t, and u2 then is negative u3, which is negative t, and u1 is negative u3, which is negative t. So writing my vector u1, u2, u3, it's negative t, t, which is just t times negative 1, negative 1, 1. So an eigenvector associated with r equal minus 3 would be negative 1, negative 1, 1. So that means a fundamental solution would be negative 1, negative 1, 1 e to the minus 3t. So here's our fundamental set of solutions. And so if I'm looking for the general solution, which they want the general solution up here, the general solution is x of t equal to, that's the vector x, so that's x1, x2, x3 is a column vector. It would be c1 times negative 1, 1, 0 e to the 3t plus c2 1, 0, 1 e to the 3t plus c3 negative 1, negative 1, 1 e to the minus 3t. So that would be one form, that's the vector form of the general solution. Or if you want to write it as each individual dependent function, remember x is x1, x2, x3, so that means that x1 is negative C1 e to the 3t. I'm taking the first entries in each vector, plus C2 times 1 times e to the 3t, minus C3 times the 1 e to the minus 3t. That would be your x1. Your x2 will be C1 e to the 3t, the 0 e to the 3t, and then it's going to be a minus C3 e to the minus 3t. And then our x3 will have 0 e to the 3t's, C2 e to the 3t, and then plus C3 e to the minus 3t. So this would be the form of where you're writing each equation, each dependent function separately. Okay? So when you have a symmetric matrix, we're guaranteed we're going to get n distinct eigenvectors, so that's going to give us our fundamental set of solutions, and we can easily get the general solution for it. Okay, now what do we do when there's an eigenvalue that has multiplicity 2, but there's only one eigenvector associated with it? That's going to leave us short on our fundamental solutions in that set. So the second solution can be found following this formula. Okay, now k is just going to be a constant vector and p is going to be a constant vector. We're going to have the e to the rt times some vector, p, but then we'll have a t times e to the rt times the vector k that we'll have to solve for. So we're going to find k by solving a minus ri times k equals 0, which is what we've done. That's the regular eigenvector that we found in the past. And then once you find k, solve the equation a minus ri times p equal to k. So use that k that we found for the eigenvector here, and then figure out what the p has to be, and then that'll be how you form the second solution. The first one will still be the k times e to the rt. Okay, so I want to find the general solution of this system of equations where the a is given by this. So first let's find the eigenvectors, or eigenvalues. So find eigenvalues. So we want to look at the matrix a minus r times I. We want the determinant to be equal to 0. So that means 3 minus r minus 18, 2, and minus 9 minus r has to have determinant of 0. So that determinant will be 3 minus r minus 9 minus r plus 36 equal to 0. So multiplying this out, we get r squared plus 9r minus 3r, so that's plus 6r. And then we have minus 27 plus 36 gives us plus 9. Okay, so you see that r equal negative 3 has multiplicity 2. So we have one eigenvalue. So now let's see if we can find two eigenvectors associated with that. So now so this is step 1. Step 2 is find the eigenvectors for each eigenvalue. So you find those by looking at a minus the r, which in this case the r is negative 3, so it's going to be a plus 3i times the u equal to 0, which the u is just the k. Okay, so the a plus 3i is just going to be taking this matrix and replacing the r's with negative 3. So it's going to be 6, negative 18, 2, negative 9 plus 3, so negative 6. So we'll have this matrix times u equal to 0. Okay, so let's just row reduce this matrix. Now this one's a pretty simple one. We could do it easily by hand. You could do it calculator. I'm just going to go ahead and divide the first row by 6. So that'll be 1, negative 3. And then when I add a multiple of the first, negative 2 times this row added to the second row, I get a row of zeros. So it's just Gauss-Jordan elimination. That says that u1 minus 3u2 is 0, so that means u1 is equal to 3u2. So if I let u2 be t, that means u1 will be 3t. So that's t times 3, 1 which means we only had one eigenvector associated with the eigenvalue -3. Okay, so we need to have 2, though, to get that fundamental set of solutions. So we know one solution will be of the form x equal 3, 1 e to the minus 3t. That's one of our solutions. Our second solution we're going to get by this. Okay. So we already solved a minus ri times k equal to 0. So this is our k. So now we want to solve this equation for the p. So if k is equal to 3, 1, the a minus ri is just the 6 minus 18, 2 minus 6, and then times p, which is p1, p2, equal to the k. Okay, now this is a system that we're wanting to solve. We can use the calculator, or again, this one's a pretty simple one. If you just take the augmented matrix, 6 minus 18, 3, 2 minus 6, 1, divide the first row by 6, we'll get 1, -3, 1/2. And then a multiple of this one, let's see if we take 2 times this row and add, or -2 times this row and add it to the second one, we end up with a whole row of zeros. So that tells me that 1, 0, -3, 0 times p1, p2 has to equal to 1/2, 0. That says that p1 minus 3p2 is equal to 1/2, and then 0 equals 0. So that means that p1 is 3p2 plus 1/2. So our vector p1, p2 now if I want to let p2 be a constant t, I can. I'm just going to leave it as p2. You don't have to change the variable. And then we'll just leave p2 as it is. So that means if I split this into 2 vectors, I've got p2 times 3 and 1 plus the vector 1/2, 0. I just split the p's up and the numbers, the constants added to it, and so it comes out to be that. Now p2 can be anything. So what I'm going to do is I'm going to choose p2 to be 0. And so that's going to give me my vector p to be 1/2, 0. So my second solution up here is going to be x2 equal to the k, which is the 3, 1, t e to the minus 3t plus the p e to the minus 3t. So that's my second solution. Okay, so to find the general solution, we'll have x equal to c1, 3, 1, e to the minus 3t plus c2 times 3, 1, t e to the minus 3t plus 1/2, 0, e to the minus 3t. Okay, so if you want to write this as separate dependent variables, x1, remember x is x1 and x2, will be 3c1 e to the minus 3t plus 3c2 t e to the minus 3t plus 1/2 c2 e to the minus 3t. And our x2 will be c1 e to the minus 3t plus C2 t e to the minus 3t, and then plus 0. And that looks very similar to some of the things we did before. Remember when we had that repeated root before, we had to, repeated solution, we had to do a t times the e to the minus 2t to get a second solution, and that's what we've got. You could combine these e to the minus 3t's and say that's 3c1 plus 1/2 c2 e to the minus 3t, and then a plus 3c2t e to the minus 3t. You could write it that way as well. Okay, so now what if we have an eigenvector or an eigenvalue that had multiplicity 3 and only have one eigenvector associated with it? That means we need to find 2 more. So let's go through a situation like that. If we have that situation, you have only one eigenvalue or eigenvector, should be vector, associated with an eigenvalue of multiplicity 3. The second solution we've seen comes out to be this. The third solution is going to look like this. And so it's very similar. You get the k, which is our u, and then you'll solve for the p by using the k, and then you'll solve for the q by using the p. Okay? Okay, so let's find the general solution of this. So first find the eigenvalues. So a minus ri times, or the determinant of that is equal to 0. 2 minus r, 1, 6, 0, 2 minus r, 5, 0, 0, 2 minus r. Minus 1, expand on the first row. And then plus 6 times. Okay. Now these both have a value of 0. So we end up with just 2 minus r cubed. Which means, okay, so here's our characteristic equation. And our characteristic polynomial is simply the left side. Okay, so we have one eigenvalue with multiplicity 3. Okay, so now find the eigenvector. So we're going to have 2 minus 3, so negative 1, 1, 6, 0, negative 1, 5, 0, 0, negative 1. Okay, we're going to use the calculator to row reduce this. Negative 1, 1, 6, 0, negative 1, 5, 0, 0, negative 1. Double checking everything. Okay, I'm going to quit out of that. Now go to RREF, so math. Oops, well, carried away. Matrix A. Okay, and I see that I don't get what I need to get, and I go back and check where my mistake was. I used the wrong eigenvalue. So coming back over here, the eigenvalue was 2. So our matrix then, A minus Ri, becomes 0, 1, 6, 0, 0, 5, 0, 0, 0. Okay. There's not much row reduction that is needed here. Okay, we're trying to solve. Okay, that says that U2 plus 6U3 is 0, and 5U2 is 0, which means that U2 is 0, and that tells me that U3 has to be 0. U1 can be anything. So that means my vector, U1, U2, U3, there's no limits on the U1, would be U1, 0, 0. So it's any multiple of the vector 1, 0, 0. So my eigenvector is 1, 0, 0 that's associated with the eigenvalue 2. So this to 2t, that's one solution to my system of equations. Okay, so now let's find, we're looking for we've got our k. And now we need to find p so that a minus 2I times the p is equal to k. Okay, so we're going to have the a minus 2I again is over here. Okay, so you can row reduce the matrix. Now, because it's so small, I'm not even going to bring up my calculator. I'm just going to use the row operations. The last row is always going to be zeros. The third one, I can make that 0, 0, 1, 0 by dividing both sides by 5. And then I want to eliminate this position, that 6 there, by multiplying negative 6 by row 2 and adding it to row 1. So it would be 0, 1, 0. Negative 6 times 0 plus the 1 is still the 1. Okay, so that tells me then that I've got the system 0, 1, 0, 0, 0, 1, 0, 0, 0 times the p equal to 1, 0, 0. Okay, remember that last column is what's on the other side of the equation. Okay, so now this becomes P2 equal to 1, and let's see, P3, I'm just multiplying first row times the P vector, so that's P2 is 1, and then P3 is going to be equal to 0, and then I don't have any limit on P1. So P1 is a free variable. So I'm going to leave it as P1. P2 is 1 and P3 is 0. So if I want to split this up by putting the p's, so rewriting everything with p's separate from the constant values. Okay, then I have p1 times the vector 1, 0, 0 plus the vector 0, 1, 0. And the simplest thing to do would be to choose p2 equal to 0 or p1 equal to 0. And so that gives me that this is my vector p. Okay, so we've got our k, we've got our p. And now we need to find our Q. So the third thing we need to do is to find when A minus 2I times the Q is equal to the P. So again, we start with this vector matrix. Okay, so I'm going to take the augmented matrix row reduce it. So I'm going to start with second row is 0, 0, 1, 1/5. And then the first row, when I eliminate this 6, becomes 0, 1, negative 6 times row 2 added to row 1 will make that 0. Negative 6 added to 0 is negative 6/5. Okay, so that tells me then that this times the Q's tells me that Q2 is negative 6/5. Q3 is 1/5. Q1 again can be anything. Separate out the parts with the variables, multiples of Q, plus the constant terms. Okay, so the simplest thing to do would be letting Q1 be 0. And so then our matrix, our vector Q, becomes 0 minus 6/5, 1/5. Okay, so now let's form our solution. We've got our K, we've got our P, and now we have our Q. Okay, we know our first solution, X, is whatever the eigenvector was, which was the K, 1, 0, 0 times e to the 2t. That was X1. Our X2 is going to be the K times the t, e to the 2t, plus the p times e to the 2t. So X2 comes out to be 1, 0, 0 t e to the 2t plus 0, 1, 0 e to the 2t. Our X3 is going to be K times t squared over 2 times e to the RT plus PT e to the RT plus Q e to the RT. So it's going to be 1, 0, 0 t squared over 2 e to the 2t plus 0, 1, 0, the p, t e to the 2t plus the q e to the 2t. So now we've got our three linearly independent solutions. Our general solution will be x equal C1 times the first solution plus C2 times the second solution plus C3 times the third solution. And that's our general solution. And there will be some things that will combine, and you can, make it a little more simplified if you wanted to break it into the three x1, x2, x3s and write out each dependent solution. Okay, so you use this method when you have an eigenvalue with a higher multiplicity, but that you don't get separate eigenvectors to match that multiplicity. So when you need to have additional eigenvectors, or additional solutions because you don't have enough eigenvectors, this is how you find them. So you're only doing this method when you're looking for more solutions than what the eigenvectors would give you. Okay, so we find our eigenvalues by finding the values of r that make the determinant of a minus ri equal to 0. We've looked at the cases when r came out to be distinct real numbers, and we've looked at the case when r was a repeated real number. So now the other possibility is roots to this equation would be when r is a complex eigenvalue. So if the matrix A has complex conjugate eigenvalues, remember that if a plus bi is a root to a polynomial equation, then a minus bi will also be a root. So we always know that we'll have complex conjugate pairs when you're dealing with the eigenvalues. So now, once we find the eigenvalue, and it comes out to be complex, we're going to go ahead and look for the eigenvectors and look at the real and the imaginary part. So we're going to separate A is the real part of the eigenvector, and B will be the imaginary part. Once we get those, then our solutions to this differential equation system will look like this. We'll replace the real part here and here, and the imaginary parts here and here. So those will be they will be vectors that are real and imaginary parts of those eigenvectors. Okay, so let's look at an example. I want to find the eigenvalues. So we look at a minus ri, and we want the determinant to be 0. So it's minus 1 minus r, 2 minus 1 minus 3 minus r. That determinant is so we get r squared plus 4r plus 5 equal to 0. Okay, so when you solve this, you're going to see it doesn't factor. Instead, r comes out to be, using the quadratic formula, minus 4 plus or minus the square root of 4 squared minus 4 times the 1 in front of the r squared, and then the c is the 5. All of that over 2 times the 1. So that's negative 4 plus or minus 2i over 2. So our r values come out to be negative 2 plus or minus 1i. Okay, so now let's look at the eigenvector. I'm going to just look at the eigenvalue minus 2 plus I. I don't need to worry about both of them, just look at one of them. For that particular eigenvector, a value, the eigenvector will be the u's that make this true. I'm just going to place that. So I'm just replacing the r's up here with minus 2 plus I. So remember, I've got the minus in front here. So it's going to be minus 1 minus, so it's going to be plus a 2, so that's going to be a 1, and then minus I. And then we'll have minus 3 minus the negative 2, so it's going to be a minus 1 minus the I. Okay, this says that 1 minus I times U1 plus 2U2 is 0, and minus U1 plus minus 1 minus I U2 is equal to 0. Okay, I just need to work with one of these two. I'm going to take the second one and just solve it for U1. So U1 will equal to minus 1 minus I times U2. I can pick U2 to be any value. So just for simplification, I'm going to choose U2 to be negative 1. So that makes U1 equal to 1 plus I. Break it into the real and imaginary parts. This will be 1 negative 1 plus I times 1, 0. Okay, this is my A, and this is my B in the eigenvalue A plus BI. Okay, so when you go back to the solution, notice you have the e to the alpha t, and then you've got your cosine of beta t times the A, and then you'll have minus the b times the sine of beta t. Okay, and then the second solution, again, take the e to the alpha t out, and now you have a sine of beta t times the A plus the b cosine of beta t. Okay, okay, so our solutions then will be, where's my alpha? Okay, looking at the eigenvalue here, the alpha is negative 2 and the beta is equal to 1. So we have e to the minus 2t, the A cosine of 1t minus the b sine of 1t. All I'm doing is filling in my A and the B. A's here and here. That was A. The B goes here and here. This is my B. Beta was the number in front of the I, and the alpha was a constant term. And that's your solutions. Okay, so this is my x1, this is my x2. So if you want the general solution, we'll have that x is equal to C1 and you can write this any number of ways. If you want to distribute it out, it's 1, negative 1, e to the minus 2t cosine of t minus 1, 0, e to the minus 2t sine t plus C2 times the second. And there's not a unique form for this because it all depends on whether you put U1 in terms of U2 or vice versa. So it's going to look, the book has it done a little bit differently just because they solve for the other variable. E to the minus 2t. Okay, so there's your general solution. And you can break this up into the x1 and the x2 by looking at the first components all the way across in the second components. But that is your general solution. Okay, so we've solved a homogeneous system of linear equations that was of the form x prime equal to ax of t. Okay, now what we want to do is, what if there's another function that's added onto that? So when some of the terms don't have the dependent variables in them, you just have extra functions of t, how do you find the non-homogeneous solution? Okay, so we're going to do the same thing that we did back in previous chapters. We're going to use the method of undetermined coefficients for certain ones of these. Now we can use this when the f of t's are made up of polynomials, exponential functions, sines, cosines, or finite sums or products of those. So this f of t has to be specific forms for us to be able to anticipate what that particular solution is going to look like. So the solution to this is going to be the solution of the homogeneous system. So we'll start out the same way we have been, find the solutions to x prime equal to ax, and get that general solution to the homogeneous equation, and then find a particular solution to this equation, and that will give us our general solution. Okay, so I want to find the general solution of this equation, x prime equal to, here's my a, x plus t times this vector. Okay, so here is the f of t. Now the f of t, you see, is a vector that's negative 9t, 0, negative 18t. Okay, back when we were solving the second order differential equations and we had a non-homogeneous equation where there was a function on the right, when we had a polynomial such as 9t, we anticipated the particular solution was going to be of the form a constant times the t plus a constant. So I'm going to anticipate my particular solution here looking like at plus b, ct plus d, and et plus f. Now it's a little more complicated when you have multiple variables like this, because we have three different x1, x2, x3 functions that we're trying to do at once. Okay, so now let's first get the solution to the homogeneous system. We saw previously that for x prime equal to this a, 1, negative 2, 2, negative 2, 1, 2, and 2, 2, 1, x of t, the eigenvalues were r equal 3, that had 1, 0, 1 for an eigenvector, r equal, well, it actually had multiplicity 2, and then negative 1, 1, 0 was a second eigenvector for that eigenvalue, and then r equal negative 3 had negative 1, negative 1, 1. So our general solution to the homogeneous system was this. Okay, so now what we need to do is worry about the particular solution. Okay, so we know what our particular solution's form looks like, and so it's going to be a matter of just plugging that into the whole differential equation system. So I need x prime. If this is my x of p, then x p prime will be a, c, e. And then plus the f of t, which is minus 9t, 0, minus 18t. So all I'm doing is I'm plugging in our suspected form for the x sub p into the differential equation. And now I just want to solve this. So I'll have ACE. I need to multiply a times the vector x, which will be 1 times AT plus B minus 2CT minus 2D plus 2ET plus 2F. And then I'm going to go ahead and add on the minus 9T. Okay, row 2, I'm going to have minus 2AT minus 2B plus CT plus D plus 2ET plus 2F. And then the third row, 2AT plus B plus 2CT plus 2D plus ET plus F. Oh, I missed the 2 here. And then minus the 18T. That tells me that A has to be, okay, let me look at all the T's. T times, I've got an A minus 2C plus 2E minus 9. That's all the coefficient of the T on the this first row. And then my constant terms will be B minus 2D plus 2F. Okay, row 2. I have that C is equal to, now my T values will be T times minus 2A plus C plus 2E. Just taking everything here that has the T's. Then I'll get these here in a minute. And then my constant terms. And then the last E. And then the constants will be 2B plus 2D plus F. Okay, so this is going to give us, we have 6 unknowns, A, B, C, D, E, F. This gives us 6 equations with those 6 variables. We're going to equate coefficients of T in each equation and then constants in each equation. So this equation tells me that A minus 2C plus 2E minus 9 has to be 0, since there's no T's on this side. And I know that B minus 2D plus 2F has to be the A, since that's the constant term on the left side. This equation tells me that minus 2A plus C plus 2E has to be 0, since there's no T's over here. And the constant terms are that minus 2B plus D plus 2F has to be C. Now I have that 2A plus 2C plus E minus 18 is 0, since that's the T coefficient on the left. And then 2B plus 2D plus F has to equal to E. So taking these equations, I'm going to group the ones that have A, C, E in them and the ones that have the B, D, F, which aren't just totally separated. Now this is going to be quite an extensive problem to solve ourselves by hand. So what I'm going to do is I'm going to show you how to set it up, and then I'll use my calculator to get the solution using the RREF, the Gauss-Jordan elimination method. So first, since there's 6 unknowns, I'm going to set this up to be a system of equations. I'm going to put A, B, C, D, E, F in order. So the first equation becomes A plus 0b minus 2c plus 0d plus 2e plus 0f equal to 9. The second one, I need to bring the a over, so I'll have minus a plus b plus 0c minus 2d plus 0e plus 2f equal to 0. The third one, minus 2a plus 0b plus c plus 0d plus 2e plus 0f equal to 0. Minus 2b, oops, for the a, 0a minus 2b minus c, bringing it over, plus d plus 0e plus 2f equal to 0. And then I have 2a plus 0b plus 2c plus 0d plus e plus 0f equal to 18. And then 0a plus 2b plus 0c plus 2d minus e plus f equal to 0. So here's a system. 6 unknowns. You'd set it up as an augmented matrix as a 6 by 7 matrix. So we're going to have 1, 0, negative 2, 0, 2, 0, and then 9 is that extra column. Okay, and then I'd use my calculator. So I'm going to pause here and actually enter this into the calculator as a 6 by 7 matrix and do RREF. Okay, so I've gone in and I edited 6 by 7 matrix entering these values, and now I'm ready to RREF. So I'll go back down to math operations here. RREF over on matrix A, that's 6 by 7, and this is what I get. So if you notice, all these are, it's just the identity. Oops. And so I'm looking for A, B, C, D, E, F. And I came out with 5, 1, 2, 0, 4, 2. Okay, so I'm just finding the variables that I had in the order here. Okay, let me get rid of those. Okay, so now come back up to what we chose our particular solution to be and fill in those values. So our particular solution then is 5t plus 1, 2t plus 0, and 4t plus 2. Okay, so if you want to break that up into t times the vector 5, 2, 4, plus the vector 102, you can. But now take the x sub p over here, and the x of h, the solution of the homogeneous, with the x sub p, so the general solution, which is the x of h plus the x sub p, will be c1 e to the 3t plus c2 e to the 3t plus c3 e to the minus 3t Okay, so that's one form, a way to write it. Or you could expand it out. Remember, the x is just the three different variables, the x1, the x2, x3. So our x1 will be c1 e to the 3t plus c2, well, minus, got the minus sign there, minus c2 e to the 3t minus c3 e to the minus 3t plus 5t plus 1. Our x2, I'm just taking the second components now in each vector. So I'm going to have 0, c1, 1, c2 e to the 3t, minus 1, c3 e to the minus 3t, plus 2t plus 0. And then the x3 will be 1, c1 e to the 3t. I'm just taking these third components now for each vector. 0 c2s plus 1 c3 e to the minus 3t plus 4t plus 2. So either form, either as individual dependent variables or in vector form, where you're talking about the vector x here. Okay, so now we want to look at a method to solve the non-homogeneous equations when we don't necessarily have the f of t in those forms, the polynomial, sines, cosines, exponentials. Or it could work in those situations as well, and maybe it'll simplify it. But we want to be able to have a method when undetermined coefficients doesn't work. So let's say that we have a set of solutions. The x1 to xn's is the fundamental set of solutions for the homogeneous system. Okay, so then that means the general solution will look like this. Now, if we expand each of those vectors out like this, and then add all those vectors together, we can get one big vector here that represents that solution, x of t. That's that general solution. Now, I want to look at another way to write this. We could write this as the product of this matrix times C1, C2, Cn. Okay, this matrix was called the fundamental matrix of the system. All we've done is we've taken the vectors, the solutions, x1, x2, and we've written the components in the columns. Okay, so if we write those solutions in the columns, we can look at the solution of the homogeneous equation simply as that fundamental matrix times the vector c, where the c's are those constants that we're multiplying each of the solutions by. Okay, so now we know then that the general solution to the homogeneous system is this. So we're going to extend that by looking for the solution to the non-homogeneous equation and guessing that it's going to take the form of the x of t times some function v of t. Now, this is just like when we did previously when we were looking at variation of parameters, when we were solving the second order differential equations, and the right side ended up being functions that weren't the polynomials, exponentials, trig functions, sines or cosines, or finite products and sums of those. So we used a variation of parameters to be able to, find the solution of that non-homogeneous equation. So we're doing the same idea here. We're guessing that the particular solution will be that x of t, which is that fundamental matrix, times some v of t, and so we just want to find what is the v of t. Okay, so now, if this is the form of the solution and it satisfies this equation, then I'm just going to plug this in for the x's. X of p then, now notice here that x of p is x times the v of t. Both of those are functions of t. So that means x of t, x prime of t, will be x prime of t times v of t plus x of t times v prime of t. All I did was I found the derivative of this using the product rule, and I'm plugging it into this. Equal a times, now the x, we're assuming the x is of this form, x of t times v of t. Okay, and then plus the f of t. Okay, now we're going to use the fact that x prime is the same thing as a of t x of t. So this a times x of t is just x prime. Okay, and that's going to allow us to cancel this term and this term out. So we get that x of t, v prime of t, is equal to the f of t. Now, the x, that's that fundamental matrix that has the solutions that are linearly independent in the columns. So this matrix, since it has columns that are linearly independent, does have an inverse. So if I multiply both sides by x inverse, that tells me then that the v prime of t will be x inverse times f of t. So if I want to find v, v will just be the antiderivative of x inverse of t, f of t. That's where this result comes from. So now, once I find my v, I'm going to substitute it in here. So that means x of p will be the x times the v, which will just be the x times this. This is the v. Okay? So now, if that's the particular solution, so if you want the general solution to the non-homogeneous equation, you'll add the solution to the homogeneous system, and then here's my x of p. So this is the x of h, and that gives you the general solution. So that's the idea here to solving these matrix equations for the non-homogeneous systems using the variation of parameters. Now you have to do it when the function f isn't of those special forms, but you can also use it, and sometimes it simplifies, over using the method of undetermined coefficients. So let's find the solution to this initial value problem. Okay, so first step would be to finding the homogeneous system, the solution. Okay, and we did solve the homogeneous system back in section 9.5, and we got that x of h, well, let me just write the separate solutions. x1 was 3, 1 e to the t, and x2 was 1, 1 e to the minus t. Okay, so that means that our homogeneous solution was C1, 3, 1 e to the t, plus C2, 1, 1 e to the minus t. And we could write that as 3 e to the t, 1 e to the t, e to the minus t, e to the minus t, c1, c2. So this is our x of h. Okay, and this is our fundamental matrix, x of t. We're going to use that when we get this other form. Okay, so we know I want to find the v of t. The v of t will be the integral of the x inverse times the f of t. Once I get the v, I know that my particular solution is going to be the x of t times the v of t. Okay, so let's find x inverse. Okay, x is a 2 by 2 matrix. And we saw that when you had a matrix of the form A, B, C, D, x inverse was just 1 over AD minus BC. Swap the D and the A and just change the signs of the B and the C. Okay, so for this particular matrix then, AD minus BC is this product minus this product. So we're going to have 3 e to the t times e to the minus t minus e to the t times e to the minus t. Now, e to the t times e to the minus t is e to the 0, which is just 1. So this comes out to be 1 over 3 minus 1, which is 2. And so the d is e to the minus t, the a is 3 e to the t, and then I'll just make these others negative. Okay, so this comes out to be 1/2 e to the minus t, negative 1/2 e to the minus t, negative 1/2 e to the minus e to the t. Well, I've got a minus in there. I shouldn't. No, that's right. And then 3/2 e to the t. Okay, so my v of t then is going to be the integral of the product of this with the f. And here's my f. Okay, so let's multiply those matrices out. You're going to have 1/2 e to the minus t times e to the 2t. So that's 1/2 e to the t minus 1/2 e to the minus t. And then we're going to have minus 1/2 e to the 3t plus 3/2 e to the t. Okay. There's two components. We're going to integrate them term by term. So we're going to have 1/2 e to the t plus 1/2 e to the minus t. I'm just taking the integral of each term. Minus 1/6 e to the 3t plus 3 halves e to the t. Okay, we don't need to worry about the constants. We're just trying to find a function v that works. Okay, so that's your v. So now the x sub p is going to be the x times the v. Now this is a sum. Just two components though. Okay, so we're multiplying a 2 by 2 by a 2 by 1, so we will get a 2 by 1. So we've got 3 e to the t times this whole first component. So 3 e to the t times plus e to the minus t times the second component. And then we've got e to the t Okay, and then simplifying. So I've got 3 halves e to the 2t plus 3 halves e to the 0 minus 1/6 e to the 2t, got the exponents, plus 3 halves e to the 0. Then I have 1/2 e to the 2t plus 1/2 e to the 0 minus 1/6 e to the 2t plus 3 halves e to the 0. Okay, so the e to the 2t's be 9/6, so we have 8/6 or 4/3 e to the 2t. I just combined them and got a common denominator and reduced them, plus 3. And then I have 1/6, so 3/6 minus 1/6 will be 2/6, which is 1/3 e to the 2t plus 2. And that's your x sub p. So then, our general solution and you've got lots of ways you could write it. And you could break this up to 4/3, 1/3 e to the 2t plus the vector 3, 2. If you want to break it up that way. Okay, and then we need to find we have initial condition. Okay, so we're given that x of 0 is -1, 0. Okay, so let's plug in t equal to 0, and then this side should be -1, 0. So that's 3c1 and c1 e to the 0, which will just be 1, plus c2, c2 e to the 0, plus 4/3, 1/3 e to the 0, plus 3, 2. Okay, so combining all of those, we have that -1 is equal to 3c1 plus c2 plus 13/3. And then we have 0 equal to c1 plus c2 plus 7/3. Okay, that means 3c1 plus c2 is equal to minus 16/3, and we know that C1 plus C2 would be negative 7/3. Okay, it's easy to solve this for C1 by just subtract the two equations to eliminate the C2. So I'm going to have 2C1 equal minus 16/3 plus 7/3, so that's going to be minus 9/3, which is minus 3. So C1 is negative 3/2. And then we know that C1 plus C2 is negative 7/3, so negative 3/2 plus C2 is negative 7/3. So that means C2, common denominator 6, that's going to be negative 14 plus 9, so that's negative 5/6. Okay, so this was our general solution. We just need to plug in those two values. So we have that x is equal to C1 minus 5/6 and we could leave it that way, or we could expand it out if we want to find the x1 and the x2. So if I write it out in the two different components by combining all those vectors, it's going to be minus 9/2 e to the t minus 5/6 e to the minus t plus 4/3 e to the 2t plus 3, and then minus 3/2 e to the t minus 5/6 e to the minus t plus 1/3 e to the 2t plus 2. So x1 would be this vector, and x2 would be this one. So those are the solutions to the two different dependent variables in the system, x prime equal to ax plus the f that was given. Okay, so use the method variation of parameters either for simplification purposes, or when you have to use it when you have functions that aren't those basic polynomials, exponentials, and sines and cosines. And so this is when you have a non-homogeneous system that you're solving. So it has that plus f of t at the end.